the 2D S wave superconductors at T equals 0, I mean, it is oftentimes described quite successfully by attractive Hubbard model, and this study has been performed, which is called the Bogolubov-Digens method, or some kind of an inhomogeneous mean field theory, which showed that in presence of disorder, which is the x-axis, superconducting correlations like the superfluid stiffness, there are two lines, red and green. Let's focus only on one. I mean, the red line, let's say that's the superfluid density that decreases monotonically as a function of disorder, eventually causing a transition at some critical disorder, which is somewhere here. Uh, and then also off diagonal long range order behaves in a similar manner as a function of disorder. However, the energy gap in the single particle spectrum remains pretty insensitive to disorder, as you see in this blue line. In fact, at a very high disorder, I mean, this energy gap persists even beyond the disorder where the superconductivity has collapsed, which is signaled by the vanishing of the superfluid stiffness. So this has been known for some time. In another thing which was sort of interesting from these old studies is that the growth of inhomogeneity as a function of disorder was also quite impressive, and that was related to much of the physics that was found here. For example, if you look at the pairing amplitude in space, so that will have some inhomogeneous random structure with more or less large pairing amplitude all over the system. This is on the system. Goes into something where you have at a very large disorder, you have only very limited, sparsely populated superconducting islands, which are like this large value, which is in color yellow. They're called superconducting islands, separated by this blue or black region, which are insulated. So that's kind of the evolution of inhomogeneity. So you go from something which was sort of amorphous to something which is granular structure in the space of this pairing amplitude, for example. And disorder, we have in mind something like a box disorder. It doesn't matter. I mean, any kind of disorder would essentially do the same thing. Instead, if we focus on the role of orbital magnetic field in a clean system, we know that this field penetrates a superconductor in a type 2 superconductor in the so-called mixed phase, and the magnetic field lines penetrate through regions which are called vortices, like this conical structure that you have here. So if you keep on increasing, and they form a periodic array of such vortices, which is called a vortex lattice. And then if you keep increasing the field, this vortex lattice actually, there is a suppression. The suppression will occur to the value of order parameter, which is far from the vortex center, because the vortex density increases with increasing magnetic field. So these vortices come close to each other, and the order parameter far from the vortex cannot come up to the BCS value. So it goes down, and with increasing field from here to here to here, I mean, it basically collapses. The vortex lattice collapses. So which is given by this dotted points. I mean, which is just to say that the average value of the order parameter goes to 0 somewhere. So all this has been done. I mean, in this case, we are going to study. I mean, which we are going to study is within the framework of an attractive Hubbard model, where we introduce the orbital magnetic fields in terms of some kind of a Peierls phase factor. And these are just the standard Landau gauge in which we are using the magnetic field and all that. So this is also well known. I mean, so this you can see as a function of temperature. So this is the melting of so-called melting of vortex lattice that I'm talking about, and zero temperature, which is this line. I mean, this is superconductor, and then the vortex lattice disappears in this. I mean, superconductivity disappears. And if you go over temperature, so this line goes like this, and so this region is a superconductor with abricos of vortex lattice structure. I mean, superconductor because ds is non-zero and energy gap is also non-zero, single particle energy gap. And beyond that, in zero disorder, this is the clean system, abricos of theory. So you have a metal. So that's the picture which is known. So what we are going to address in this talk is this plane. So we are in addition to that, now I am introducing another axis, which is disorder, and I'm going to get to the phase diagram. So here it is showing a bunch of things, which is all we are going to discuss. So what we'll see among various things that this is essentially the phase diagram. So superconductivity will be signaled. I mean, the two signature of superconductors, one is ds, which is the superfluid stiffness, and energy gap. They will behave, though they start behaving similarly for weak disorder in the Abrikosov region. They separate out from each other, where superfluid density dives down to zero, whereas energy gap persists, and that will change the nature of vortices in the system at strong disorder from what is known as I mean, here it was known as Abrikosov vortex. I mean, we have talked about it, to something which is a Josephson vortex. And then the physics seem to be quite different. And that's the thing we are going to address. Okay, so that's basically the outline. We'll talk about how to get to this phase diagram. And then it turns out that our understanding of this phase diagram will actually also solves two very important experimental puzzle. One is to do with magnetoresistance peak. Another is local density of states at the vortex core, both of which are there are some interesting observations, and our development of the theory for disordered vortex lattice can actually address both of them. So we'll talk about that. So first, to the phase diagram, these are very standard calculation that we have done using this inhomogeneous main field theory in the presence of vortices. So it is evaluation of, again, we are going to focus our discussion to superfluid density, behavior of superfluid density, as well as the energy gap. So here, this red curve is the superfluid density. So here, this is the picture I showed. This is at zero magnetic field, when there is no magnetic field. So this is the old result. What we are going to show here is, as a function of magnetic field at specific values of disorder, how do these two quantities behave? So for example, when the disorder is weak, and there is a particular reason for calling that weak, I'll explain it to the next slide. So both of them decreases, both meaning the superfluid stiffness, the red line, as well as the blue, which is the energy gap, and both disappears roughly at the same point, and pretty similar to what you expect for zero disorder, clean system like Abrikosov theory, within Abrikosov theory. Now, as you increase disorder, it seems the behavior changes quite dramatically. So superfluid density still decreases and goes to zero, whereas the energy gap decreases, but remains at a healthy value. So in particular, the two scale changes from one to other, and both of them are presented in the energy unit that I should have mentioned, but that's certainly true. And also the magnetic field is expressed in the unit of flux. Number of flux quantum through the system in the unit of flux quantum, superconducting flux quantum, the field such that a certain number of superconducting flux quantum are present in the system. And then at very high disorder, where the superconductivity is very fragile, to begin with, the superfluid density is very small, they quickly disappear. On the other hand, energy gap essentially does not decrease at all. So that's what we get. And here, what we show is the energy gap, and the energy gap. In disorder and in the presence of disorder and magnetic field, one has to define it in a particular manner. So, for example, this is the standard S-wave energy gap, hard energy gap that we all know. But in presence of magnetic field, you will often have this kind of a suppression, and then if you have to define the energy gap, you have to. This is somewhat. You have to define it a particular way, and we defined it the way experimentalists do. So that is, we basically lift the baseline x-axis from here to somewhere, such that at an energy greater than twice of, or actually thrice of energy gap of the superconductor, not thrice, I think it is about 2.5 times the energy gap value, it matches with the actual profile of the density of state. So where it matches, so we take this line such that it matches there, and then we see what is the energy gap, which is defined by this cut. So for the clean system with hard gap, this is obviously the result that we know. But for this particular case, when it is like a V, we can still define an energy gap. So that is required for all these cases. So following that procedure, you extract the energy gap from the average density of state, and superfluid density we calculate using Kubo formula. This is the evaluation of Kubo formula. Okay, so now once we have done that, so this is the phase diagram that I was showing the schematic picture of to begin with. So this is the actually calculated phase diagram. So at low disorder, which is in the plane of V versus H magnetic field here, and so at low disorder, I mean DS and EG, they follow each other, the blue line and the red line. However, at strong disorder, this is the DS which actually goes to zero, which it should, because I mean, this is, I mean, for example, this is the critical disorder strength where superconductor to insulated transition occurs in absence of magnetic field, whereas the energy gap keeps increasing sort of forever. So this divides the whole phases into three distinct regions. One is the superconductor. This is a paired insulator in the sense that it has a finite gap and there is no superconductivity. And this is quote unquote metal. I mean, I don't mind if you want to call that an Anderson insulator, but at low disorder, at least it is. Yeah, I don't argue on that point. I mean, this metal could be an Anderson insulator with a very large localization length. That's fine by me. It's, after all, you have to keep in mind that this is weak disorder, and this is the Abrikosov theory line. I mean, so okay. Uh, so in addition to that, the spatial structure shows something very interesting. So for example, this is the weak. Okay, so sorry, I go back just to say that now I will present all result in three representative disorder strength. One is weak, which is this vertical line, dotted line. So where both of these two DS and EG behave in the same manner, weak disorder. This is the intermediate disorder, which is roughly where the peak of this superfluid density is. That's not so important. I mean, basically, intermediate is intermediate. Instead, what I can define better is a strong disorder, which is just, I mean, this probably doesn't show, I mean, it doesn't come at the right place. It is just below the VC for the superconductor without magnetic field as a function of disorder. So it's just about to go non-superconducting. So it's very strong disorder. So strong, weak, and then intermediate somewhere in the middle. So at those three representative places, what I show here we are increasing magnetic field. So like here we have two vortices, in the sense that two flux quantum, and you can see see the location of these two vortices. So there is a disorder, weak disorder, and then this is not a periodic structure at all. And please remember that what I'm showing is just one unit cell. So actual system has many unit cell with many more number of flux quantum, which are not periodic. I mean, in this case, somewhat irregular array of vortices, what you will find for disorder. But then as you increase the number of this flux quanta here, 6, so this actually wipes out this pairing amplitude, which was red, and this creates the blue region, which is where the pairing amplitude is nearly 0. And then at very large value, it is essentially wiping out superconductivity everywhere. So that's roughly consistent with the Abrikosov picture. Instead, what if we go to a very large disorder case here? What we see that there is hardly any change of the pairing amplitude profile as a function of magnetic field. The reason is simple, because this is a large disorder. To begin with, you have a situation where there are large small superconducting islands separated by large non-superconducting insulating places. So your magnetic field will actually penetrate, will go through this non-superconducting region just for the energetics, right? So as a result, what you end up with is something what is called a Josephson vortex. I mean, here it was like a Abrikosov vortex, but here it is Josephson vortex, where pairing amplitude is large in region here. However, at the center of these field lines go through the region where there is no pairing. So that's the picture of a Josephson vortex. And as you increase the magnetic field, it just finds more and more blue region for penetrating the flux lines, and hence there is hardly any change in the profile of the pairing amplitude. So that's the extreme limit. And intermediate disorder will have something intermediate. So that's something what one understand. So Rajdeep, how much time do I have?
Yeah, so you are at 9:42. The whole thing should end by 9:50. So let's
About 8 minutes.
for.
Okay.
No, we would like to keep maybe 2 minutes.
Oh, okay, sure.
So
Okay,
maybe
so that's fine. Okay,
five,
thank
six
you.
minutes. Yeah.
Okay. So now let us go to so now we are going to address what kind of connection to experiment we can do with respect, I mean, with our phase diagram, which was shown here, and given the physics that we are describing here for this changeover from a Abrikosov to a Josephson vortices. So the one intriguing question was to address magnetoresistance. What has been found in a bunch of experiments, I will not describe all of them. I mean, these are from various different experiments where one was studying, and this is about 10 years old by now, one was studying the superconductor to insulator transition as a function of magnetic field. So there is a smaller value of field here. So BC is the superconductor insulated transition. So beyond superconductor insulated transition, so what one finds that in a system, in a thin film, which is strongly disordered. So this is very important. I'll quantify that somewhat more. If you look at the trace of the resistivity, so that shows a very, very strong magnetoresistance peak. It goes up by several orders of magnitude, typically of the order of typically 8 to 10 orders of magnitude, and then it comes down, making it a very strong peak at a field which is much larger than BC. So that was shown in various cases. So it started with Sambandmurthy et al. In the group of Dan Sahar, and then it was done by many people, Baturina, and this is also from Sahar's group. And then this is Kapitulnik and collaborators have made important contributions there. It has also been found that kind of magnetoresistance P, though weaker here, was also found for underdoped cube-thread superconductors, and there are many other people who have found this thing. I mean, with varying degree of sharpness, but in what was found that if the disorder is very strong, the peak gets very sharp. And also, this peak is a bit asymmetric in the sense that it rises very sharply, whereas falls relatively smoother or relatively gradual fall. That you can see from here also. So those are the two features I am going to focus on. So now, from those experiments, I'll pick up these two cases. One is that the peak is sharp and asymmetric like this. So this is my cartoon picture for the I mean, as you lower the temperature, the peak gets sharper and asymmetric. Whereas also as a function of disorder, the peak, I mean, higher the disorder, peak gets stronger. So we are going to address these two particular issues here. And the method is again very simple. We'll calculate the dynamical conductivity or frequency dependent conductivity. And let's first focus on relatively stronger disorder, V equals 1.25, which we call moderate disorder. In the experimental case, that will be a large disorder. I mean,
So,
the
Amit,
films that
2 minutes.
show superconductor. Yeah.
2 minutes.
Okay.
Yeah.
So now from there you can calculate the frequency dependent conductivity for various different field values. These are different traces of field. I mean, these are the actual data, and from there you can try to, I mean, not try to, you can also get the sigma at omega going to zero. That is the Drude conductivity. Let me go straight to that. So this is the result for V equals 1.25. So what one finds that this is how the superfluid density goes to zero. And if you are calculating sigma omega, that actually disappears here. So the metal stops here, quote unquote metal, I mean, stops here, leaving out this paired insulator region. So this is nothing but, so it is like going along this line. You go from here to this paired insulator and then you go to a metal. So it's exactly that picture that we are getting. And then if you convert this to a conductivity to resistivity, so it will look like that. So resistivity will be zero for all the field values where there is a superfluid density. And then it sharply goes up to infinity because it's an insulator here. So it is insulator, and then it will drop like that. I mean, this is the fall of resistivity at very large value of field. So that has a structure reminiscent of this. I mean, it goes up sharp and then falls off slowly. And this is the magnetoresistance peak. So I could also argue, which I don't have time for, is that the magnetoresistance peak will appear much weaker for weaker disorder. But let me leave that out. And also tell you just in 1 minute what the interesting physics of this with the density of state at the vortex core. So it's well known by the work of Caroline Higgins and Matricon that S-wave vortices at the vortex core has a very strong peak structure, which is like an Andreev reflection peak. So that is a signature of a vortex lattice for a clean vortex lattice, and that has been shown. So what we find that in presence of disorder, this I mean particularly for largest disorder, I mean if you
So,
look at the vortex core density of state, that has a gap instead of a peak. I mean so there is no peak. I mean this is the vortex
Amit,
core.
if you
Yeah,
can end, it would
yeah, yeah,
like in
yeah.
maybe
I'm just done.
10
So, so
seconds.
that
Yeah.
one can also understand it in certain way, but that is little involved argument, and I'm not going into that. And it just turns out that that actually finds support from experiment. There have been several experiments which did not find. I mean, including the experiment from Pratap Raichudri's group and also Roddy Chave and Sesepe, that they didn't find the Carolingians metric on peak when the vortex lattice is very irregular. So that is our explanation that because of disorder there is irregularity. There are more experiments here. So and then so I'll just leave the conclusion and I'll be happy to take questions.
Okay.
Sorry about this
No,
figure.
thanks, Amit. Questions, and please raise your hand, and we can take one or two questions. If you have a question, please raise your hand. I don't see a question, so maybe I can ask. So, Amit, about your sigma DC.
Yeah.
So, how large a size were you working? Because you have to extrapolate the 0 omega piece to get the sigma DC, right?
Yeah, so that's not actually difficult. I mean, so the size was for one unit cell, it is 36 cross 72. I mean, or 36 cross 36, you can say, for single vortex. Yeah, so that's not bad. And in particular, what happens is that actually it is little more difficult. So let me try to go back to the that slide. So here. So you can see that this is roughly where our data ends, and then this is an extrapolation. But by the time your data ends, it is such a fantastic flat. I mean, this is very easy to fit. It's not very difficult. I mean, you can't go too wrong if you have to extrapolate this.
Okay.
So the reason is that you are developing some kind of a so you're developing some low energy states which helps to do that extrapolation. This is actually a little more difficult for weaker disorder, because things happen very quickly. And so you can't change the magnetic field continuously if you're working with a finite, I mean fixed system size, because you can change flux only by discrete.
Yeah.
So this, but for large disorder, which is the area of interest, large or intermediate disorder, where the interesting thing is, I mean, for that matter, it also, I mean, which I didn't have time to, I mean, you have very interesting evolution for weak disorder versus strong disorder. In strong disorder, you see this slowly fills up the gap, whereas it seems like for weaker disorder, it bodily moves. So it is a good possibility that you can have a direct superconductor to metal transition in that way. I mean, there is a gap, and then suddenly, I mean, without any intervening insulator.
Okay, Amit, thank you. So we'll move on to the next talk. So Amit, if you can stop sharing your screen.
Yeah, I will. Yeah.
And
I think it is now off, right?
Yeah. So Aarti, can you try to share your screen? Our next speaker would be Professor Aarti Garg from Saha Institute of Nuclear Physics. And she'll tell us about many-body localization and enhanced non-ergodic subdiffusive regime in the presence of random long-range interactions.
Thanks, Rasti. Can you see my screen now?
Yeah, can you put it on full screen? We can see your screen.
Is it okay now?
Yeah, okay. Over to you, Aarti. Yeah.
Thank you. So thanks, Rasti. And I would also like to thank all the organizers of the Young Investigator Meet to invite me and give me a chance to speak here. So we already heard a lot about the competing effects of disorder and interaction in the previous talk by Amit Ghoshal. And my talk is also about the effect of disorder and interactions, but in a very different context. So I'm going to talk about many-body localization and more interestingly about this non-ergodic subdiffusive phase, which has been a topic of recent discussions. And I will tell you how the presence of random long-range interactions helps in getting a broad non-ergodic subdiffusive phase in this MBL system. So the work is already on arXiv. So let's think about a very simple situation where you have a single quantum particle moving around in a disordered medium. And excuse me. And the toy model for that is this Anderson model, where you have a tight binding hopping term and random on-site energy. So in the absence of random on-site energy, we know that the system is an ideal conductor. And in the absence of hopping, there is no communication between different sites. So the system is insulator. So as you tune the ratio of T to the disorder strength, you expect the system to show a metal to insulator transition. So for weak disorder, it should have extended states, and for strong disorder, the system is supposed to is known to have an insulating phase with localized states. But dimensionality plays a crucial role here. And we know that in 1D and 2D, all the states are localized, but in 3 dimension, the metal to insulator transition takes place through the formation of something called mobility edges. So when you turn on disorder, it's not that all the single particle states get localized in one go. The states on the edges of the spectrum are localized, but states in the middle of the spectrum remain extended. And as you increase the strength of disorder, almost all the states get localized. And that's when you have a full insulator. Now, something interesting happens near the mobility edges, the single particle mobility edges. So the states in this red localized region look something like this, and the states in the extended regime look something like this. But then near the mobility edges, you have critical states, which are extended but not fully extended. They are still non-ergodic. Okay, now let's see what happens to this system when you turn on localization, when you turn on interaction. So again, we have the same Anderson model in the presence of some nearest neighbor repulsion between these pinless fermions. And we know that if the interactions are weak and short range, then the localization survives and all the many-body eigenstates remain localized. But as you increase the strength of interaction, slowly a part of the many-body eigenstates in the middle of the spectrum gets delocalized and ergodic. And if the interaction strength is strong enough compared to the disorder strength, then the entire spectrum can become ergodic and extended. So this is the most popular phase diagram of many-body localized system that people are aware of. But there is also another possibility where the system does not undergo a transition from ergodic extended phase to the many-body localized phase directly, but there can be an intermediate non-ergodic extended phase, which can be obtained by tuning certain parameter in the Hamiltonian, for example, disorder strength or the interaction strength here. So there was a proposal for this non-ergodic extended phase long back by Altshuler and others, and they call it as a bad metal phase. But the problem was in this kind of system, which I have shown you here, with the short range interactions, and where in the absence of interaction, all the single particle states are localized, the non-ergodic extended phase, which was seen in some of the numerical studies, was very narrow. And it is hard to really come to a conclusion whether such a narrow phase will survive in the thermodynamic limit or is it just a numerical artifact. But then there are other couple of studies where broad non-ergodic extended phases were seen. For example, in a numerical study on disordered Josephson junction arrays, where it was shown that between a metal at low temperature and an insulator at high temperature, there exists what they call something called a bad metal phase, which is basically a non-ergodic phase, but the wave functions are still extended, okay, and the transport is subdiffusive. Then there are a couple of other studies, for example, the quantum random energy model, which has also shown indications of a non-ergodic extended phase. And now going back to the model of spinless fermions in the presence of disorder, if you think if you start with a disorder model where the non-interacting system has single particle mobility edges separating the localized and the extended states, then there was a proposal that there is a possibility of a non-ergodic extended phase which should survive even in the thermodynamic limit. And the logic is basically that if you have both localized and extended states in the non-interacting system, and then you prepare a many-body eigenstate from this from the Slater determinant of this localized and extended states, you are most likely you will get something which is non-ergodic but still extended. And if you turn on the interactions which are weak enough, then such a non-ergodic extended state should survive for a range of interactions. And so in this work by Shankar Das Sharma and his group, they showed that in this non-ergodic extended phase, the system violates ETH, it's not thermal, but the entanglement entropy still shows a volume law. And then a transport study was done by Subrata Mukherjee and his group, and they showed a subdiffusive transport in this region. So what I'm going to, okay, so there is one more very recent paper which I found where they have looked at the effect of spin-orbit coupling in a one-dimensional spin-full fermionic system in the presence of Hubbard interaction. And the disorder is coming from this Zeeman term, which is basically an Aubrey-Henry potential. And what they found is that in the absence of interactions, the system has a broad regime of critical states where the eigenfunctions are non-ergodic but extended. And the claim is that even if you turn on the interactions weakly, a part of this critical regime remains many-body critical. So they claim to see non-ergodic extended phase in this disordered interacting system. So what I'm going to talk about is how one can realize a broad non-ergodic subdiffusive regime in the presence of random long-range interactions. Okay, so this is the model of spinless fermions in the presence of some source of random on-site energies. And so this is the phase diagram I will show that for very weak disorder, you have an ergodic phase. For very strong disorder, you have this many-body localized phase. And in between, you have the non-ergodic phase, the width of which can be tuned by tuning the strength by the range of interactions in this term. And here the eigenvalue statistics obey Wigner-Dyson statistics, and here the system has Poissonian statistics. And in between, you have Poissonian statistics for level spacing ratio, and the inverse participation ratio goes as 1 by n to the power mu, where n is the dimension of the Fock space with mu less than 1. Okay, so the states are not fully ergodic; they are non-ergodic but still extended. And from the mean square displacement and the imbalance study, we see that the transport is subdiffusive in the sense that this exponent gamma is less than half in this entire region. Okay, so that's basically the outline of the talk, like how do we get this phase diagram and how can we understand it. So now since I'm going to talk about long-range interactions, let me give some background of what already has been done on MBL systems in the presence of long-range interactions. So there was a common belief in the community that MPL can survive only in the presence of short-range interacting systems. And that was mainly because that most of the numerical works were first of all on one-dimensional short-range systems, and then there's a theoretically MBL has been established for systems with short-range interactions on one-dimensional chains. And the belief that it cannot survive in systems with long-range interactions was basically to somehow linked with what Anderson showed in his old paper, that if you have long-range hopping, a power law hopping with the power exponent alpha less than or equal to dimension of the system, the locator expansion breaks down and the single particle localization does not exist. And so people did generalization of this resonance count argument, which was given by Anderson for the interacting systems. And what they found is that if you have a power law Heisenberg model, where the couplings GIJs are random, then MPL can survive only if alpha is more than 2D. It means in one-dimensional system, one can expect to see a many-body localized phase only if alpha is greater than 2. So this critical alpha was obtained from the resonance count argument, and also there are numerics which support this argument. For the power law interactions in the XY model, again with the couplings Gij to be random, the critical exponent was found to be 3 by 2 for a one-dimensional system. And for the XXZ model, where the exponent for the spin flip term is alpha, and the exponent for the spin preserving term is beta, for the so MPL was predicted only when the range of the spin preserving term is longer than the range of the spin flip term, and only for beta greater than 2D, one can expect to see a many-body localized phase. But most of these predictions of the critical exponent are based on resonance count argument, which only focus on a subsystem of very few particles, and actually they are basically heuristic arguments. So this XXZ model was actually revisited by David Logan and Shadi Roy recently, and using a self-consistent mean field theory of the local propagator in Fock space. And what they found is that as long as the spin flip term is short range and only the spin preserving term is long range, the system is always localized. But if you have the spin flip term, which is short range, say alpha less than half, then the system is always delocalized. And in between, there is an insulator to metal transition, and one can expect to get an MPL phase for finite values of disorder, even for beta less than 2, which is opposite to what was proposed by the resonance count arguments. So we looked at the effect of long-range interaction earlier in this work last year on in the presence of power law hopping and power law interactions, but keeping the coefficients of hopping and the interaction to be uniform. Okay, and what we find is that if you have power law hopping but nearest neighbor interaction, then the system gets delocalized for the exponent alpha to be less than or equal to 1.5. But if you have long-range interaction, then the system remains localized even for alpha less than 1. Provided you start with a large enough strength of disorder at which the system in the presence of nearest neighbor interaction and nearest neighbor hopping showed infinite MPL phase. So the studies, so the last two studies which I showed you by David Logan and us, that is actually consistent with what has been found in some of the experiments on MPL in the presence of long-range interactions. So for example, in this Nature paper, which were trapped ions were studied, and a long-range Ising model with power law interactions was simulated. And this alpha can be tuned experimentally between 0 to 3. So this phase diagram has been obtained for alpha equal to 1.5, and they do claim to see a many-body localized phase. And there is another work published in this Nature Physics, where again trapped ions were used to simulate long-range transverse phase Ising model with the exponent alpha between 0.95 to 1.8, and many-body localization was observed. So that gives us the confidence that many-body localization does survive in the presence of long-range interactions. And now in this talk, I'm going to tell you the effect of long-range interactions, but the coefficients Bij's are taken from a random uniform distribution. Okay, so for this model, please keep in mind that the resonance count argument predicted that many body localized phase can be obtained only if alpha is greater than 2. So now coming to the details of the disorder potential we have used. So we use a deterministic aperiodic potential where for n between 0 to 1, the system has single particle mobility H's provided H is less than 2T, and for H greater than 2T, all the single particle states are localized. So in this work, we choose to work with n equal to 0.5, where we have the option of working either with the system with single particle mobility edges, or in the situation where all the single particle states are localized. So this model, in the absence of this local on-site term, that is for h equal to 0 and alpha going to infinity limit, was studied recently by Shankar Das Sharma and his group. And what they found is if randomness is only coming from the interactions, then random interactions themselves can cause many-body localized phase. Okay, so and on the contrast, this resonance counter argument shows that if you have random power law interactions, long range interactions, then the system gets delocalized. So this is the two arguments are completely basically sounds opposite to each other, and that's what we will try to understand in this talk. So to understand the effect of random long-range interactions, let's first map the model which I showed you here, to the effective Anderson model. Rasif, how much time do I have?
So you started at about 9:52. So I guess you have maybe 6 minutes.
Okay, fine, thank you.
5 minutes.
So in order to understand the effect of this random long-range interaction, we first map the model we started with to this effective Anderson model. Now, the effect of local on-site energies and the interaction among all the particles has gone inside this local energy. Okay, so we look at the correlation among this local energy, which is defined here. And what we see is that as we change the range of these random power law interactions, the correlation among the local energies change significantly. So as you increase the range of interaction, the intermediate values of correlation become more probable, although the larger values of correlation become less probable. And following this work of David Logan and Shirupta Mukherjee, we also looked at the correlation as a function of the Hamming distance between these pair of configurations in the Fock space. And what we see is that the correlation actually behaves as 1 minus x by L to the power b, where x is the Hamming distance. And this exponent b increases as the range of interaction increases. Okay, so this is the study where the disorder strength is fixed to be 1, and the interactions are also lying in this range. Okay, so now let's see what happens when you keep the disorder strength interaction strength fixed and increase the strength of disorder. Okay, so this is the plot for alpha equal to 0.5, and what you can see is as we increase the disorder strength from 1 to 10, the correlation basically goes back to what it was for the non-interacting system. So we know that in the absence of interaction, this system shows localization. And now from here, you see what is the strength of disorder required in the presence of these random power law interactions to go back to the same correlation which you see in the absence of interactions. Okay, so this black curve corresponds to the correlation in the absence of interaction. And here we keep increasing the strength of disorder, and you see by the time you go to disorder strength equal to 10, the curve looks exactly same as what you had in the absence of interactions. But if you are sitting for at a shorter range of random power law interactions, then this happens at a much weaker strength of disorder. Okay, and as we will see in further slides, that this basically gives you an estimate of the disorder strength required to undergo ergodic to non-ergodic transition. So as long as the system has this modified correlation among local energies, because of the presence of random power law interactions, the system does not show non-ergodic behavior. Only when you increase the strength of disorder sufficiently large such that the correlation effect of the interaction is nullified, then one starts seeing the non-ergodic behavior. So here is the plot of the critical disorder at which the transition from ergodic to non-ergodic takes place. Okay, so this is based on the level spacing ratio. So below this curve, you see that the system has states in the middle of the spectrum are always obeying Wigner-Dyson statistics, and above this curve, the entire spectrum shows Poissonian statistics for level spacing ratio. And here I have shown the details. So for example, if you look at the case of alpha equal to 1.5, the h equal to 6, all the states are localized. But if you look at h equal to 6 for a longer range case, then it already has the mobility edges. And then if you go to weaker disorder, then of course the system with longer range interaction has broader range of extended states compared to the system with shorter range interactions. So here I have shown the mobility edge obtained on the basis of level spacing statistics only, that for a short range interacting system, you have a shorter range of extended states, but as you increase the range of interaction, the fraction of delocalized states increases, and one needs larger and larger disorder strength to localize the entire, I mean, not actually still localize the entire spectrum, but to see the Poissonian statistics for the level spacing, a stronger disorder is required as the range of interaction increases. And so this is, yes.
Aarti, 1 minute, okay? Yeah,
Yeah.
go ahead.
Oh, 1 minute is left,
Yeah.
okay.
Yeah.
Okay, so let's look at the eigenfunction statistics. So as you can see that for the very strong, very weak disorder, the states are extended and this exponent actually reaches 1 in the thermodynamic limit. And for very strong disorder, the states are localized where this exponent is almost 0. But then you have this intermediate regime of disorder where the mu neither reaches 1 in the as the volume of the Fock space increases, and nor it is tending to 0. So these are the non-ergodic extended states or the multifractal states which we see for intermediate strength of disorder in the presence of interactions. And then we looked at the density imbalance starting from a charge density wave initial state, which in the intermediate time regime decays with the power law. And this exponent has been shown to be related to the exponent of the mean square displacement like this, such that gamma equal to half means that you have a diffusive system. Okay, so here I have shown the log scale plot of the imbalance, and what you see is that there is a change in the slope of the imbalance as a function of time, such that the gamma extracted from the short time fit and the long time fit is different, and the long time fit actually gives you the larger values of gamma. And here is the plot of the exponent gamma, which basically tells you that if you have very weak disorder, the system has super diffusive transport, which is related to the fact that we are studying a deterministic quasi-aperiodic potential. And but the interesting thing is, as the range of this random power law interaction increases, the width of the super diffusive phase also increases. And then the system enters into the sub-diffusive phase, where gamma remains less than half. And as you increase the strength of disorder further, the system is non-ergodic and the gamma is still less than half for a broad range of disorder strength. And only when increasing the disorder further, the system becomes diffusionless and localized. So this is the main interesting part, I think, of our work, where we see this non-ergodic sub-diffusive phase, where I showed you that the eigenstates are multifractal, they are partially extended, and the system has very slow dynamics. And this, we think, can be explained in terms of some very non-local Lefschetz effect. Yes, so that's the conclusion, and I'm at the end of my talk. Thank you.
Thank you. Thank you very much. So questions for Aarti. Uh, please raise your hand if you have a question.
Hi, Rajdeep, Anamitra here.
Yeah.
As a host, I am unfortunately not able to raise my hand. Can I quickly ask a question?
Yeah. Go ahead. Go ahead and
Sorry
ask.
about that. I'll try to fix it.
No
Hi, Ati.
problem. Go ahead.
Yeah.
Nice talk. Just one sort of curiosity. So, in interacting frustrated systems,
Yeah.
we know bad metals can sort of violate the iopherigal limit. So, finite temperature, this going, the reactivity keeps on growing. So,
Yeah.
in kind of situations, the interacting disordered problem in your study, did you encounter, or is there understanding in the community that there is a violation of such this thing?
So actually, I think we are still not at that level because this analysis is completely for an isolated quantum system. Okay, and so basically, I'm still trying to make. I mean, Altshuler, I think, is the only person who called it bad metal, but I'm not sure whether I should even call it a bad metal because the
So,
transport
it's a
is
particular thing. Yeah, sure. I understand. Okay.
okay.
Okay, sure.
So
Thank
the
you.
only thing we see is that it is subdiffusive and the eigenstates are critical. They are non-ergodic but still extended.
I see. Okay. Sure. Thanks.
Any other questions? I do not see any other questions. So then let us thank Aarti for a very nice talk.
Thank you.
And we will move on to the next speaker, which is Professor Siddhartha Lal. So Siddhartha, can you try and share your screen?
Sure. Am I audible, Rajdeep?
Yeah, you are. So
Okay, great.
this will
okay.
be Professor Siddhartha Lal from ISAT Kolkata, and he'll tell us about insights on the origin and nature of superconductivity in the hole-doped 2D Hubbard model. So, yeah.
So, Rajdeep, before I begin, can I ask your permission to keep my video off? I'm just sharing my bandwidth with my daughter who's doing online classes right now, on from home.
That's not a problem.
So I just share my screen and
yeah. Sure. No issues.
I guess, is it best to do it with the entire desktop that way or just the PowerPoint?
I think it's easier to do it with just the PowerPoint.
Just the PowerPoint? Okay,
Yeah.
let's see how this goes. Okay. Can you see this?
And now you can go to the, we can see this. Can you go to the full screen mode?
Yeah. Is this visible?
Yeah, this is visible. Looking nice. So go ahead, over to you,
Okay.
Siddhartha.
Yeah. Thank you, Rajdeep, and the organizers. Thank you so much for organizing this meeting, and I wish it well. We've had a strange year, and I hope this will bring some cheer to all of us to get together and share our physics. I'll be talking about some work that my students and I have been doing for the last few years. Some of it is published and some more is under review. The student who did this work is Anirban Mukherjee, who submitted his thesis recently and is currently on his postdoc. The work deals with the trying to understand some physics of the hole-doped 2D Hubbard model, and I'll tell you that as we go along. Let me first introduce the physics of the model itself. It's very simple to understand, and it's the paradigmatic model for understanding metal insulator transitions driven purely by electronic correlations. The Hamiltonian has only a hopping term and a on-site repulsion term at half filling, and you have a chemical potential term away from half filling. What we expect in this model is that if we are sitting at half filling and the on-site repulsion dominates over the kinetic energy in a big way, then we expect that double occupancy will be strongly forbidden and we'll enter some kind of a jammed insulating state. On the other hand, we expect that when the reverse is true, we should get some kind of a metallic state showing conduction, which tells us that there should be a metal insulator transition at some critical U by T. And the ground state for U being greater than that critical value should be a charge insulator with Néel antiferromagnetic spin order. Okay. However, it's also believed that a Mott transition can also be obtained by doping carriers or basically moving away from half filling. And a large section of the community believes that studying the 2D Hubbard model, hole-doped 2D Hubbard model, could give us some insight into the nature of this famous phase diagram for the high temperature superconducting cuprates, though there's no theoretical consensus here, one must add. However, several numerical simulations of various kinds done by various well-known people suggest that there are strong reasons to believe, let me put it that way, that there are superconducting pairing correlations upon hole doping the 2D Hubbard model. Okay, there are even some indications that there might even be a quantum critical point, some exotic quantum critical point hiding under this superconducting dome. So that's the reason. That's another reason for studying the 2D Hubbard model. Some open questions. Well, why so much complexity upon tuning away from half filling? And is this universal in the sense that can the Hubbard model on the 2D square lattice help us understand some of this physics? Also the criticality. Is there a quantum critical point, for instance, hiding within the superconducting dome? Those are some of the questions we'd like to look at. Now, to get on to the 2D Hubbard model on the square lattice, one very important thing that I'd like to bring to your attention is this business of electronic differentiation. So if we look at the kinetic energy piece, that's just the tight binding Hamiltonian with a well-known dispersion, which we often teach in our courses. Well, this dispersion actually hides something very interesting. It's certainly well known that at half filling, the Fermi surface is this square with nested Fermi surfaces and Van Hoff singularities, and there's been a lot of work that focuses on them. However, one other fact that many of us often do not appreciate is that if you look at the electronic dispersion normal to the Fermi surface, okay, the Fermi surface at half filling, then it's actually different everywhere along this Fermi surface. So exactly at what are called the nodal points, that's pi by 2 here, roughly. If you look at the electronic dispersion normal to the Fermi surface here, it's massless Dirac line. On the other hand, if you go away from here and towards the Van Hoff singularity, it gradually changes until it becomes hyperbolic at the antinodes, which are here, okay, pi 0, 0, pi. And this wide disparity in the kinetic energy leads to the fact that all the electronic excitations are very, very different in nature. And when put together with the fact that the Hubbard term, if you were to convert this into momentum space, turns out that this is democratic and it's all-to-all in nature. It's infinite range. Everyone talks to everyone with the same strength. All of this is beginning to tell you that this must be some really, crazy problem to work with. Okay, so the way we decided to study it was to use the renormalization group algorithm, and I'll describe that very briefly. What this typically needs us to do is to integrate out the effects of two-particle scattering, because that's what the Hubbard term will want to do, away from the neighborhood of the Fermi surface, that is these blue rectangles, to regions that are far away in momentum and energy from the Fermi surface, that is these red zones, and back, okay? And we can have a forward scattering, tangential scattering, or backward scattering, okay? These are the three kinds of scattering processes. And we want to be able to do this and integrate out all degrees of freedom very far away from the Fermi surface until we have the physics only in these blue zones near the Fermi surface, okay? If you remember, this is essentially the essence of Anderson's approach to the Kondo problem, the so-called poor man scaling approach, where we do pretty much the same thing. Now, the way we did it here was slightly different from Anderson's method. What we did was we actually came up with a unitary way of doing this, which means that what we did was imagine that we have some degrees of freedom, electronic Fock states, okay, single particle Fock states, lying within this red block here. And we are looking at all scattering processes that, let's say, connect this states within this blue zone to the red one. Okay. What we want to do is that we want to come up with a unitary operator that decouples all the electronic states, Fock states, lying within this red zone. Okay. So if we could do that, then essentially the eigenvalues of the number operator lying there, the decoupled guys, would become integrals of motion. Okay. And such a unitary operator applied to the Hamiltonian would lead to a renormalized Hamiltonian. Okay. So if we could reiterate this several times and we keep decoupling states far away from the Brillouin zone, far away from the Fermi surface and closer to the Brillouin zone edge, then hopefully we would end up with a low energy theory that would be simple to understand. That's the hope. Now, in practice, the way it works out is that once we figured out how to carry out these unitary transformations, we can, from such a procedure, extract one particle, two particle, etc., vertex flow equations. Okay, this is a zero temperature process. Let me tell you right in the beginning. And certainly, we are able to obtain effective Hamiltonians in which the renormalized couplings begin to appear. Okay, and these effective Hamiltonians describe the stable fixed points of this RG procedure. It turns out that for the Hubbard problem, for instance, the one we've studied, we can even obtain the ground state wave function for the effective Hamiltonians that we obtain. And then we can compute various one particle and two particle properties, for instance, self energies and various correlation functions, even some entanglement quantities from this effective Hamiltonian and the wave function. Now, questions that we'd like to answer, for instance, would include, for instance, can hole doping the Mott insulator lead to a quantum critical point? There were some indications of this as far back as 2009 in a work by Vidyadhiraja and company using DCA or cluster extension, momentum space cluster extension of DMFT. We'd like to reinvestigate this. And we want to ask whether such a quantum critical point would lie hidden somewhere within the superconducting dome. And if we do find such a quantum critical point, then what would be the nature of the metallic state lying right above it? For instance, essentially this would be like asking the question, what is the nature of the parent metal from which this superconductivity would arise? And is the superconductivity related to the quantum critical point in some way? Essentially, what drives the physics at optimal doping? And how is it related to the critical quantum fluctuations at the quantum critical point? These are some of the questions that we would like to ask. The strategy, well, do the RG until you get to an effective Hamiltonian and a ground state wave function for a Mott insulating state, okay, the hole dope Mott insulating state. And then try and compute whatever you can to answer these questions. But first, let me tell you about some benchmarking that we did of quantities like the ground state energy per site using the effective Hamiltonian and the ground state wave function. Essentially, the idea is that once you have the effective Hamiltonian, the ground state wave function, carry out a Schrodinger equation computation of the ground state energy. These were some of the values that we obtained, okay, from the ground state energy per site from the RG at half filling, okay. And these are at various values of the bare Hubbard coupling in units of T. So we've taken everything from weak coupling all the way to strong coupling, 2, 4, 6, 8, 10, 12. Okay, these are the values that we obtained. And in this box, this column, we actually have the values taken from the literature. Okay, so the ranges here are taken from an extensive work that was carried out in 2015 by the Simons collaboration, where they actually used something like 12 or 13 different numerical methods to benchmark the Hubbard model, both at half filling, that is hole fraction 0, as well as 1/8 or 12.5% hole doping. Okay, so these two columns are their results, and the ones at U by T equal to 10 were taken from a exact diagonalization study by D'Agotto et al. Way back in '92. If you look at some of these numbers, you begin to see that our values are reasonably close to these ranges. Sometimes they lie within them, and sometimes they're just a little off. Okay, our values are taken. These are thermodynamic limit extrapolations that we have received from our RG method, and these are typical thermodynamic limit values that were obtained from several methods, numerical methods. Of course, this is not the case at U by T equal to 10 because they were working with ED of small cluster sizes. So the proximity of our numbers to the ranges and the values that they obtained suggests that the effective Hamiltonians and ground state wave functions obtained from the RG analysis can be trusted, even as we work with all the way from weak coupling all the way to strong coupling. Now here is a plot of the ground state energy per site as a function of the hole fraction at strong coupling, U by T equal to 8. Okay, and what we can see here is that as you hold up the system, the ground state energy per site actually drops and then has a kink-like discontinuity at around 25% hole doping, after which it starts to rise. Okay, such a kink-like discontinuity is seen whether you plot it as a function, whether you compute the ground state energy per site as a function of the hole fraction or the effective chemical potential. Okay, which is shown in the inset. And this is a typical hallmark of a zero temperature quantum critical point. Now, what is the physics in these, in these areas? Why do I call something a pseudo gap? Why do I call it a Mott liquid? Well, here's a picture that gives us some idea of what's happening. Let's look at the pseudo gap region. What I mean by pseudo gap is that if you look at a K-space map, as is shown here, okay, this is one quadrant of the Brillouin zone. Then what we see is that in the region near the nodal points, okay, in the pseudo gap region, you actually have a gapless region, whereas the antinodal regions are actually gapped out. Okay, they're insulating. So this is some coexisting state of matter with insulating and gapless regions in momentum space. The so-called Mott liquid is where the entire Fermi surface is gapped out. It completely becomes insulating. Okay. The quantum critical, exactly at the quantum critical point, that's where the nodal points become gapless for the first time. Okay. So imagine that in the entire Mott liquid, this entire Fermi surface was gapped out, but right at the QCP, for the first time, the nodal points become gapless. Okay. Whereas everything else is still gapped out. And it turns out it's gapped out and has preformed Cooper pairs sitting in the gapped regions. Now, if you continue to hold dope, at some point, this pseudo gap changes because these gapless regions stretch and slowly eat up the insulating antinodal regions until the Fermi surface, these arc-like regions, actually reconnect and become a completely connected Fermi surface. And that's where you begin to have something called a correlated Fermi liquid, where you begin to get some Landau quasi-particles. Interestingly enough, in the pseudo-gap region, where you have these nodal Fermi arcs, it turns out that there, the signatures of metallicity that we obtained were not of the Landau Fermi liquid kind, but rather the marginal Fermi liquid. So this is a phase diagram for what we found. So here, what we plotted, the x-axis is actually the effective chemical potential that tunes the hole doping. And since this is a zero temperature method, instead of having KBT, what we have on the y-axis is actually an energy scale for quantum fluctuations. So this is a way in which RRG actually partitions out various kinds of states of matter. What we find is that at very low quantum fluctuation energy scales, okay, so essentially at zero, right out here, that's where we would have had the Fermi surface of the tight binding, of the original tight binding Hamiltonian. So proximate to it, at very low quantum energy scales, we actually have a gapped insulating topologically ordered state of matter with twofold degenerate ground states, one of them having charge-like character driven by holons and doublons, and the other one by spinons. Now, when you carry out symmetry breaking, it turns out that at very low doping, this Mott liquid is replaced by the Néel antiferromagnet. Okay. On the other hand, if you look above at very high quantum fluctuation energy scales, the metallic state that you get is actually a marginal Fermi liquid. Okay, and it appears to have all the phenomenology that Verma and company had first proposed way back in the day. The pseudo gap is, as I described to you in the in the last slide. Now, what's equally interesting is that at this quantum critical point, right above it, if you look in terms of quantum fluctuation energy scales, you have a pseudo gap state of matter where the antinodal regions have preformed Cooper pairs in them, and the nodal regions, okay, are gapless. That's what I described earlier. Now, this quantum critical point is actually reached because of the rather strange fact that we actually encountered two reasons for pseudo gapping. One was the pseudo gapping of the charge degrees of freedom, that is the holon doublon degrees of freedom, and another one for the spin-on degrees of freedom. Now, the holon doublon degrees of freedom feel the changing effective chemical potential as a kind of electric field which separates out the holons and doublons, and that causes their physics to slowly decay until the quantum critical point is reached. And that's what we call the collapse of Mottness. Okay. The spin pseudo gap, however, is not really affected radically by as radically by the changing effective potential, the chemical potential. Instead, it's mostly flat and is only affected once we cross the quantum critical point and tangential scattering across the Fermi surface begins to kick in. At that point, the spin pseudo gap is also gradually killed and sort of dies off. And to the extreme hole dope point beyond the QCP, we actually have the reconnected Fermi surface taking place and a correlated Fermi liquid beginning to happen. Now, the quantum critical point itself is interesting. It has this D-wave type, physics. In K space, you only have 4 nodal gapless points and spin gapping everywhere else. So this D-wave-like nature is already telling us where we're headed with the possibility of superconductivity. Another interesting thing to keep in mind here is this dashed line that we see that is sort of surrounding this quantum critical point. This black dashed line is the region where we can see superconducting phase fluctuations. So this is what we find from the zero temperature RG method we developed. Now remember, this so far does not have the physics of any symmetry breaking. That's because RG transformations cannot break symmetries by themselves. However, what we did was we actually searched for symmetry breaking states, symmetry broken states of matter by explicitly including them in the RG formalism and checking when those order parameters become dominant or the fields that couple to them become relevant under RG. And this is what we found. The phase diagram changes such that at low hole doping, we actually have the Mott liquid being replaced by the Néel antiferromagnet, the spin density wave. This yellow region is actually the D-wave superconducting dome, and that completely clouds out the quantum critical point. It sort of screens it out. To the left of the quantum critical point, and at reasonably close to it, there is a pi CDW phase that we found. Okay, and slightly further away, extending further away, we've also found the existence of nematic fluctuations, which actually extend into these pseudo-gap regions. So as you begin to see, there is all kinds of things that are actually, all levels of complexity that appear to be there within this 2D Hubbard model when studied using this renormalization group formalism. And funnily enough, this phase diagram, this zero temperature phase diagram with a y-axis that sort of looks at energy scales for quantum fluctuations is in reasonable conformity with the temperature hole doping phase diagram obtained for the cuprates. This suggests that the physics that we see at zero temperature from this method seems to have some very close connection with the physics at finite temperature as well. Now, some more questions that we'd like to answer, and that'll be the last thing that I'd like to do in this talk, is how does the nature of the many particle entanglement change from that at half filling to that at the QCP? And how does this correlate with the kind of many body correlations that we would see at these two fillings? I mean, many body correlations, let's say the Néel type antiferromagnetism, spin density wave type correlations, or superconducting ODL arrow. And furthermore, how do things differ in the passage from symmetry preserved or these topologically ordered ground states to the symmetry broken ground states? So what we did was we took the ground states that we obtained, let's say at half filling or at the quantum critical point, okay, at the fixed points. And then we took the wave functions along, let's say, two directions in the Brillouin zone, let's say the normal direction and some point close to the antinodal point direction. And in those two directions, we unitarily evolve the RG transformations backwards, such that we get out a sequence of wave functions. Okay, and then from this sequence of wave functions, at every step of the reverse RG process, in some sense, we compute various kinds of quantities like many body correlations, spin density wave correlations, or superconducting ODL arrow. We also compute mutual information, which is an entanglement-based quantity, and I'll show you what we found. So the first thing that we will do is that we will look at
Siddharth, 2 minutes, okay?
Yeah. Okay, yeah. So the first thing that I'd like to tell you is what we observed at half filling. What we found was that at half filling, the topologically ordered ground states, the charge and the spin Mott liquids, have very high mutual information that which is telling us that they're very highly entangled, but their STW correlations are poor. On the other hand, the symmetry broken Néel antiferromagnet has very poor entanglement. It vanishes at the IR fixed point, whereas the STW correlations are naturally very high. Furthermore, we get the surprising insight that there are subdominant superconducting pairing happening even within the spin Mott liquid. Okay, while this thing, the ODLRO in that system is very poor. Now, at the quantum critical point, on the other hand, what we did was we asked ourselves what happens to the charge and spin degrees of freedom. And what we found is that the holon-doublon pairs, actually their mutual information or their entanglement gradually vanishes at the quantum critical point as you carry out the RG. However, for the spin type Mott liquid, in the antinodal direction, the preformed Cooper pairs are actually very highly entangled, whereas along the nodal directions, they are not. So this weak entanglement is an outcome of the fact that we have the marginal Fermi liquid in the nodal regions, whereas here, the preformed Cooper pairs within the antinodal regions are highly entangled. Then we asked for the ODLRO. What happens to the ODLRO? And what we saw is that in the superconductor, the D-wave superconductor, both in the antinodal and the nodal regions, the entanglement is naturally very poor. On the other hand, of course, the ODLRO is strong in the antinodal region and very weak in the nodal region, as you'd expect for a D-wave superconductor. Whereas in the spin Mott liquid, in the antinodal regions, we have some weak ODLRO in the antinodal regions, but it's almost negligible in the nodal regions. So to summarize, what we observe from our analysis, our zero temperature analysis, is that the symmetry broken Néel antiferromagnetic Mott insulator has a topologically ordered counterpart, which we call the Mott liquid. And we observe that upon hole doping the Mott liquid, there arises a quantum critical point, which involves the collapse of a pseudo gap for holon-doublon excitations along the nodal directions. Now, the QCP actually has gapless marginal Fermi liquid lying in the nodal directions, but spin gapped everywhere else. And this D-wave-like structure of the QCP then appears to give rise to the D-wave superconducting state. This topologically ordered Mott liquid at half filling is highly entangled, whereas its Néel antiferromagnetic counterpart is not. And furthermore, there's a subdominant superconducting ODLRO present in the system even at half filling. At the quantum critical point, on the other hand, the holon-doublon pair formation is replaced by the formation of Cooper pairs in the antinodal directions of the spin type Mott liquid. And this is again a highly entangled state, but with no ODLRO. In contrast, the D-wave superconducting state has absolutely no many particle entanglement, but very strong superconducting ODLRO along the antinodal directions. Thank you.
Thank you, Siddhartha. So maybe one quick question. We are almost running out of time. If there is one, because we have to finish the session. If you have a question, you can raise your hand.
Rajdeep, I have one very quick one. If nobody else
Yeah.
is there,
Go ahead.
Siddharth, one quick question.
Yes.
So if you just take a square lattice half filling Hubbard model,
yes.
And we know that at zero temperature, as a function of U, one goes from a Slater to a Mott. Well, Slater to a Heisenberg kind of. So the question is, within your way of characterizing it by mutual information, how would you characterize will you call it a crossover, a transition between the SDW and the sort of strong coupling Mott?
Well, okay, so the strong coupling Mott counterpart in some sense would be the topologically ordered system that we find here, okay? Remarkably though, we find that at half filling, I didn't have time to show this, but what we found was that at half filling, there is no critical U. And this is actually being backed up even by some other later, new studies that are happening in the literature, that at half filling on the 2D square lattice at zero temperature, there is no critical U. So there is no, in some sense, Slater to Mott like transition. Everything seems to be a Mott kind of state.
But if you look at the, sorry for prolonging one just comment. So if you look at the moment size, clearly in one limit, the moment size will get saturated. In other case, it's sort of is proportional to the U. So shouldn't that, so isn't there a
but it's, what all these studies, including ours, seems to suggest that there is no real, what shall I say, nesting Slater-like physics that is giving rise to that. It's all in some sense coming from the renormalization of the correlation effects, okay, which is closer in some sense to the Mott-like physics. And what we see from our analysis is that when you allow for symmetry breaking, this Mott-like physics is replaced at half filling by the Néel antiferromagnet that we observe.
Okay, thank you. Thank you.
Okay. Thank you, Siddhartha, for a very nice talk. So if you can stop sharing, we will move on to the next speaker.
Okay. Yeah.
Yeah, our next speaker is Priyanka Mohan from TIFR Mumbai, and she will be telling us about trigonal warping and anomalous valley Hall conductivity in twisted double bilayer graphene. So Priyanka has already shared her. So Priyanka, can you go full screen?
Yes. Can you see this?
Yeah.
Okay.
Okay. Over to you, Priyanka. Yeah, go
Okay.
ahead.
Thank you. So let me start by thanking the organizers for this opportunity. So the field of twistronics started around 2010 with the McDonald Bristreiser paper, where they studied two layers of graphene which are stacked on top of each other, misaligned by a small angle. Now, what they found that even though this model, so I have given a figure here, breaks the translational symmetry of graphene, it will result in a larger lattice known as the Moire lattice. And they also found that for some values of these twisting angles, the bandwidth can become zero, which means that you will get completely flat bands. Now, later in 2018, the MIT group found that these flat bands can host a variety of interesting properties such as superconductivity and correlated insulating states. So thus started the field of distronics. So what we will be talking, looking at today, would be a cousin of twisted bilayer graphene, which is known as the twisted double bilayer graphene, which has basically two layers of bilayer graphene stacked on top of each other. Now, this work is done here in TIFR in Professor Rajdeep Sen Sharma's group with his PhD student Unmesh Gorai, and this is the archive number of the paper. Okay. As I said, the model is twisted double bilayer graphene. So I have given a picture of bilayer graphene here. So bilayer graphene has the couplings of bilayer graphenes are, so you will have a hopping within the layer and hopping between the two layers, for example, say gamma 1, gamma 3, gamma 4, etc. And here gamma 3 is known as the trigonal warping term, and this would result in the trigonal warped band structure of bilayer graphene. And here we have two, the figure I have given is one bilayer graphene. So we have two of these models stacked on top of each other. And so you will have the bilayer graphene Hamiltonian and the coupling between these two terms. These couplings are a function of the twist angle, so which are known as the twist parameters. Okay. Now we study a range of twist parameters going from 1 degree to 5 degree. And we divide them into three: small angle, intermediate angle, and large angle. Small angle is from up to 1.5 degrees. Intermediate angle is from 1.5 to 3 degrees, and large angle is everything more than 3 degrees. Now, there are two ways you can have you can stack a twisted bilayer graphene. One is that you have an AB bilayer graphene stacked on the top of AB bilayer graphene. So the top figure here. The second one is the ABBA, that is AB and stacked, rotate by 180 degree and keep it on the top of the other one. Now these two differ because of the difference in stacking. The symmetry also differs. The ABAB will have C2X symmetry and ABBA will have C2Y symmetry, and because of this, the properties would change. So, and since this is a small talk, I would would be talking about. I'll just go to the results. What we study is the topological properties of this model. So the idea is that the topological phase can be determined by calculating the topological invariant, the Chern number in this case. And this Chern number is calculated not for the full Brillouin zone, but the Moire Brillouin zone, which is a very smaller Brillouin zone. And the topological phase diagram is given here for ABAB and ABBA. And you can see that the white lines here represent the phase boundary. So there are two phase boundaries, meaning there are three topological phases. And the first one from bottom, and this is when you increase delta, where delta is a perpendicular electric field you apply to the system. Okay, so that will create a potential difference between the layers. On the right hand side is the direct gap, which you can see that the direct gap also goes to 0 because the gap has to close when the topological transition occurs, also corresponding to the figures on the left. Now, so there are 3 phases and 2 phase transitions. To understand that, we have to recall this fact that graphene by itself has a Dirac cone at the K point in the Brillouin zone. As I said, in the case of bilayer graphene, you will have a Dirac cone, and there are 3 small satellite Dirac cones around it, thanks to the trigonal warping term. And in the case of twisted double bilayer graphene, what would happen is that as you increase the electric field, uh, the as you reach the first transition, the 3 the satellite Dirac cones in the Moire-Brillouin zone closes, as is shown in the figure B here, which each of them has a chirality of -1, resulting in a Chern number change of -3, and further increasing delta, which is electric field, they opens, the 3 small Dirac cones open, and the central Dirac cone closes, which has a chirality of 1, which causes a Chern number, the second transition, Chern number of change of 1. Okay, now we understand the mechanism behind the 2 transitions. We have the whole phase boundary and phase, we know where the phase transition occurs. And now the next question we asked is how much of this can you see in an experiment? And the reason is the following. The experiments usually measure the smallest gap in the system. And as you can see here, this is the band structure for one of the twisted bilayer models. And as you can see here, the orange band and the blue band, they always have a gap here. So there is a non-zero gap all the time. But the gray line is the Fermi energy, which passes through both the bands. In the result is that the system would be metallic even with a gap. So it is important to understand, it is important to know what would be the indirect gap, which is the difference between the lowest point in the orange one and the highest point in the blue band. Okay. So on the right column is the indirect band gap for ABAB and ABBA. And you can see that the indirect band gap makes it a point that most of the system, which is the black region in the the black region in the plot, is closed, which means these are all metallic regions. And between say 2 to 3 degree or so, you can see that you still can see 2 transitions where the indirect band gap is non-zero. So topologically, to understand what happens, we calculated the Valley Hall conductivity sigma xy, and that is plotted on the left hand side, where you can see that the sigma xy, the Chern number, it is quantized on the corresponding to the right hand side pictures. It is quantized on smaller regions here, which is between say 2 and 2.5 degrees. So okay, so we now understand which are these regions one should look experimentally to find the 3 phase, the 3 phases or the 2 phase transitions in both the models. So this is most of my talk, and the archive number is again given here. So a part of the results are presented here. We also study other things such as the difference in how the phase diagram changes with model parameters, and what are the role played by different parameters in the different couplings in the system, and so on. Thank you.
Okay. Thank you, Priyanka. So questions, if anyone has questions, we can take it.
Hi, Rajdeep. This is Shubhra. I have a question, small question.
Yeah.
Priyanka,
Yes.
you put in a magnetic field. I mean, sorry, I missed a part of your talk. So
No, there was no magnetic field. We have an electric field perpendicular to the system.
I see. So what is this Chern number about?
Sorry, Shubhru, can you repeat
So
the question?
you break the time reversal symmetry of the system?
No, actually, actually, by completely we don't. But this is calculated for the K point of the of the full Brillouin zone. And you can similarly do for a K prime point, and the churn number will be the opposite. So totally there won't be anything, but this is for different values.
Okay, so that's how you get a Valley Hall effect. But
yes,
do you? So what symmetry protects this Valley Hall effect?
The time reversal symmetry is not broken.
Yeah, what symmetry then protects this Valley Hall effect?
I think this is the C2X, the translation, the C2X and the C2Y symmetry of the ABAB and the ABBA.
I see. So this is one of these crystalline insulators.
Yes.
I see. Okay, thanks.
Any other question? If not, then let us thank Priyanka. And let us thank once again all the speakers of today's session for very nice talks. And I will hand it back to Mitro for the next session.
Sure, and let us all thank Rajdeep for chairing the session with the hodgepodge done by us in the beginning. So sorry for that. Okay, thank you, Rajdeep. I'll thank you on behalf of everybody. Okay, so an announcement. So we'll begin as scheduled at 11. Sorry for the 10-minute thing that happened in the beginning. Okay, so if the speakers for the next session are around, I will make, so Tanmay, I'll make you a co-host.
Okay.
Just a second.
So co-host means I can then unmute people. That's the.
Yeah, you can unmute or you can make other people co-hosts, I guess. And I'll also make the 4 people, the people who are speaking in your session as co-hosts, so that they can quickly share their screens when their turns come. So Kalpataru.
So Tanmay, you can also mute people.
I can also mute people. So the first thing I will do is I'll mute you.
Tanmay, you have great powers.
And now I have the powers. But that comes with responsibility.
You can even kick out people, you know.
The first thing I will do, I will kick out Amit. Because he gave me this idea.
Yeah, I would appreciate that actually.
Okay, I will do some. मेहरबानी करता हूँ मैं आपसे. रहने देता हूँ. Okay.
So there are 2 faculty invited speakers and 3 student postdoc speakers. So
yes, I have that list, right?
Yeah. So far I have made Sagar. Let's see if Manish is around. Manish Kumar, I don't see him.
Hey, can you hear me, Anumitra?
Yes.
Okay.
Amit.
So,
go ahead.
No, so how do you do the? I mean, I have to do that, right? I mean, chairing session someday, I think.
Yes. Yes.
So let me just quickly see what all does it to be. What does one do? I mean, I mean, this muting, unmuting, and all that. This is something I'm not quite familiar with. I'm not very familiar with Zoom. So okay,
yeah. So basically, I don't know if I can share my screen. Let me try to do that.
Okay.
Okay, so I have. If you can see my screen, can you?
Yeah, I can.
So, for example, for any speaker like you here, there's an option to make a host, make a co-host. Now to not show co-host because I'm sharing my screen.
So how to do that? How to make something?
So that mostly we will do. So we will do it prior to the session. So Tanmay, should we already begin? It's 11.
Yes, we can try that. So
okay. So Kalpataru, if you are around.
Yes.
So with that, I will give the session to Tanmay, who has kindly agreed to chair this session. So Tanmay, please, it's yours.
Sure. Yeah. Thanks, Anamitra. So we can start with the next session. So as Anamitra said, we'll have 2 invited talks, which means like 25 minutes, 20 plus 5, as it was instructed, and then followed by 3 contributed talks, 10 plus 2. So we'll start with Kalpataru. So Kalpataru, so can you please share the screen?
Okay, let me try.
And so just to keep reminding everybody that please mute your microphone in case you have been unmuted or you have unmuted yourself, just to avoid echoes and all. So Kalpataru, I'll give you a warning, let's say in 20 minutes or 18 minutes or so. Yeah,
Okay.
so you can keep it within 20 minutes. Yeah.
So should I start?
Yes, let's start.
Okay, so let me thank the organizers for inviting me. So today I'll speak about this inverted hysteresis in LSMO and SRO superlattices. So as I go along, I'll explain what is LSMO. This is like one kind of manganites, both are ferromagnets. And in our group, can you hear me clearly?
Yes, I can hear you clearly. No problem.
So mostly what we are studying is the, like we have one ferromagnet or superlattices. Most of the study will be on superlattices. Either we study ferromagnets or ferromagnet or antiferromagnet. So one of them will be ferromagnet, other is ferromagnet, either ferromagnet or antiferromagnet. We also started studying about insulator superlattices, but mostly today I'll talk about this ferromagnet and ferromagnet antiferromagnetic superlattices. And what we are interested in is the physics at the interface. So when you join ferromagnet with a ferromagnet or antiferromagnet, what are the physics that is being changed or something different from the bulk ferromagnet? And the change in the physics will be governed by the charge degrees of freedom, lattice degrees of freedom, orbital degrees of freedom, and spin degrees of freedom. So that's why it's very more or less complicated, at least complicated to us. And because the delicate magnetic and electronic phases will be there, then then electronic and magnetic reconstruction will be at the interface. So we need a microscopic level studies to unearth what is the physics at the interface. So today I'll speak about this ferromagnet and ferromagnet. So I have colored it 2 colors. So one of them is ferromagnet with high TC, let's say 300 Kelvin, another at low TC. And they interact antiferromagnetically to each other. And in research interest wise, we mostly study magnetic materials, oxide heterostructures, and 2D material cluster. We use both model Hamiltonian calculation and sometimes we use also DFT calculations. The plan of the talk is like this. So I'll start with ferromagnet and antiferromagnetic heterostructures. So this will be LSMO, PCMO like manganites. Then I'll move to what is the exchange bias in oxide heterostructures, negative exchange bias and positive exchange bias. Then I'll move to magnetism in ferromagnetic heterostructure. At that point, I'll show you how they are antiferromagnetic coupled to each other. Then I will show you what is the inverted hysteresis loop in LSMO, SRO. Then something called magnetic switching, which is unconventional. Then if time permits, then I'll move to more complicated heterostructures. So to start with ferromagnetic and antiferromagnetic oxide heterostructures, so we have to, I'll give you the example in the next slide, but we join ferromagnet and antiferromagnetic insulator, and we can vary this width of the antiferromagnetic insulator. So varying even we fix the width of the antiferromagnetic insulator. What I'm saying is that if you join a ferromagnet with an antiferromagnetic insulator, then there will be charge transfer from the ferromagnet to antiferromagnet, because the Fermi level is there will be mismatch in the Fermi level. So the charge transfers from the ferromagnetic to the antiferromagnetic. So there is charge transfer, there will be magnetic instruction because these are magnetic materials. As a result, so there will be some magnetic dead layer at the ferromagnetic interface. What I meant is that if we are planning to make a ferromagnet, ferromagnetic junction, but that is expected. This is ferromagnet, and antiferromagnet insulator. But what in reality we get is that ferromagnet, the end point of the ferromagnet are magnetic Dell layers. It is no more a ferromagnet at this end layer. They become spin disorder kind of thing. So that is due to charge transfer from the ferromagnet to the antiferromagnetic insulator. So there are many experiments. I'll quote this experiment, which is 2007 PRL paper. So what they have done is that there is ferromagnet of LSMO and antiferromagnetic insulator from the PCMO. PCMO is one of the charged or insulating manganites, and LSMO is ferromagnet. So what they have shown is that if you vary this width of the antiferromagnetic insulator, you can see that the magnetic moment in the antiferromagnetic layer, this is the magnetization in the antiferromagnetic layer, that increases and then decreases. That we try to analyze using model Hamiltonian calculation, two-band model Hamiltonian calculation. So that we could show that we have used a 24 cross 24 lattice. So you see that the magnetization first increases with width and then decreases. And this is due to the magnetization in the antiferromagnetic insulating layer. So this we can show, this is a 2D calculation, but what I'm saying is that if you join a ferromagnet with antiferromagnetic insulator, then there will be charge transfer from the ferromagnetic layer to antiferromagnetic insulating layer. Then because of this charge transfer, the ferromagnetic layer at the interface will lose its magnetism. So the magnetism will be like spin disorder at the interface, and that gives us to a magnetic Dell layer kind of thing. Then if we move to what the main topic of this talk is exchange bias in oxide heterostructures. And if I move to this positive and negative exchange bias, if you go back to 1956, there is iron and SM cobalt. This is one of them is ferromagnet, another is antiferromagnetic. So this is a ferromagnetic antiferromagnetic bilayer. So we can see that if the cooling field is positive, then the hysteresis slope shifts to the left. Okay, this is called negative exchange bias. And if for positive exchange bias, even if the cooling field is positive, if you see the this hysteresis slope shift to the right, and this is the positive exchange bias, and this also depend upon the materials. So this is also iron and Fe fluoride, and this is also recently observed LSMO and SRO. So what is difference between these two materials and these two means what is the difference between this set of materials and this set of materials? If we see closely, then what we see that there is a ferromagnetic interaction at the interface. So what I mean is that the iron and SMO cobalt, this type, this material, sorry, this material is interacting with the second material ferromagnetically. The interaction at the interface is ferromagnetic. But this set of material, which is get the positive exchange bias, the interaction is antiferromagnetic. So even though this is a ferromagnet, LSMO is a ferromagnet, SRO is a ferromagnet, but the interaction at the interface is antiferromagnetic. So depend upon whether the interaction at the interface is ferromagnetic or antiferromagnetic, we will get negative exchange bias or positive exchange bias. And then we'll move to the specific case, LSMO and SRO. Why LSMO and SRO? LSMO means is soft ferromagnet, which is TC is 300 Kelvin, and SRO, which is hard ferromagnet, but the TC is 150 Kelvin. So SRO, you can see the blue one, which is the hysteresis loop is very large, and that's the hard ferromagnet, signature of hard ferromagnet. Cohesive field is large, but LSMO, the cohesive field is very small, but the TC is large. So these two, although they are ferromagnet, but their magnetic properties are completely different. One is soft ferromagnet, another is hard ferromagnet. If you join these two ferromagnet, then we'll get the positive exchange bias. So this is from this APL paper 2004. So this is like in 2004 or means early 2000. So they show that if they join two ferromagnets, we'll get a positive exchange bias. And moreover, why LSMO SRO? Will have a good quality of heterostructures. So generally, it's not very clear. If you join two materials, the heterostructure will be of good quality. But in LSMO and SMO heterostructure, the quality of the heterostructure at the interface is very clean, more or less clean. And the LSMO is half metallic. And in the negative point is that the strontium euthenate is very complicated. Even the bulk strontium euthenate is very complicated. And then from the experiment, what we know is that antiferromagnetic interaction at the interface. So if you join LSMO and SRO, the interaction at the interface is antiferromagnetic. From this curve or this from cartoon, from the high temperature, if you go from the high temperature, LSMO and SRO, L is for LSMO, S is for SRO, there is no magnetic moment ordering. There is no ordering at all at high temperature. So at TC of LSMO is 300 Kelvin. If you lower the temperature below 300 Kelvin, you'll see that LSMO is ferromagnetically aligned. But strontium euthenate, there is no alignment at all, even above 150 Kelvin. If you decrease the temperature below 150 Kelvin, we'll see that there is ferromagnetic alignment in the strontium euthenate, but typical means also there is antiferromagnetic alignment. So LSMO and SRO are antiferromagnetic aligned below 150 Kelvin. So this is what we will use in our calculation, that ferromagnetic, they both are ferromagnetic, but at low temperature they are antiferromagnetically aligned. And this is the inverted hysteresis and double flipping. So you can see that if you from the hysteresis loop at high field, both are ferromagnet. So at high field, if you see this cartoon, so at high field, both are ferromagnetic aligned. Because we apply very large magnetic field, so both LSMO and the SRO are aligned in the same direction. But if you decrease the magnetic field before it hits zero, means if you remove the magnetic before even that, you'll see that both of the are aligned antiferromagnetically, LSMO and SRO. And if you apply very large negative magnetic field, then it will align in the opposite direction, which is means typical. But this one, which will be before the magnetic field hits zero, they are aligned antiferromagnetically. And this hysteresis loop shows that. And because we'll see why this is called inverted hysteresis, because if you go down from here, you see that. And if you go down from here, this hysteresis loop in between, it's like inverted. And this is at 10 Kelvin. If you go to 100 Kelvin, it's even more complicated. At high magnetic field, it is known that they will be in the same direction. But if you decrease the magnetic field little bit, means towards zero, then you see that they are antiferromagnetic. But here the antiferromagnetic is different from this antiferromagnetic. Here the antiferromagnetic is that LSMO switches. Soft ferromagnet switches first. But here at high temperature, the LSMO is fixed, but SRO switches first. So this antiferromagnetic and this antiferromagnetic are different. So if you decrease it further, you'll see that these two ferromagnets, they are completely reverse their direction. LSMO becomes down and SRO becomes up, which is not present at low temperature. And if we apply very large magnetic field, definitely both samples goes in the down direction. And then the next point is we get an insulating behavior from metallic bilayers. So if you join two ferromagnetic layers, both are metallic, but if you join both of the layers, because of this antiferromagnetic interaction, you'll see that there's an insulating behavior. From this is the experiment from Takahashi group. What this is saying is that if you have manganese and ruthenium, these Eg electrons can hop from one layer to other layer, one ferromagnet to other ferromagnet, if they're antiferromagnetic. So if they're antiferromagnetic, then it's metallic. If they are ferromagnetic, it's insulating. So this cartoon shows that if this is ferromagnet, the conductivity is low. If this means these two cases, right and left cases, both are ferromagnet, aligned in same direction, conductivity is low. But if they're antiferromagnetic, the conductivity is large. So that's because if they're antiferromagnetic, this Eg electron can hop from one layer to other layer. So with this all input from the experimental side, so we have a model, we have construct a model Hamiltonian for LSMO and SiO2 structures. And this is the LSMO, which is like 3d4 electrons are there. There will be crystal field splitting, and we treat this classical spin as a classical spin. There is EG electrons, and there is a Hund's coupling in between them, and we take the super exchange interaction between manganese and manganese. Then there is a double exchange interaction. So these things we include in a model Hamiltonian. And for SRO, the experiment shows that the magnetization depends upon the thickness. If you grow the bulk strontium ruthenate, then you will see that depend upon the growth direction, either 001 or 110 or 111, the magnetic moment, saturated magnetic moment is either small, then it increases further, which 110, then for 111, it's maximum, like 4 μV. From this cartoon of this paper, from this job paper, which we model our Hamiltonian, that there's T2G electrons and EG electrons, or T2G electrons which will be mobile. So this is the cartoon. So we have Mn3 plus, we have T2G electron and EG electrons. Here ruthenium 4 plus, we have T2G electrons and T2G which will be mobile electrons. And we have model Hamiltonian with kinetic energy, Hund's coupling between the T2G electron and EG electrons. There is super exchange interaction between classical spins. Then we apply magnetic field. Then we take the anisotropy of the material also. Because strontium ruthenate, the anisotropy is very large as compared to LSMO. And we choose parameters such that LSMO, ferromagnet, but it's soft ferromagnet. And for SRO, it's hard ferromagnet. TC of LSMO is large, TC of SRO is small. Then anisotropy, you mostly take the anisotropy of the LSMO is 0 and SRO is 0.1. And we do have a spin for Monte Carlo, so I will not go detail into it. But we take a 6 into 8 lattice where the LSMO and one of them is SRO. M is the number of layers of LSMO, and N is the number of layers of SRO. So we need a 6x6 lattice at the interface to study the properties of at the interface. So this is the model Hamiltonian, as I told you. So what the electron density we take for LSMO is 0.7, and for SRO, strontium ruthenate, we are taking electron density to be 0.4, and we show that TC for LSMO is greater than TC for SRO. So, and the cohesive field of LSMO is smaller than the cohesive field of SRO. So we choose our parameters as that. So LSMO, here we show the TC of LSMO and SRO. So TC of LSMO is, it's not twice big, but we have chosen such that it's larger. LSMO is, TC of LSMO is larger using these parameters. And using the same parameter, we show that the cohesive field of LSMO is smaller than the cohesive field of the SRO. And whether they are antiferromagnetic, when you grow layers like 5 layers and 3 layers, we see that if we go from the high temperature, the LSMO layers from these 3 points, we can see that LSMO layers align ferromagnetically fast. SRO, there is no alignment at all at this temperature, up to this temperature. Below this temperature, this SRO aligned, but in antiferromagnetic direction. This is for 5 plus 5 layers of the LSMO and 3 layers of SRO. If you go to the next one, so if you have 4 plus 4 layer, you can see that at high temperature, there is no alignment. But if you, from these 3 red points, you can see that LSMO is aligned, SRO is not aligned. But if you decrease the temperature further below this one, LSMO is aligned and SRO is aligned, but they are antiferromagnetic. Because they have the same layer structure, 4 plus 4, the magnetization goes to 0. This shows that, and we have shown, we have seen directly that they are antiferromagnetically aligned. One layer is antiferromagnetically aligned to the next layer.
So Kalpadaru, just to remind you, we have sort of used 19 minutes or 20 minutes.
Okay, so this is the positive exchange bias. So we also show that there is positive exchange bias in LSMO. If you fix the SRO and do the LSMO layer, then you will see that this is the positive exchange which we get also from the experiment. In the inverted hysteresis wise, you can see that this is the experimental I have shown you from the applied physics later. And calculation wise from spin Fermi and Monte Carlo calculation, we can see that there is a one-to-one matching. First, if you apply large magnetic field in our calculation, we see that LSMO, L and S, L is for LSMO, S is SRO, they are ferromagnetically aligned. But if you decrease the magnetic field, then these structures like LSMO first flips, then SRO, no, sorry, LSMO first flips and SRO is fixed. If you apply large magnetic field, both are flipped. But in the down direction, I think this it's symmetric. And this is called inverted hysteresis because of this loop is very inverted. Generally, it's like other way around, but here the loop is first goes to down and then while coming back, it goes up. And this is the inverted hysteresis loop. And the next one is the spin flipping, the unusual spin flipping, which has more physics there. So we can see that this is also one-to-one with our experiment. So first, if you apply large magnetic field, ferromagnet, first LSO. If you decrease the magnetic field, SRO flips its sign. Then if you decrease further, then both of the layers switches the direction. Then applied large magnetic field, both goes to negative. And also we have calculated the conductivity, and we show that if in this case, if the parallel conductivity is smaller, if the parallel conductivity is smaller, if they are antiferromagnetic, the conductivity is large, which is more or less similar to the experiments. And we are also studying more complicated magnetic structures like this is the what I told you, but LSMO and SRO, like why there is an induced magnetic moment in STO, then the room temperature ferromagnetism in gallium manganese arsenic. So in most of the cases, what we learned, there is charge transfer across the interface. Then oxygen deficiency is also there, interlayer antiferromagnetic exchange coupling also there, all plays an important role. And we are also studying ferromagnetic and ferroelectric superlattices nowadays. So, and I will not go into detail, but so this is more or less like a conclusion slide. So theory versus experiment. So this is the inverted hysteresis found in the experiment, and more or less with our model Hamiltonian calculation, we have more or less there's one-to-one matching between the experiment and we have taken all the ingredients from the experiment, the antiferromagnetic interaction and many other parameters from experimental results. And thank you. So, and this work is done by Sandeep Haldar, who is a PhD student.
Okay. Thanks, Kalpataru.
Yeah,
Thanks a lot for the excellent talk. So you can have color questions, and especially people can also type question in the chat box so that you can go one by one accordingly. Otherwise, just go ahead. I think I see a question from Ganesh. Ganesh, please go ahead.
Hi, Kalpataru. So
yeah,
I missed this part. So what is the nature of the Hund's coupling in SRO?
So it's antiferromagnetic.
And in LSMO, it's ferromagnetic.
Yeah,
is it? That's the difference.
Yeah,
yeah. So Sanjeev Kumar and I have used a very similar Kondo lattice model for LSMO SRO. I'll send you an email. I'll send you some references. Thank you.
So is there more question?
Can I quickly ask one? Hi, Anamitra. I can raise my hand. Sorry.
Can you tell who is speaking? Who is asking the question?
Anamitra.
Anamitra. Sorry.
Sorry, that's okay. So, no, Kalpataru, I missed part of your talk. So, did you take into account the electron-phonon coupling in the theory as well?
No, we have neglected this electron-phonon coupling because, as you know, this ferromagnet's electron-phonon coupling is very weak at LSMO. That's what I think. So we have neglected that electron-phonon coupling.
That's okay. It was just a clarification. And second thing was, did you worry about this Madelung energy? I saw something like with regards to long-range Coulomb towards the end.
No, we have taken that into account by potential. So we have given different potential to different layers. So that's how we take care of it.
But it is done self-consistently, you mean?
we have done self-constantly and also by putting potential by hand, both, but the self-constant calculation are very time exhaustive. So we have done the both of them.
Okay, okay, sure. Thank you.
Okay, so we can have one more question or so, if anybody has. Maybe Kalpataru, I have one. So
yeah.
You showed at the beginning that the charge transfer is pretty important.
Yeah.
In this model, which is sort of an extension of teacher model, like this charge transfer physics is included.
So we fix the charge density, like let's say 0.5 to everywhere. Then we see at each layer what is the charge density. And because of this, one is ferromagnet metal, another is insulator. We see that you can see that this is like everywhere it should be 0.5, but there is the electron density at the interface decreases drastically. And we do it self-constantly. We don't control the charge density by any means. We fix the chemical potential such that the whole electron density of the whole system will be 0.5.
I see. So you don't vary that that electron density.
No, so we fix that to 0.5 and we see what happens to the electron density of each layer.
I see. Okay. Yeah. So I don't see any other question, at least no raised hand. So in that case, Kalpataru, thanks a lot.
Yeah, sure.
In the interest of time, we'll move to the next talk. So thanks, Kalpataru, again.
Yeah, thank you.
So next talk is by Shantanu Mukherjee. Shantanu, can you start sharing your screen?
Yeah, sure, I'll do that.
And in the meantime, I'll tell. So he is an assistant professor at IIT Madras in the physics department. And his talk, the title has changed slightly, I guess, no?
Yeah, the meaning is the same. I just changed the words.
So it's again strontium ruthenate and hot parity superconductivity. So okay, I think you will give the background, right?
Yeah, sure.
Yeah, okay, thanks.
So yeah, thank you for inviting me. So as you know that we are on a much more serious lockdown here at IIT Madras the last few days. So everybody is working from home. I wanted to talk about strontium ruthenate, but essentially the other end of the Rudelston and Popper series with respect to what Kalpataru talked about. The talk, this is one of the materials that I'm interested in right now. But a majority of the talk, the way I have set up is essentially kind of looking at many of the recent experiments, interesting experiments that have come in on this system. So a big part of the talk would be actually a review talk. So apologies to people who have been following this system in some detail. But I'll just, as I go along, I'll explain the particular ideas and what do they mean from a theoretical perspective. So I'll start off by kind of completely generic ideas for people who are not directly working in this field, that all of us know that the Cooper pair wave function for some irreducible representation gamma can be written in terms of momentum dependent part and a spin part for the wave function. If you have a material, that is the spare wave function, if you have a material which is described by a symmetry group which contains a part which is the point group symmetry of the crystal lattice, the time reversal operator and the gauge group, then the crystal can be described by this particular symmetry group. If you have a conventional superconductor, as we know that the primary normal to a superconducting transition is described by the breaking of this U1 gauge symmetry. If you have an unconventional superconductor, you would have additional symmetry breakings in your system. For example, the point group symmetry could be broken, or in some cases, time reversal symmetry could be broken. Although now kind of we don't really use that necessarily as a definition of unconventional superconductivity, owing, for example, you have the iron-based superconductor where you have a sign changing S wave state, but from a pairing perspective, it's still unconventional. The spin part of the wave function can exist for this the two spin-off fermions that pair can either give you a spin singlet or a spin triplet state. If you have finite spin orbit coupling in your system, then effectively we rather describe them as a pseudo spin singlet and pseudo spin triplet. We do that because we still have Kramer's degeneracy in our problem, and there is this twofold degeneracy. So when we say typically spin singlet or spin triplet, we are implying pseudo spin singlet and pseudo spin triplet. Now the exclusion principle also tells us that if you have a spin singlet state, then the momentum part of the wave function would be even under k, even function of k. And if you have odd parity state, then the momentum part of the wave function would be odd under k2 minus k transformation. You can then expand, let's say if you're working with an even parity state, you can expand the momentum part of the wave function in terms of order parameter eta I and a basis function that corresponds to this particular gamma g irreducible representation of the point group. So if a gamma g has degeneracy of m gamma g, then you sum over all of them to write down this part of the wave function. So if you have a SO3 symmetry, for example, like in superfluid helium-3, the gamma g for, if this corresponds to L equal to 2, then these m values would of course take 5 values. Below, I give you an example of a representative basis function for the A1G representation, kx square plus ky square plus kz square, and also idea about a B1G basis function, which is a kx square minus ky square. It is to be noted that the way we write it out here, these are just representative wave functions written for the lowest harmonics. But for the same B1G, you can of course write down in a higher harmonic the same basis function. Now, the effect of having significant contribution for higher order kind of harmonics in your basis function is to bring more structure into your wave function and the gap function that you have in your system. Although it does not, of course, it has to have the same symmetry. For the odd parity states, however, you can write down the basis, the wave function in terms of these d vectors. You can choose to write it in this particular, this is kind of the popular way of writing it, where these d vectors point along these spin directions determined by these components of the polyspin matrices. Now, if you have spin orbit coupling in your system, a strong spin orbit coupling in your system, then the d vectors that you have in your system can be expanded again in terms of order parameter components eta I and a vector basis function, which you corresponding to, let's say, some irreducible representation gamma u. And if you write down this in terms of these basis functions, then the basis functions are expanded in terms of these unit vectors x cap, y cap, z cap for the spin vector, and these directions are determined by the directions of the crystal lattice. So here I give you two examples of two d vectors, one corresponding to the A1U representation, which has the symmetry of the lattice, the full G symmetry, and a B1U representation written down out here for a lower symmetry group. So if you go to the problem of strontium ruthenate and you talk about the point group symmetry, the gamma that you have corresponds to essentially D4H symmetry. So you can look at, you can write down from the character table all the irreducible representations and the possible superconducting states that you can have in your system. So each superconducting state would correspond to a subgroup, an invariant subgroup. And you can see that in general, there are effectively 4 possible even parity representations and one two-dimensional even parity representation, 4 one-dimensional. And similarly, for the odd parities, you have 4 odd parity, one-dimensional odd parity representation and 1 two-dimensional odd parity representation. Now, if you look at some of the basic properties of strontium ruthenate, it is an unconventional superconductor, which means that it is believed that the pairing is likely mediated by spin fluctuations rather than electron-phonon interactions. What that can indicate to is that typically if you have a superconductor which is governed by electron-phonon interaction, that the wave function tends to belong to the attractive pairing, for the attractive pairing belong to the A1G representation or the S wave pairing. If you have a spin fluctuation mediated pairing, well, all you can say at this point is that all irreducible representations generically are into play as possible superconducting states. The details about what is preferred are kind of governed by the details of the crystal structure. Now, again, if you look at the low energy electronic structure of this particular material, they are primarily governed by the dxz, dyz, and dxy orbitals on the ruthenium. That kind of accounts for the largest density of states at the Fermi energy in the normal state. And the Fermi surface for this material is found to be quasi 2D. That means this is a layered material. Like I said, that this is the other end of the Rudelston-Popper series. And what this kind of hints towards is that if the material is layered, then it is likely that it is energetically more favorable to pair two electrons in the ruthenium oxide plane as compared to two electrons paired in two different planes, right, for these quasi 2D materials. So what it means is that if you were to typically try out a pairing calculation, although it does not discount it, it is less likely that you would have states like the EG representation KZ-KX and KZ-KY being preferred ground states in such calculations, because if you were to look at these in real space, effectively these correspond to electrons pairing in two different ruthenium oxide plates. The third aspect is that there seems to be a presence of significant spin orbit coupling, and that implies that effectively, like I told you, that this is a typical basis in which you can account for the presence of a spin orbit coupling in the symmetry of the wave functions that you have for a system in the odd parity representations. Now, again, the normal state is well described by Fermi liquid theory, and this is the reason why strontium ruthenate as a superconductor has been so famous, because you are not to worry about unusual charge order phases, or typically you don't worry, or pseudogap phases in the normal state, making you unsure whether you should be looking just at the representations of the D4 edge group only, or there is some other lower coupling of lower symmetry orders at play. So one of the first experiments that I want to talk about is this NMR night shift. As you know, that the NMR night shift is governed by effectively the nuclear spins as they precess about an external magnetic field. And if you have a RF pulse, then you find a resonance where the precession frequency, which is determined by the gyromagnetic ratio and external field, matches with the frequency of the RF pulse. The night shift corresponds to the fact that these nuclear spins are essentially coupled to the conduction electrons that you have in your system. So that causes a shift in the frequency, the resonant frequency. And now, if you kind of think about this, you can understand that if you have, for example, superconducting state where the electrons are paired up, that is going to cause the transition to the superconducting state is going to cause a transition to the NMR night shift. So out here, I talk about first the spin even parity pairing, and you can show that the NMR night shift is actually directly proportional to the paramagnetic susceptibility. And as you can expect that if the electrons pair up in an even parity channel, you have lesser and lesser electrons as you go down in temperature below Tc, which are available for kind of contribution to the night shift signal. And effectively what you find is that the main contribution to the paramagnetic susceptibility is only from the elementary excitations. Strictly at t equal to 0, the night shift should go to 0, and this behavior is kind of governed by what is called as the Yoshida function. The Yoshida function, if you have an even parity gap, a full gap like in classical superconductor S-wave gap, behaves like an exponential temperature dependence. If you have a nodal gap, you would get power law dependence in this Yoshida function. For the triplets, it is kind of more interesting. If you, for example, for the moment, consider a weak or negligible spin orbit coupling, then the external magnetic field in that case is going to determine the quantization axis. And what you find is that if you put your external magnetic field along the D vector in your system, then the spin projection along this magnetic field is effectively going to be 0. It's going to correspond to the ms is equal to 0, up, down, plus, down, up component, contributing along this longitudinal susceptibility. And the susceptibility still would be governed by this Yoshida function, because there are no Cooper pair electrons effectively contributing in this direction. If you have the external magnetic field rather along the dx and dy direction of the D vector, then you effectively are coupling to the other spin projection 1 and -1, and effectively they would contribute to the night shift, to the susceptibility. And what you would find is that the susceptibility actually stays, as you go below the superconducting transition, almost stays unchanged to the normal state value. Here N0 forgot to say is the density of states for my system. So this is kind of done for, of course, for the non-interacting system. If you include electron correlation in a more involved calculation, you could calculate all these quantities. So the overall, the point to make out here is that if you have a spin triplet superconductor, you expect that the NMR night shift should be independent of temperature. This is one experiment from 1998 by Maino's group in Japan. This is the famous experiment where they found that the NMR night shift is actually unchanged as a function of temperature. And this was the evidence that strontium ruthenate seems to be indeed a spin triplet superconductor. However, more recently, when this experiment was performed in strained in samples which were uniaxially strained, what they found is that below the transition temperature, the NMR night shift gets suppressed. And this was kind of initially thought to imply that what is happening is there is a transition from a triplet to a singlet state. However, as they reduced the strain to 0, what they found is that the NMR night shift still kind of was significantly suppressed below the transition temperature. And as the story goes, it later turned out, in fact, Maino also was able to check that the problem or this experiment, what was happening is that the energy that is provided by the RF pulse was actually causing local heating of the sample, which was actually making the sample locally normal. And that was causing this flat curve out here. If you were to kind of calculate this with a pulse with a lower energy, you could get the dip in this, see the dip in the NMR night shift. So this entire story, which was very crucial, this strontium ruthenate in a sense is back. And this kind of experiment seems to indicate that probably a strontium ruthenate might actually be a spin singlet superconductor from the behavior of this NMR night shift. The other aspect which kind of favored the chiral triplet superconductor, you know that people working on topological materials also have found this material interesting because the chiral triplet superconductivity had meant that possibility of edge states, topological edge states in the system. But the time reversal symmetry breaking is still kind of observed. That story has not died out. If you do consider muon spin relaxation rate experiments, you find below TC, the relaxation rate kind of increases. And in fact, in polar Kerr experiments also, you find order parameter like dependence in the polar Kerr angle below the superconducting transition, indicative of some local magnetic moments, which are believed by a significant community to be due to intrinsic moment in the Cooper pair wave function. The strain did not just kind of create this issue with the NMR night shift. Another exciting result from the strain experiment was that as you increase the uniaxial strain, you found that the TC kind of enhances strongly. The TC shows a peak behavior before it is going down. One kind of the simplest picture in which to see this is if you look at the normal state density of states as a function of a compressive or tensile strain, you find that at a critical strain, there is a Lifshitz point that kind of forms near this x0 and y0 points. And at a critical point, you have this this sharp peak in the normal state density of states. However, it is believed that there is not just a TC enhancement due to enhancement in the density of states, but there is actually a transition from one superconducting state to another. And it's a much more complex beast if you kind of look at it from a pairing perspective about what's happening as a function of strain. If you consider the strain and if you consider, for example, the superconducting state in a Ginzburg-Landau kind of approach, and if you consider, for example, let's say a two-dimensional representation, delta 1 and delta 2, which would correspond to here, let's say, for example, either the EG or EU representations, or you could also have a two-dimensional representation, which are accidental degeneracies of two different representations that you have out here. So if you consider that kind of a picture, then you can write down a free energy for the superconducting state. You can figure out how many fourth order invariants you have. You can, and let's say that we consider a strain component, which is primarily the C66 strain. The C66 strain is, if you consider the strontium ruthenate square lattice, the C66 strain would correspond to compression along one of the diagonal directions and expansion along the other. So the interesting aspect about the C66 strain is that if you consider a strain order parameter UXY, because this transforms as a XY, any coupling of this strain to the superconducting order parameter has to be through a term which transforms as a xy. The reason is that each term in the free energy must, after all, have the full symmetry of the D4H, must belong to the A1G. And if it, and you know that the xy belongs to the B2G, so effectively this entire term has to belong to B2G square, which is A1G. Now, why this is interesting is because this implies that you can never have a coupling of this UXY strain to a one-dimensional representation, because the square of each one-dimensional representation by itself would belong to the A1G and not to the B2G. And you must have a square here because you have to maintain the U1 gauge invariance in your system. So if you have a coupling to this particular strain, it tells you that that coupling has to be through a two-component order parameter. And if this term is allowed, physically what it means is if you were to do, for example, ultrasonic experiments, you look at the sound velocities corresponding to this strain, what you would find is that this strain coupling would mean that right at TC, there would be a discontinuity in this C66 components. So this experiment, which was recently done, actually found a clear kind of jump at the TC in the C66 component. And what this kind of tells you is that indeed, it seems that this particular material has to be described by a two-component order parameter. Now, like I said, the two-component order parameter, one intrinsic order parameter, if we for the moment ignored the triplet states, considering that from the NMR perspective, then the only is the EG representation, which is the DXZ DYZ, or kind of based on the type of nodes that you see in thermal conductivity experiments and so on, you could consider an accidental degeneracy between D and G states that you see out here. Like I said, that this particular state is kind of a natural candidate until you feel that the quasi 2D nature would make it very unlikely for this particular state to be a ground state wave function. That kind of makes this a possible candidate for the superconducting state, accidental degeneracy.
Santanu, you have exhausted like 19 minutes or so.
Okay, yeah.
You have like 6 minutes more.
Yeah, sure. So now I kind of start off with a picture where kind of I consider a two-component order parameter, which is a free energy, again with a quadratic Hamiltonian and a quartic Hamiltonian. And like I said, that you can consider a dx square minus y square and a g order parameter having accidental degeneracy for the wave function for the system. And you can solve this wave function, and you can find as a function of gamma 1 and gamma 2 different regimes from the free energy that would effectively be the different ground states. The 1I would be the state that breaks time reversal symmetry, but depending on where you are in the parameter regime, the other states could also form. But however, one interesting aspect we find is that if you consider the full pairing calculation, there is another state which has almost the same symmetry as this D and G. That is what is, I haven't written the prime, what we can call as the S prime and the DXY state. And in fact, in the parameter region, this state can also turn out to be the ground state. Why I call this as a S prime is that although this is a A1G representation, because of the contributions from higher harmonics, what you find is that this state, the gap becomes extremely small due to at the 1, 0 and 0, 1 direction, that is the x square minus y square locations. And it's, which effectively means that it is very anisotropic. If you consider this particular gap, then you have a similar phase diagram, except that by symmetry for a normal to superconducting transition, this regime would be forbidden. You can also consider, like I said, a coupling of these two-dimensional order parameter to strain. And if you consider that coupling, what you find is, like I said, that it couples to the this two-dimensional order parameter. And you can kind of solve this entire problem for F0 and F1 as it was done by Kivelson, proposed by Kivelson recently. And so they proposed it for the D and G, but you can also do it for the S prime and D that we find. And what you see is that you have different regimes of transition temperature for a first transition and a second transition within the superconducting state. And for the higher order transition for 1, 0 and 0, 1, the temperature, the TC dependence of the strain goes as quadratic in T. And for the lower transition, you can get to a time reversal broken state with a temperature dependence of the strain, again quadratic in T. However, if you are in the regime where the 1, 1, 0 is the ground state corresponding to the D and G representation, then you find that the TC dependence of strain that you would observe in experiments, you should expect a linear dependence in T, and the second transition would correspond to a quadratic dependence in T. So this kind of helps you to understand that when you look at the different type of strain, here I have only mentioned it for the XY strain, but you also have the B1G strain and the A1G strain, and each of them have their own TC dependence of strain. For example, for this B2G strain, it is actually quadratic TC dependence of strain, which kind of seems to indicate that one of these must be the high temperature phase from normal to superconductor. However, if you consider, let's say, the pairing calculation, what we find is that although the DG scenario has got many advantages in terms of the nodal properties and so on, almost this we expect, as expected, the DXZ, DYZ never follows to be the ground state. So this would be a calculation where you consider the full tight binding Hamiltonian with the L dot S coupling, including the spin flip terms, and then you do a pairing calculation within flex. You never find the DXZ, DYZ to be the ground state. And however, the other problem is that this G state is also never showing up as a ground state in this parameter space. What this implies is that though you get the other component for the DG accidental degeneracy scenario to be the ground state, it is very hard for these two states to have accidental degeneracy if they are kind of well separated in energy. So this is kind of a issue right now in terms of understanding, comparing the experiments with the microscopic calculations. However, if you consider the B1G calculation, so this was a calculation in terms of the Hubbard model and the BDG, and look at it as a function of strain, what you find is that the regime in which the B1G or the dx square minus y square is the ground state, the TC dependence of the superconducting gap does show a hump-like behavior, and this is kind of not expected in every case. For example, when we look at it for the chiral triplet state, we never find this hump, rather a TC which continuously goes up beyond the Van Hoff singularity point, which is at about 0.45 out here. Yeah.
Anthony, you are about to exhaust all your 25.
Okay. I'll end it. Thank you. So I'm almost done. Yeah. Thank you. So yeah, Tanmay, I'm done.
Okay.
Yeah.
Yeah. Thanks.
Thanks.
So I mean, you can keep the summary so that people can also read it. While if there are any questions, we can have a discussion.
Sure.
Yeah. Is there any question? So Shantanu, maybe I will start. I have few questions, but I will have to limit to one or two.
Yeah.
So can you go back to your free energy?
Which one? With the strain coupling?
Yeah, with the strain coupling. Your free energy, not the Kivelson's one. I think this is the Kivelson's one, right?
Yeah. This is
can you go back to your one or the one that you showed earlier? Go back.
You're talking about this one? Yeah.
So this strain term, so first of all, it will probably be only for one sign of the strain, right? Which will be one of them, either compressive or tensile.
So this mode, Tanmay, would be effectively for this C66 component. So you effectively are kind of here looking at experiments where you're putting in transducers and kind of you are exciting different modes of oscillations of the sound wave, right? So this would be essentially the mode where you have expansion along the, let's say, 1-1 direction and compression along the 1-1 direction. So that would be this strain mode that would be considered.
And this one, the way the coupling is done, it's quadratic, but it's kind of a different gap parameter, right? So is it going to, will there be any issue with the stability? Especially it looks like, it's like, so there will be a free energy minima only for either positive delta or negative delta. It will break that symmetry, a positive delta, negative delta, na?
You mean the superconducting gap values?
Yeah.
That's
the energy with the gaps.
Yeah.
So it will break that Z2 symmetry, right?
That should not matter so much, Tanmay, because when we kind of look at the ground states of this particular superconducting state, you can always multiply the gap by a global gauge e to the power I pi, which won't affect the ground states of the free energy because the symmetry remains the same, the overall symmetry. So the way we calculate it is we essentially kind of integrate out the superconducting states out here. And the C66 component is calculated by the second derivative of the free energy with respect to the strain component. So this is irrespective of the sign of delta 1 and delta 2 in that sense.
No, I see. Okay.
Yeah.
So actually sort of exhausted time.
Okay.
So in that case, Shantanu, yeah, thanks a lot for the excellent talk.
Thanks.
We'll move to the next topic. Thanks, Shantanu.
Yeah.
So next talk is a contributed talk by Sagar Sarkar from SN Bose National Center for Basic Science. Sagar, are you there?
Yes, can you hear me?
Yeah, I can hear you now.
Yes, so I'm going to share my screen.
So he will be talking about charge ordering in rare earth nickelates.
So is my screen visible?
Yes. So it's 10 minutes plus 2. So maybe I'll give you a warning around 8 minutes. Huh?
Sure.
Okay.
Thank you. Thank you, Dr. Das. And I would like to begin by thanking the organizers for organizing this event and giving me this opportunity to talk. So I will be talking on charge ordering, coupled electronic and structural properties in rare earth nickelates. So this work started when I was doing my PhD with Professor Priya Mahadevan at SN Bose Center, and in collaboration with many others, and their names are shown here. Right now I am doing postdoc in Asia Pacific Center in South Korea. So let us start with the structure of these materials. So these materials are having a chemical formula RnIO3, where this R atom stands for the rare earth atom. And they have a perovskite crystal structure, and that crystal structure can be easily described with the help of an cubic unit cell, which is shown here. And in this cubic unit cell, the nickel atoms basically sits at the cube corner positions, and the oxygens are at the edge centered position of this cube. And together they form an corner sharing octahedral network. And the rare earth atom basically sits at the cavity of these octahedrals. Now, the electronic structure of these materials are governed mainly by 3 important parameters. The first one is the on-site electron-electron Coulomb repulsion energy. So when an electron tries to occupy a nickel site, which is already occupied by another electron, so there is an extra energy cost which is given by U due to this electron-electron repulsion. The second important parameter is the charge transfer energy delta. So we have also oxygens in our system. So there is a possibility of charge transfer between the oxygen and nickel atoms. So it is defined as the energy required to transfer an electron from this oxygen band to any empty nickel D state. And finally and lastly, the kinetic energy that is associated with the electrons, and that basically allows the electrons to get delocalized between the oxygen and nickel sites. And this is also linked with the bandwidth of the system. So there is always a strong interaction between this competition between these 3 parameters, and coupled with the structural degrees of freedom, we see many interesting properties in such materials. For example, complex magnetism with high Nil temperatures, metal insulator transition with temperature, and multiferroicity. So I would be basically focusing on properties related to this metal to insulator transition. So first, let us have a look what happens at the metal to insulator transition. So for all the rare earth nickelates, there is a critical temperature above which it is a metal, and below which it becomes insulator. So there is a change in the electronic structure, a gap opens up and it becomes insulating. So in this plot, basically the transition temperature for all the rare earth nickelates have been shown. The x-axis here shows the tolerance factor, and this tolerance factor is directly linked with the size of the rare earth atoms. So when we go from left to right, we see that the tolerance factor value is increasing. That means when we go from LU to PR, the size of the rare earth atom is increasing. And along this curve, each of these points represent each of the rare earth nickelates in the family, and corresponding Y value is basically the transition temperature where this metal to insulator transition happens. And together this red line basically defines the phase boundary between the metallic state and the insulated state in these materials. Now, with this electronic structure change, where we have a gap opening, we also have some structural changes. So what happens is that in the metallic phase, we have identical nickel oxygen octahedras in the system. They have all equal shape and size. But as we enter the insulating state, we have two types of nickel oxygen octahedra. One is larger and one is smaller. Also, this state is referred to as a breathing mode distorted state. And previously in the literature, it has been referred to a charge ordered state because the two nickel atoms inside this small and large nickel oxygen octahedra are having different charge or magnetic moments associated with it. Now, to explain this simultaneous structural change and electronic change, there have been several studies in the literature, and often they do not agree with each other. But one of the important facts that comes out from these previous studies is that the charge transfer energy, especially a negative value of the charge transfer energy, might play an important role in driving the system into a charge ordered state or breathing mode distorted state. So the physical idea is that in these materials, the oxygen and the rare earth atom network is very ionic. And a negative value of charge transfer energy would mean that there are oxygen on the there are holes on the oxygen p band. So there are holes on this oxygen network, and this will destabilize this oxygen rare earth interaction, and which may drive the breathing mode distortion in the system. So to address this question, in our work, we do model ab initio calculations taking NdNiO3 as our system. So the process is to systematically tune this parameter delta, the charge transfer energy, and then look at the effects on the structural distortion in this material. So for this, what we do, we add a constant term in the orbital dependent one electron potential in the LDA plus U formalism, which is shown here. And with adding this term, these terms only acts on the nickel d orbitals, and then we use this constant as a parameter, and we change the value of this constant. We increase the value of this constant in steps. For example, we increase the value from minus 0.5 to 5.5, say, in steps of 0.5. And actually or physically, this means that we are pushing the nickel d states higher and higher in energy with respect to the oxygen p band when we are increasing this value. So this is analogous to increasing the charge transfer energy of our system. So what we do at each of these points, we calculate the electronic structure and we optimize the structure of these materials and see how the breathing mode distortion is getting modified or changed. At the same time, what we calculate the electronic structure and map it onto a tight binding model from where we can extract the orbital energies of the oxygen p and nickel d states. And from those energies, we can calculate the delta, which is defined in this equation. And also, when we take into account the bandwidth associated with the oxygen p band, we can define a new parameter, which is effective charge transfer energy or delta effective, that basically defines a transfer of electron from the edge of this oxygen p band to the empty nickel d states. So this plot basically shows the results from our calculation, and in this plot, the top panel basically shows the nickel oxygen bond length associated with two different nickel atoms in our system as a function of the charge transfer energy. So along x-axis, going from left to right, we are basically increasing the charge transfer energy of our system. So in the top panel, if we see that when our charge transfer energy value is lower initially, so we have two types of nickels in the system and they have two different types of nickel oxygen bond. So this black dot is the nickel oxygen bond length of the nickel, which is inside a small nickel oxygen octahedra. And these are the bond lengths for the nickel inside a larger nickel oxygen octahedra. So we see that initially we have a breathing mode distortion in the system, and this difference between the 2 points basically indicates the degree of breathing mode distortion in the system. Now in the bottom panel, we are showing quite a similar thing. So instead of here showing the nickel oxygen bond length, we are showing the associated nickel moment of the two nickel atoms. So we see that initially they have different magnetic moments, and we can consider this difference as a measure of charge ordering in the system. So we see that for a lower value of charge transfer energy, we have charge ordering or breathing mode distortion in the system. Then when we gradually increase the charge transfer energy, we see that the breathing mode distortion and the charge ordering gradually decreases, and after a certain point it vanishes. So the main conclusion
Sir,
is
you
that,
have 2 minutes for the talk.
okay, yeah, I am almost done. So the main conclusion from here is that there is a certain critical point above which there is no charge ordering, and below which the charge ordering or breathing mode distortion arrives in the system. So the microscopic mechanism that is happening in this region can be understood from this schematic, where above the critical point, the nickel states and the oxygen p bands are well separated in energy, and we do not see any breathing mode distortion in the system. But below the critical point, when the oxygen nickel D states basically tries to enter the oxygen p band, so there is a transfer of charge from the oxygen p band to the nickel D states, and we see occurrence of breathing mode distortion. But and also with, after the breathing mode distortion occurs with a lower value of this charge transfer energy, then it increases as we decrease the value of the charge transfer energy. But at certain point it also stops, so there is a minimum value also of the charge transfer energy, below which the breathing mode distorted state or charge ordered states become unstable. So after this, we calculated the charge transfer energy, the natural charge transfer energy for all the rare earth nickelates, and we see that except for LaNiO3, all the other rare earth nickelates in the family have this charge transfer energy within a very narrow range, and they all have charge ordered ground state. But for LaNiO3, the charge transfer energy is too negative, and we do not see any charge ordered state. It remains in the metallic phase. So this is also in agreement with our phase diagram, where we see that too much negative value of the charge transfer energy do not allow for a breathing mode distorted state. So with this, I would like to end, and I would like to draw the main conclusion of our work, that charge transfer energy is indeed very crucial for this breathing mode distortion or charge ordered state in the system. And this charge ordering or breathing mode distortion occurs at the point when the nickel D states enter the oxygen P band and there are holes on the oxygen network. So with this, I'd like to thank you all for listening.
Thanks, Sagar. Thanks a lot. Is there any question?
Hi, as Anamitra, can I quickly ask the question if there is no other?
Yes.
Okay, so I'm sort of, so I have a couple of points. So you must be aware of this theory by Leon Balance, etc., in the regime of Praseodymium, the point you were trying to look at, which is a theory of the spin density wave riding the charge density wave. And then there are strong coupling theories, which is like saying that, you know, the breathing mode where the octahedra collapses is like a generalized Hang-Rice singlet, where the oxygen and the D form a singlet screening out the nickel. Now in your theory, so all of that theory doesn't require tuning the charge transfer energy. It's for a fixed charge transfer energy. If you change the bandwidth, you get all the physics of the phase diagram. This is also work of partly of Melis, etc.
Yes.
So I was wondering, why are you varying the charge transfer energy? I mean, because at fixed charge transfer energy, just by varying bandwidth, you can explain most of that phase diagram. So I'm just trying to understand your justification of varying delta effective.
Yes. So I mean, if we want to vary the bandwidth of the system, so we have to impose some kind of structural distortion. So that could be a way. But as I told that, the main idea was that when the system has a negative charge transfer energy, there can be holes on the oxygens. So that can be only addressed. I mean, if we want to fix the bandwidth of the system, we do not want to alter it and only want to vary the charge transfer energy and see how the holes on the oxygens vary. And it tries basically the breathing mode distortion. So this is the approach that we took. But that can be obviously a way that varying the structural degrees of freedom and varying the bandwidth of the system, and then check how this changes. But we have not done that.
Okay, thank you.
Okay, thanks. Is there any other question? Yeah, I do not know why the young people are so quiet. People should ask more questions. There is no other question. Thanks, Sagar. Excellent.
Thank you. Thank you very much.
Thanks. And we go to the next talk, which is Manish Kumar.
Yes, sir.
Yeah. Can you start sharing your screen?
Yes, sir.
So Manish Kumar is from IIT Delhi, and his talk is about role of defects in photocatalytic water splitting, monodoped versus codoped strontium titanate. Okay, Manish, you start. So again, I will remind you at 8 minutes.
Okay, sir.
Yeah, thanks. Go ahead.
So, good morning, everyone. I am Manish Kumar, and I am going to talk on role of defects in photocatalytic water splitting, monodoped versus codoped strontium titanate. So, strontium titanate can be used as a photocatalyst for water splitting, since it has suitable conduction and valence band edges that straddle the reduction and oxidation potential of water. It is also chemically stable, non-toxic, and of low cost. However, it has a wide band gap of around 3.2 electron volt, due to which it only absorbs UV radiation that consists only 4% of our solar spectrum. So we have done monodoping and codoping in order to introduce defect state near valence band or conduction band, such that they straddle the reduction and oxidation potential of water, as well as they absorb the visible light of visible spectrum. We have also ensured that the trap state, the defect state should not lie in between the forbidden region, otherwise the recombination rate will be increased. So for this, we have used hybrid density functional theory to calculate the electronic density of states and bandage alignment. We have used ab initio atomistic thermodynamics to predict the stability of the defects. Further, we have used green function approach, that is GW on top of HSEO6 orbitals, to calculate the optical response of the systems. So first, we have determined the stability of the defects by calculating the formation energy of the defect X with charge Q. So this is the total energy of the defected system. This is the total energy of pristine system with neutral charge. Ni are the number of atoms added or removed from the system, and mu I are the corresponding chemical potentials. Q is the charge and mu is the chemical potential of electron, that is the energy required to add an electron to the system or remove an electron from the system to the reservoir. So here we have included the effect of temperature and pressure in the chemical potential term. For example, the chemical potential of oxygen is given by this relation, where this term is due to translational motion, this term is due to rotational motion, and this term due to vibrational motion. M is the spin multiplicity and sigma is the symmetry number. So here is the 3D phase diagram for monodoping of N that reflects the stability of N-doped strontium titanate. So here on x-axis, we have varied chemical potential of oxygen, that is varied from O-rich condition to O-poor condition in accordance with temperature and pressure. On y-axis, we have chemical potential of electron that is referenced from VBM and varied across the forbidden region of the system. The colored regions show the stable compounds that have minimum formation energy. So here we can see that in O-rich condition, N interstitial is more favorable, with negative charge states are stable near CBM, that is in N-type strontium titanate, and positive charge states are stable in P-type strontium titanate. But for a wider range of region, we can see that N substituted at oxygen position is more favorable, with positive charge state stable in this region and minus negative charge states are stable in this region. Further, we have seen the stability of monodoping of Mn. So here we can see that Mn at SR with neutral charge state is stable for the most of the environmental growth conditions, whereas Mn at Ti is only stable in O-rich condition in N-type strontium titanate. And Mn interstitial is stable in O-poor condition with positive charge states in P-type strontium titanate. So from monodoping, we have seen that the substitutional doping is more stable in comparison to interstitial one. So therefore, we have considered only substitutional position for Mn at Ti or Sr and N at O for further discussion. So here we have seen the stability of N-Mn co-doping. So we can see that Mn at Ti, N at O is only stable in O-rich condition in N-type strontium titanate, whereas Mn at Sr, N at O is stable for a wide range of environmental growth condition, that is temperature and pressures. So here the negative charge states are implies that these are act as acceptor in the N-type strontium titanate, whereas positive charge states are reflect the fact that these will act as donor in the system, that is donor in the P-type strontium titanate. So we can see that Mn at Sr, N at O is more stable in comparison to Mn at Ti and N at O in most of the regions. So further, we have plotted the density of states plot to see how the band gap is getting reduced on creating the defect in our system. So here, this is for the pristine system, that is strontium titanate. So oxygen 2p orbitals contribute to valence band maximum, and the titanium 3d orbital contribute to CBM. Further, on introducing nitrogen at oxygen site, what happened? The nitrogen states arise near valence band as well as in the forbidden region, and these states will act as recombination center and enhance the recombination rate. Further, in case of Mn at Sr position, there is no reduction in band gap since Mn states arise inside the valence band and inside the conduction band region. Whereas in case of Mn at Ti, the band gap is getting reduced by lowering down the CBM, and that is conduction band minimum. So in conclusion, monodopants are not much suitable for enhancing the photocatalytic efficiency, either due to the trap states in case of nitrogen, and the lowering of CBM will degrade the reduction power of the system. Whereas in case of co-doping, that is Mn at Sr, N at O, the band gap is reduced by introducing the shallow defect levels here and as well as here. And in case of Mn at Ti, N at O, here again the CBM is lowered and the band gap is getting reduced. But here there are no trap states in between the forbidden region, and the band gap is also reduced. Further, we have determined the optical properties using GW on top of HSCO6 orbitals. So we have calculated the dielectric function. This is the real part of dielectric function, and this is the imaginary part of the dielectric function. So here, this is the pristine dielectric function, and as we doped our system, the real part of the dielectric function is increasing. And in case of imaginary part, here is the peak of the dielectric function for the pristine system, and as we doped our system, the peaks are shifted towards red region. That is, in conclusion, that is the defected system can absorb visible light, and hence the photocatalytic efficiency can be increased. However, only visible light absorption cannot ensure the enhanced photocatalytic efficiency. For that, the conduction band minimum and valence band maximum should be on the appropriate position such that they straddle the reduction and oxidation potential of water. So we have done the bandage alignment. First, we have aligned the bandages of pristine, that is VBM and CBM, with respect to water redox potential. Its CBM lies 0.8 electron volt above the water reduction potential, and the VBM lies 1.25 electron volt below the water oxidation potential. And further, we have aligned the bandages of the defected system with respect to pristine by observing the shift in valence band and shift in conduction band minimum. So in case of N at O, the VBM is elevated. However, there are trap states in the case of N at O substitution. Whereas in case of Mn at Sr, there is no reduction in band gap. In case of Mn at Ti and Mn at Ti, N at O, there is large shift in conduction band minimum, due to which its reducing power is deteriorated. Whereas in case of Mn at Sr, N at O, it has suitable valence band and conduction band edge positions, as well as it has a suitable band gap of around 2.3 electron volt, and there are no trap states are there. So for photocatalytic water splitting, Mn at Sr and N at O is the most desirable candidate. Further, to see the effect on carrier mobility, we have calculated the effective mass for pristine and Mn at Sr, N at O system. So here, this is the band structure for pristine one, and this is for the Mn at Sr, N at O. So in case of pristine, there are bands which are degenerate at the gamma point. So there are, and as we move from gamma to R or gamma to X or gamma to M, the degeneracy is lifted. So we have calculated along the gamma X direction, the band gap is 5.18. And for light electron band, it has 0.38 times ME effective mass. And if we doped our system, that is Mn at SR, N at O, the effective mass will not change drastically. So the effective mass are comparable. And we can see that the effective mass are different in different directions. That implies the anisotropic nature of the effective masses. So in conclusion, carrier mobility will not be affected considerably since the effective mass are comparable. And even if the effective mass is increased, the carrier mobility also depends on the scattering time. So scattering time will be increased as the degeneracy is lifted in case of the defected system. So here are the key conclusions. Nitrogen substituted at oxygen and Mn substituted at Sr are the most stable ones in case of monodoping under equilibrium growth conditions. Mn at Sr, N at O defect configuration is stable than the Mn at Ti, N at O. Monodoping of nitrogen or Mn can induce visual light absorption, but not suitable for photocatalytic water splitting either due to the trap states or the lowering of CBM. In case of Mn at Sr, N at O codoped strontium titanate, it is a potential candidate for producing hydrogen via photocatalytic water splitting since it reduces the band gap to ideal visible region, that is around 2 electron volt. It passivates the localized trap states that is introduced by the nitrogen, and it forms the continuous band with suitable bandage positions. Further, the charge carrier mobility will not be affected much due to shallow defect levels in Mn at Sr, N at O. Finally, I would like to thank my supervisor, Professor Shashwat Bhattacharya, and the group members, IIT Delhi and HPC at IIT Delhi for computing hours, and CSIR for funding. Thank you.
Thanks a lot, Manish, for being on time. So you are from Shastrada's group. I should have guessed it from the slides. The slides are very nice, clean. Your fonts are pretty fancy.
Yes, sir.
Very nice talk. Great, thanks. So is there any question from the audience? So Manish, maybe I'll start. I had a so especially strontium titanate being a polar material, there is a charge transfer between layers and so on. And then you are also concerned with the band gap. So have you tried to benchmark the band gap values with GW calculations? Because GW should be able to take care of the charge screening. So this HC calculation, so this band gap that you get, have you checked with the GW?
So we have checked for the HSC hybrid functional. We have checked that with LDA the band gap is 1.74 electron volt, while with PB it is 1.82 electron volt, and with HSCO6 it is 3.28 electron volt. So, but in case of GW we didn't check that much, but the band gap is getting increased as we use the GW function. It is overestimated by GW. Yeah.
I see. That makes sense.
Yes.
Okay, I don't see any other question. Maybe we are approaching the lunch time. Okay, Manish, thanks a lot for the excellent talk. So we move to the final talk of this session, which will be given by Paramita Datta. So Paramita, are you around? You can you first have to unmute yourself.
Yes. Hello, sir.
Yes.
Am I audible to you now?
I can hear you now, yes. So please start sharing the screen. And so she is from IIT Mandi, and her talk is on understanding the temperature and pressure dependent electronic properties of iron silicon, DFT and DMFT study. Yeah, you go ahead. I will give you again a warning around 8 minutes.
Okay. Okay. Hello, everyone. And first of all, I would like to thank the organizers to give this opportunity to present my recent work. And today I'm going to talk on the understanding the temperature and pressure dependent electronic properties of FESI by using TFT plus DMFT tool. This is the outline of my talk. And first, I'll start with the briefly introduction of strongly correlated electron system, because FESI being one of the members of this system, and this system is for with the electrons partially occupying 3D, 4F, or 5F narrow orbitals, and due to their special confinement in these orbitals, the electrons experience strong Coulomb repulsions, and these system exhibit complex behavior due to the various competing interactions in the Hamiltonian, where the basic one is the competition between tendency of delocalization of electrons and the tendency of localization of electrons, which leads to various exotic physical properties. And these properties are not so easy to understand by using the DFT method, that is this by seeing the embedded as independently. I mean, when the electrons are treated independently. So the most advanced theory has been developed, which is the DMFT, which is dynamical mean field theory. This theory replaces the solid with full of atoms and electrons with one impurity atom, and which is embedded in a bath of electrons. So this approximation captures the dynamics of electrons on an impurity atom as it fluctuates among different atomic configurations with time. So next is the introduction of, I mean, the properties of FESI, which is the system which I'm going to study present here. And here, this is P20 cubic structure. These are the properties, which is non-magnetic, and it has a semiconducting band gap of 50 to 100 milli-electron volt, and it has two peculiar properties. One of it is magnetic susceptibility, and another one is resistivity. So I'll be focusing on the resistivity data mainly. So experimentally, it has shown that it has a sharp drop in resistivity up to 100 Kelvin, while at around 200 Kelvin, it has shown a semiconductor to metal transition, and in the another temperature region, that is 5 to 40 Kelvin, it has shown a variable VRH type of transport, which with localized states in the gap region. So because of these two peculiar properties, it has been under study for decades, and FESI since belongs to the strongly correlated electron systems, and these systems are very sensitive to external properties such as parameters such as temperature, pressure, electronic composition, electric and magnetic field. So I'll be only focusing on the pressure dependent studies, which has been reported recently, and it has reported contradictory results of resistivity and band gap for two different temperature regions on FESI. So first is showing the temperature resistivity data as shown reported by Boyer et al. In 1997. They have shown that with pressure increase, the resistivity keeps increasing, and in the next one, that is 1999, Rachel et al., they have shown that from 100 to 300 Kelvin, the resistivity increases with pressure increase till 9.3 GPa, while at less when temperature is less than 50 Kelvin, the resistivity keeps decreasing with pressure increase. However, both the results, I mean both the works have shown that there's a widening of gap with pressure increase. Next, in 2001, Money et al. Group, they have shown that they have shown the experimental data for resistivity and band gap for two FESI sample, which are nearly stoichiometric. One was FESI deficient sample, one was FE deficient sample, and another was FE excess sample. From in the second plot, we can see that for the FE deficient, the resistivity keeps increasing with the band gap keeps increasing with the pressure increase, while for the FE excess sample, it keeps decreasing. In recently also, Hane et al. Group, they too have shown the similar data where up to 11.2 GPa, the resistivity keeps decreasing when temperature is less than 50 Kelvin. However, from around when the pressure is greater than 14.4 GPa, they have shown that semiconducting to metal transition occurs there. So that means all these data, they have already shown the disparate behavior of resistivity and band gap. So focusing on these two, and which was mainly related to its of stoichiometry of Fe of the structure. So in light of this, we carried out the electronic calculations for both FeSi and another one for the FeX sample, which was where we have taken when Fe was 2% doped at the silicon side. So accordingly, the computational details are Wien2K. We have used three codes, Wien2K, EDMFTF, and Akai KKR codes for all the study. Next is I'm showing the data for stoichiometric FESI, where we have shown that three different methods are showing the volume versus total energy curve, and accordingly we have calculated the lattice constant, which was quite close to the experimental range. And in table 2, we have shown the pressures as calculated for the reduced volume, by which we have intent to see that how pressure is behaving, how the structure is behaving with this volume compression, and we have calculated these pressures, which we will be using to understand the experimental data of FESI. Next is this is the DMFT result for total. This is showing the total density of states. At one is for 100 Kelvin, another is for 300 Kelvin, and again we are showing three volume reduced volumes. One is 6.2 is the experimental structure, where 551 and 507 are the reduced volumes. So to understand the resistivity behavior of FESI for stoichiometric FESI, we'll start it that we have to start it with the simple conductivity expression, and we found that whenever delta n by n is greater than delta tau by tau, this will behave, the material will show semiconducting behavior with temperature rise, and when delta n by delta n is less than delta tau by tau, then that will show the metallic behavior of the material. But if we go with the experimental results of FESI, we have seen that 2.5 to 200 Kelvin FESI seems to be semiconducting. So that means delta sigma by sigma is quite positive, quite large value. So if we goes with this first plot here, the sharp edges, which is for the experimental data, for the experimental volume. So this sharp edges of DOS around EF, this seems to say that delta n by n is very large than delta tau by tau. And whenever the DOS, there will be flattening of DOS, that time delta n by n will be less than delta tau by tau. So using these two parameters, we can understand the behavior at 100 Kelvin for 612 Bohr cube. Again, the sharp edges is there, so it will be insulating. And at 507 volume, 507 Bohr cube, we could see that there is a deep well which is going down with a negligible DOS, and an insulating behavior is to be followed here with the formation of band gap of around 52 millielectron volt. However, at 300 Kelvin, again for 612 Bohr cube, there is a flattened DOS, so this will be less insulating than 100 Kelvin. And at 551 Bohr cube, deepening of the edge starts again with negligible DOS, which continues till 507 Bohr cube. Again, a semiconducting state to be followed here with a band gap of 55 millielectron volt. So we can say that for FESI, for stoichiometric FESI, conductivity will decrease with volume compression, and as the experimental observation of insulating to metal transition, which was firstly around 200 Kelvin, now it will supposed to be shift towards the higher temperature. So next is this other region, which is for the less than 50 Kelvin. We have carried out the KKR calculations, and there we are. This plot is actually showing the total density of states for FESI, for the pure FESI, which is the yellow shaded part, and the other three is for the FEX sample. So in broadly, we could see that in the gapped region, we can see impurity states, and which is somewhat showing the half metallic behavior of this FEX sample, where one channel is from one channel the states are contributing, while the other one is having an energy gap. So if we start from 612 Bohr cube for the FEX sample, we could see that for the red dotted ones, that one channel, the down channel, has an energy gap of 35 millielectron volt, while the other one, up channel, has a has have impurity states around the Fermi level. So accordingly, we can think of that the material has to be metallic. But experimentally, we can see that up to 11.2, the resistivity is still decreasing. That means it is the FeSi is in insulating state. So we can say that these impure states are localized in nature. Next, when we move to 551 Bohr cube, energy gap is now reduced to 18 milli-electron volt in the up channel, while states are now coming from the down channel. But still, we can say again, we can say the resistivity is supposed to decrease if we go with this Hane et al. Work, because here 11.2 up to 11.2 GPa, the resistivity is still decreasing. And for 551 Bohr cube, if we go through with um our table where we have shown the pressures, then we can see that from DMFT 551 is for 551 Bohr cube is around for 6.5 GPa, which is similar to this experimental value. Next, for 50, so that means at 551 Bohr cube the system is still in insulating state. But for 507 Bohr cube, we could see there is no energy gap, and now the states are contributing from both the channels. So we are assuming that now the system will be in metallic, and it is what we could see from the experimental data as well. Because for the experimental data, we have Harney et al. They have shown that whenever pressure is greater than 14.4 GPa, the system is supposed to be metallic. And this is what we can also see, because for 507 Bohr cube, our DMFT result is showing that it is supposed to be 27 GPa, which is quite large than 14.4. So we can assume that this suggests that from 551 to 507 there will be closure of the gap, and because of which there will be transition from semiconducting to metal at around at less than 50 Kelvin. So with volume compression, the closure of energy gap is leading to experimental observation of semiconductor metal transition at less than 50 Kelvin. Moreover, we have also found the magnetic moments at the Fe axis sites, which are decreasing with increasing pressure from 2.4 to 1.2. That means it is showing that at the silicon sites, the properties, I mean, the system is becoming magnetic, which is not the case for the pure FESI. Thus, our KKR CPA calculations suggest that observing different behavior due to the presence and absence of disorder on pressure application seems to depend on the weaker positions of Fe and silicon atoms and the nature of dopant. Because we have also carried out the calculations for when germanium was doped at the silicon site, and they have shown this KKR CPA calculations, they have shown that it is non-magnetic in nature. The strong Hund's coupling is found to be responsible for creation of net magnetic moment at silicon site. And more than that, the DMFT and DFT calculation, they are showing that there will be widening of gap with temperature with pressure, and thus the experimentally observed semiconductor to metal transition will shift towards a higher temperature for FESI. And at this moment we can say that this off stoichiometric is the off stoichiometry in FESI is prerequisite for observing metallization at higher pressure, and both the properties should not be mixed with each other. I mean, whenever there will be off stoichiometry in the FESI, this will behave in a different way than the actual FESI. And finally, the pressures which are calculated from DFT plus DMFT method are quite close to the experimental results. Thank you.
Okay. Thanks, Paramita. Thanks a lot. Is there any question from the audience?
Can I ask a question?
Yes, go ahead. Can you say your name again?
Sorry?
Can you say who is asking the question?
Oh, I'm Sagar, so I just gave the previous talk.
Oh, okay. Yeah, go ahead.
Okay, so my question is that in the temperature dependent DMFT study that you showed, so there the structure remains the same for all? Or
Yes, the structure remains the same.
Okay. And what type of impurity solver you are using for this DMFT study?
For this one, I've used the Monte Carlo impurity solver.
Okay, thank you.
Thanks, Sagar.
Thank you so much.
If there is no other question, I guess we can conclude this session. So I thank Paramita and all other speakers in this session. And then we can conclude.
Thank you so much.
Yeah, thanks. No problem. So is there any announcement or anything from the organizer? And I know that the next session should start at 2, but is
yes,
there...
okay. Tanmay, so first of all, we'd like to thank you for chairing the session. I'll thank you on the behalf of everyone. And we will resume at 2 p.m. Okay. So as usual, the speakers of the next session should join in 10 minutes earlier. Kalpataru will be the session chair, and we'll make them co-hosts so that they can work. Okay. So let's break for now. Thank you.
Yeah. Thank
डन और मैंने 10 मिनट में कर लिया मिनट 1 मिनट लीव करा था मैंने लीव हुआ कि नहीं
Hello.
Hello.
Yeah, I'm Sudipto. So can I just check the presentation once?
Yes. So I need to share the screen.
Yeah.
It says host disabled attendee screening sharing.
Hello.
Yeah. I think you have to click permission.
Hello.
Hello. Can you hear me?
Yeah. So I am the second speaker in this session.
Oh. Yeah. Hello. Yeah. So I cannot share the screen, but it says host disabled.
Just hold on for a second. Hello. Just
Okay.
Who is this? Saurabh, can you just mute yourself? Just mute for a second. Okay, thank you. So Shudipto, can you just, I'll make you a host. Saurabh, I'll come back to you in a second. Shudipto, I'll just make you a co-host.
Okay, I'm here. Pranamito, sorry for the late.
No, that's okay. We still have 10 minutes. That's not a problem. We'll check for a few people. So this is Shudipto. Try to share your screen. You are a co-host now.
So is it visible?
Yes, it's visible. Yeah.
Just a moment. I just.
Yeah, go full screen. Yes.
It's visible, right?
Yes, it's visible. Your cursor is also visible. Yeah, animation is also visible.
Okay.
Okay, so you can unshare your screen so that Saurabh can. Okay, Saurabh. Where are you? Saurabh Ghosh. Okay, I'll make you a co-host. All right, go ahead and try. Shudipto, can you? Thank you. Saurabh, you can unmute yourself.
Is it visible now?
Yeah, it's visible. Go to full screen.
Now?
Yes, it's visible. You want to move your cursor? Let's see if you can see that.
Yes.
Now? Yeah.
We can see the move. Okay.
Okay. Thank you.
Okay, sure. So let's see if the other speakers are here.
Yeah.
So Saurabh, you can unshare your screen for now. Let me just check.
Okay.
Ganesh should start.
How to do not share? I mean.
Okay, I'll do that. Don't worry about it. Okay, Ganesh, you can hear me?
Yes.
Okay, I made you a co-host. Just try to share your screen.
Okay. So is it visible?
Not yet.
Okay.
Okay, so go and practice. Tomorrow set out. Okay, good luck. Ganesh, I cannot see your screen still. Shoot.
Okay.
Now it's visible. Go to full screen.
Yeah. It's going.
Yeah, I see a blank screen. Let's just go up and down your slides.
Okay. I'm already changing the slides. Is it?
Oh, I can't
okay?
see.
No, I cannot see. So, can you just full screen your thing?
Yeah.
Yeah, now I can see it. So again, just try it again. No, so the full screen is not.
I'm with.
In the worst case, you can perhaps do it this way. Maybe you can, click on that little triangle on the side, so that you can at least the right column you can get rid of.
Okay.
No, on the let me see. So if you can follow my mouse, see there. So there is a triangle here. You can see that? There. See you can see my cursor. Right?
I can't see.
So the column, there's a little triangle next to organize, page and redact. There's a little triangle there, you see. You see on the right hand side, there is organize, pages and redact. Click on the triangle there.
Should I stop here? I don't see anything here. Okay.
Do you see the triangle next to your organize pages? Or else, worst case, you can scroll up and down like that because somehow your full screen is not working.
Yeah. Okay.
Okay.
It is visible. I mean, right now it's not full screen.
It's visible. Okay. I mean, Kalpataru, maybe.
Yeah, I can see it. Yeah.
Yeah. Okay. So I think you can use it in this mode. Okay.
Okay.
So who else is left? Shiv Prasad Shastri. Shiv Prasad. I don't see. So Shiv Prasad Shastri, the last speaker, hasn't yet shown up. I don't know, this person, Sani, or I don't know who he is, he or she, I don't know. Okay, if I see the fourth person come in, then I'll make him or her him a co-host. So Kalpataru, how is the COVID situation there?
It's all normal now. There's nothing COVID situation anymore. Means there COVID means positive rate is almost like 2,000-3,000, but still nobody cares about it now. It's almost end of the year. Everyone is in festival.
Oh, I see.
So do you go out of the campus sometime?
No, we go. I mean, not to the city. I have gone to the city only once. But other than that, generally, we stay in Jatni. We go out of campus, but not beyond the station. Campus has.
It's almost in Odisha. It's almost controlled. That's what the numbers say.
It's mostly controlled. But campus now has 3 or 4 students who came back have turned positive. So we have an on-campus COVID quarantine center. So
that's guest house A1, A1, A2.
So they are there. So at least that way people don't have to go to a government facility.
No, in IIT Madras, there are like one day 100 people.
Yeah, Shantanu was mentioning that. Yeah, it's
there was a big news everywhere.
So this Shiv Prasad Shastri, let me check if he checked this thing yesterday with us. No, the Shiv Prasad Shastri was a student, the last speaker in your this thing.
Didn't check yesterday also.
Didn't check yesterday, so I don't know. He's not here. If that doesn't happen, we'll have a slightly longer break and then. Yeah.
Hi, Kalpataru. Hello.
Yeah, hello.
Yeah. Yeah, hi, how are you?
Yeah, I'm good. How are you?
Yeah, fine. Just going on.
Yeah.
Hey, just one. Yeah. Tell me.
Nice to see you. See you and Swabab also.
Hi, Kalpataru. How are you?
Yeah. Chal raha hai.
Last year it was good, right?
Yeah, yeah. This time nicer is also very good, but
yeah, the point is that
nicer. Yesterday I was telling my wife by this time I would have been nicer and enjoying some fresh air there.
Seems those good days are gone actually, where we can physically meet in the conferences, right?
No, next year. By next year, everything will be okay. Or everybody will think that everything is okay. I don't know.
So will you give an alert 5 minutes before the end of the talk or something?
Yeah, it's 25 minutes. So, so you'll have 22 minutes to speak. So I'll give you, depend upon you, 20 or 18 minutes.
Okay, 18 minutes will be fine.
Yeah.
Okay, should we start? It's 2.
Yes, it's already. Can we wait for 1 or 2 minutes, maybe?
Let's wait because anyway,
Prasad is not there.
Yeah.
But maybe 1 or 2 minutes.
Yeah, maybe wait. Some people might come from lunch quickly.
Yeah. Okay, so if you maybe you have to make me co-host, because if you mute everybody,
Yeah, I'm sorry, I didn't make you co-host. Sorry.
Because everybody mute me, then I cannot tell them their time, exact time. Yeah. Okay.
No, sorry.
What is it? One talk. Now you find out. Where? Now? Hey, now I logged out. Can you check? Hey, can you check now? I logged out.
Anamita, maybe can I start now?
I was muted. I had muted myself. So okay, welcome back. Let's start the afternoon session. This session has 4 talks, and Kalpataru Pradhan has kindly agreed to chair the session. So I'll turn the session over to Kalpataru now. Okay.
Okay. Welcome back to the 3rd session of this conference of first day. So now we have 4 speakers. So 2 are the invited talk and 2 are contributed talk. So first speaker is Saurabh Ghosh from SRM Institute from Chennai. So he will speak about multifabrics and polar materials out of 2D material, means designed out of 2D materials. So Saurabh.
Thank you. Let me share my screen.
Yeah, so we have to share this.
Okay, so I think I'm visible.
Yeah, so we have to make it full screen now.
Yeah. Is it okay?
Yeah, it's all good.
Okay, thank you. Thank you, Kalpataru and other organizers for inviting me. So last time it is in 2018 in Kolkata, and so I visited there, and then it always gives me an option to go to your hometown. So I born and brought up in Kolkata. So, but this time we are in a pandemic situation and doing it online. But it's worth that we are meeting. So with that, I just want to again thank the organizers to give me an opportunity to present my recent research work here. So my title of my talk is Designing Layered Two-Dimensional Van der Waals Multiferroics and Polar Metal. So first I will start with the general conception of ferroelectricity. So barium titanate is one of the classic example where you have in the high symmetry you have a cubic structure, and then barium is at the corner of the cube, and you have a titanium at the center surrounded by oxygen and ions, and then you have a BO6 octahedra, and then this titanium is in +4 charge state, and plus 4 charge state means D0, and that D0 is responsible for this ferroelectricity in this barium titanate. So this titanium and titanium D and oxygen P orbitals, they want to satisfy the bonding environment. So in the search for bonding, this titanium goes off-centered, and then you have a ferroelectric distortion. So this titanium can move upward with respect to the in-plane oxygen atoms, and then also it can go down with respect to the in-plane oxygen atoms. So in that way, you have two different kind of polarization. You have polarization up and polarization down, and the structure goes from a cubic symmetry to a tetragonal, symmetry, tetrahedral symmetry. So you have here in cubic, you have A equals to B equals to C, but in this case, your A equals to B, but your C lattice parameter is not equal to A and B. So this is a classic example of a ferroelectric material. And then if you freeze in, suppose this is a particular phonon mode. Now, if you freeze in that particular phonon mode and you try to slowly change the magnitude of that particular phonon mode, then your energy is going to lower because you have a phase transition from high symmetry cubic to tetrahedral structure. And now you can have two different kind of minima. So one minima and another where you have polarization in upwards, and another minima where you have a polarization downward. So this is a classical example of barium titanate with a double well variation of energy with respect to titanium displacement. And if you can apply electric field, if you switch the direction of the electric field, then you can have either this side of the direction of the distortion or either this side of the distortion. So you have a double well in variation of polarization also with respect to the electric field. So this is a very simple example of barium titanate, and this is called proper ferroelectric material. Now, so far till 2020, what we know about this ferroelectricity, so ferroelectricity can have three different types: proper, improper, and hybrid improper ferroelectricity. So proper means where a single mode is responsible for driving the phase transition, and also it is responsible for the origin of ferroelectricity in the material. But in case of improper ferroelectrics, there's some other mode is basically the driving force for the phase transition, and the polar mode couples with that mode and give you ferroelectricity in the system. The hybrid improper ferroelectricity is a different one, where you have these two modes, they couple with each other, and there's a trilinear coupling between in the land of free energy, and then you have a phase transition, and here you have both the modes are order parameters. But here they have only one order parameter, which is that the displacement of this titanium off-centering with respect to the oxygen in-plane oxygen atoms. Now this is a double well. Now recently it has been observed in a recent Nature paper in 2020 by Sok, Pantelis, and John. So where they have figured it out that this double well is not the only one. You can have a quadruple well kind of energy variation with respect to the ferroelectric distortion. So here in the y-axis you have a total energy, in the x-axis you have a ferroelectric distortion, and you can see a clearly double well. But here you can see there's a multi-well. So you have two local minimas, and that's their defining is that quadrupole. This is a theory come experimental paper, and where they have both in terms of theory and experiment, they have proved that for this particular material, copper indium P2O, PTS6, there is van der Waals layer materials, and you can have two different kind of polarization states. One is this high polarization states, and one is low polarization state. I am audible, right?
Yeah, you're audible.
Okay, right. So there are two different kind of. So now, so what's really happening? What is the origin of this kind of quadruple ferroelectricity that has been observed very recently? So all of you may know that this is the 100 years of ferroelectricity when it started with the Rocher assault 2100 years ago. So this is exactly the 100 year of ferroelectricity, and after 100 year of ferroelectricity, it has been discovered that this double well is not the only possible variation of the total energy with respect to the polar mode, but you can have a multiple, quadruple structure as well. So I'm going to discuss what is the origin of that. So now, then another, my title contains polar metal as well. So now Now this barium titanate is insulated material, and now the question is that can you have this kind of distortions, the ferritic distortions? It may be proper, improper, or hybrid. Can this type of ferritic distortion survive or persist in a metal? So what's going to happen? So you know that if you have a finite polarization, then free electrons will screen that finite polarization, and you cannot have control of the polarizations in a metal. If I apply electric field, you can control them. But fundamentally, there is no reason that you should not have a polar distortion in a metal. So I would like to say that if barium titanate is metal, then also you could have this same kind of polarization, same kind of distortion. The problem is that you cannot control them, and it has been studied. The study has been made that by electron doping in barium titanate, you can regain this particular double well. So that the question is that so the polar metal is what we mean about that. Still, the definition of polar metal is not clear. Still, now what you understood about polar metal is that so we can have this kind of polar distortion in the metal, and the debates are going on how to control them. And this all started in this particular paper in 2014, where they have experimentally have shown that in lithium osmate, in lithium OSO3, this particular material can have intrinsic ferritic distortion in a metallic system. Later, there are later different studies. I also studied during my postdoc. I worked some of the materials on polar metals. So here you can see we have shown that in case of lanthanum LSMO LNO superlattice, that is LSMO lanthanum nickelate and strontium doped lanthanum manganite superlattices, you can have this kind of ferroelectric double well distortion, and what we have found that the system remains metallic. So this ferroelectric like behavior can really persist in a metal, and then the next question is how to control them. So here we have proposed a mechanism that is intermixing can open a gap into the system, and you can basically have the finite polarization. You can measure the finite polarization. The only problem with the polar metals is that we cannot measure the polarization by any method. There is no method available till now that you can measure the finite polarization in a polar metal. So this is the introductory slides about this double well, quadruple well, and what I really mean about ferroelectric-like mode and in a metal. Now I'm going to talk about this designing ferroelectric materials and polar metals in 2D in two-dimensional van der Waals materials, and the methodology I'm going to adopt is density functional theory, and I also show some results of finite temperature molecular dynamics simulations, and also some results will be based on NED calculations. So with that, so let me start the results, showing my results. So here I have listed, there's a complete circle that first we discuss the material copper chromium P2S6. This is a very well-known studied material in case of transition metal, in case of TMPC, it is a very well-studied material. So now here I have listed the first. You can start with the non-polar material, non-polar structure, where you have these red ones here is copper atoms, and these green ones are the chromium one. Okay, so copper in +1 with the D0, and copper is +3 with D3. Now this is non-polar material, and then if there are two modes which then goes to a ferroelectric and antiferroelectric kind of arrangements. So here gamma 1 plus mode is a ferroelectric, is antiferroelectric mode, and gamma 2 minus mode is a ferroelectric mode. So if you add this gamma 2 mode in non-polar, then it leads to a phase transition, and this leads to a ferroelectric structure. And your ferroelectric structure, you can see these both copper atoms, they moved from the center to the edge of the layer. So you have a layer, 2D layer. You have a van der Waals material, you have two different layers, and these copper atoms from the center, they moved at the edge of the layer. Similarly, if you keep increasing, keep adding this particular gamma 2 minus mode, that is you are adding the polar mode, then this copper atom leads to in the gap between two van der Waals. So that we define as van der Waals ferroelectric. That means this now copper atom has crossed the edge of the layer, and now it is in the van der Waals gap. And now if you keep increasing, the magnitude of the gamma 2 minus mode, then you can end up with a structure which is called mid van der Waals ferroelectrics. That means now your copper atoms at the middle of these two layers. So first you have a nonpolar, then you have a ferroelectric material where copper goes at the edge of the two layers. Then you have another structure where there is just the copper atom just crossed the edge. It is called the van der Waals, and here you have a mid van der Waals. Similarly, you can add this particular antiferroelectric mode where this copper atom goes up, these copper atoms go down, and then again you can add the second phase. You can keep increasing the antiferroelectric mode, and then again you can lead to the mid van der Waals ferroelectric. So you can lead to mid van der Waals ferroelectric from a nonpolar state in the two different ways. Now there are two different kind of antiferroelectric orderings are possible here. So one is called inter-antiferroelectric. That is in a layer. Here green is a copper. So here the coppers in a layer they are antiferroelectric. But here they are antiferroelectric. In a layer they are ferroelectric. But these two ferroelectric layers are coupled antiferroelectrically. So it's called inter-antiferroelectric. And you can have another structure which we discovered in this paper, that's inter-antiferroelectric. That is, in here, this is antiferroelectric. This is also antiferroelectric, but they couple in opposite way. So it's called inter-antiferroelectric. Now, so then we studied this different stability of the different ferroelectric and antiferroelectric phases and different kind of materials. So here we first present the results of copper Cu Cr P2O6. So you can see this is nonpolar structures, and we calculate this is the energy barriers. We calculated these energy barriers by using NEB calculations, and you can found that this is a ferroelectric one. This is a van der Waals mid van der Waals ferroelectric, and you can see from this energy landscape that van der Waals ferroelectric structure is more stable compared to the nonpolar and ferroelectric structure. So van der Waals ferroelectrics means this structure. This is a van der Waals ferroelectric structure. This structure is more stable, and it is also known in the literature, and we calculate the polarization. And then we have calculated also the antiferroelectric case. So in case of antiferroelectric, we discovered two new kind of van der Waals antiferroelectric phase, and you can found that this van der Waals antiferroelectric phase is not that stable, but this antiferroelectric state is stable in case of copper chromium P2O6. Now, then this system is particularly insulating. Now, what we have done, so here I would like to mention that, so here this copper is in +1 state, and then chromium is +3, D3. Now we have replaced this copper by nickel. And after calculations of optimizing the geometry, we have found that this nickel becomes nickel remains +1, and chromium remains 3+. So from the electronic structure, it also is reflected here. And for this particular material, nickel chromium P2O6, this are the predictions. These materials haven't made yet. So this nickel chromium P2O6, we have found that this van der Waals ferroelectrics, there is no stable ferroelectric state. So ferroelectric state is unstable. There is a maximum here. There is no minima, and there is a van der Waals states are stable. But nonpolar structure is more energetically stable, and you need to have a energy barrier to cross it from nonpolar state to van der Waals ferroelectric state. But the van der Waals state is stable. So when you can overcome the barrier by thermal energy, by electric field, once we have overcome this barrier, then this is a very stable state. And this particular material, nickel copper P2O6, can be stable in van der Waals ferroelectric, in between van der Waals ferroelectric gap. Now, then we extend our study. We replace this copper now by manganese. And we have very interesting result here, that we have found that now in this situation, nickel chromium P2O6, PTS6, nickel is +1. Now nickel becomes +2, and manganese become +2. So both are at the same charge oxidation state, and manganese becomes D5, and nickel becomes 3D8. Now this 3D8 and 3D8 manganese with the 3D5 configuration, and nickel with the 3D8 configuration, the system has to be insulating. And for the nonpolar structure, really we do find an insulating system. However, when you add the polar mode, the ferroelectric mode, and we change the magnitude of the polar mode, we found a metal to insulator transition. And you can see from this particular graph, this is the nonpolar structures, both in the van der Waals ferroelectric and in mid-van der Waals ferroelectrics, there is a metal to insulator to metal transition. And that is because of the hybridization of, you can see from the density of states, this is sulfur and manganese hybridization is basically driving this particular phase transition from insulator to metal. And here we have listed out the band gap, how the band gap is varies with the nickel displacement, that is with the polar displacement. So you can see the band gap reduces at a particular magnitude of the polar distortion, and then it remains fat. And now it is the polarization we have calculated. The polarization keep increases and it gets saturated. And this is the metallic region, and here we cannot calculate the polarization. So in case of nickel manganese P2O6, we predict that there should be a metal to insulator transition driving by the polar distortion. And when it crosses the polar region, you can define it as a polar metal. Now then we have calculated the different stability between different van der Waals and mid van der Waals ferroelectrics in case of nickel manganese P2O6, and we have found that here again the ferroelectric mode is not stable at all. However, van der Waals ferroelectric and mid van der Waals ferroelectrics, they are both stable, and mid van der Waals ferroelectrics is more stable compared to the van der Waals ferroelectric. But the switching barrier between this is very small. The switching barrier between nonpolar and van der Waals ferroelectrics is huge, is very large. So you need to have a thermal energy or some kind of electric field to switch them. But once you switch, then these two are very stable state. And not only that, you can tune the electric field to make a switch between these two, that is van der Waals ferroelectric and mid van der Waals ferroelectrics. Now, what we have also studied the stability of these particular materials with respect to the temperature. So we had the finite temperature molecular dynamic simulations. So this is, I took copper chromium P2O6, which is a van der Waals ferroelectric material. And then what we have found that when you we use 100 Kelvin in your simulation, what you have found that quickly this is the line. So this is basically the nonpolar structure. And when you have a ferroelectricity, these two, you can see this is copper, and this is copper 1, and this is copper 2. So initially, this orange and green, they are in the same layer, same position. They're in the nonpolar state. But now it becomes up and it goes down. So they have achieved a ferroelectric state at 300 Kelvin. Now, if you keep increasing the temperature to 300 Kelvin, we have observed a very interesting result. That you can see that at a particular time step, this is 300 Kelvin. So remember that 300 Kelvin. The C2 chromium copper chromium P2O6 has already achieved stable ferroelectric state, but here there is a crossover at this particular temperature, this particular time step. You can see the orange goes down and the green goes up. So what's happening here is basically this is the first step before switching F1. So in F1, you have this copper, and this is copper, this is another copper, this is another copper. So they are intra-antiferroelectric. They are intra-antiferroelectric. Now, during the switching, this copper goes down at this position, and then after switching, what happens? This green ball goes up, and there's a sliding between these two particular layers due to the thermal activation, and that basically gives you a switching from a interferoelectric to an intraferroelectric. So we have observed this switching at 100 degree Kelvin. Now, if you keep increasing the temperature.
So you have all total 5 minutes. So you can speak another 2-3 minutes. Huh?
Okay, 2 minutes. Okay. So now, if you increase the temperature, then if you can increase the temperature, then you can see that these switchings are happening more often at 600 Kelvin. So we have also studied this switching barrier for nickel chromium P2O6. We can found that when you at 300 degree Kelvin, this mid van der Waals ferroelectric states in case of nickel chromium P2O6 is very stable, and in case of nickel manganese P2O6, this mid van der Waals ferroelectric state is more stable compared to the others, and it also matches with our NEB calculations. So with that, I want to conclude that we have identified two different kind of modes which are responsible for driving ferroelectricity and antiferroelectricity in this kind of ABP to S6 materials, and we have found that that in case of NCPS, that ferroelectric state is unstable. However, van der Waals ferroelectric state is stable and insulating phase with a finite polarization. In case of NMPS, we show an insulating to metal transition, and it leads to a polar metallic phase. In all the above system, we found a strong coupling between polarization and magnetic anisotropy direction, which is an important phenomena for multiferroic material. So with that, I want to acknowledge my funding, ACRB, co-research grant. I have a US Department of Energy, US consultancy. And then also I acknowledge SLM supercomputing facility and NARSC, University of California, Berkeley, LBNL for providing computing facility. And this work has been done by my PhD student, MJ Saminathan. Thank you for your attention.
Okay, thank you, Saurabh. So now this session is open for questions. So please ask your questions, please.
Hello, yeah.
Yeah. So, Saurabh, this is intra ferroelectric kind of thing you told in the second or third slide.
Yes. Yeah.
Yes. Okay, so if you apply electric field or something, how do they behave? How do they respond or something kind of thing? It is very complicated.
So this thermal, we have done the thermal stability, the thermal due to the thermal effect. This is happening. But if you can use electric field to switch between different states, and the magnitude of the electric field that you have to apply depends upon the switching barriers, depending on the barriers that you have found from NAB. Yeah. So you can electric field, but in principle, by you can apply electric field, you can switch them.
Okay. 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 Thank you. So if there are no more questions, let's thank Saurabh.
Thank you.
So thank you. Now, Sudipta, can you share your screen?
Is it visible?
Yeah, it's visual. Yeah, so we can. So next speaker is Sudipta Datta from Isaac Tivipati. So he'll speak about hetero bilayers, strain effect of strain on hetero bilayers. So Sudipta, please.
So first of all, I would like to thank the organizers for giving me this opportunity to present my research work here. And it is good to see that the previous talk by Saurabh is a kind of complementary to this one. He has discussed about the electrical polarization in the van der Waals bilayers. And here I am going to talk about the magnetic polarizations for the van der Waals hetero bilayers. Okay. So the full story about this 2D van der Waals 2D materials actually that started with graphene. Okay, and we all know this the Scotch tape method of peeling off this graphene and all these things. And generally, the two-dimensional the graphite, it shows the diamagnetic behavior as I have shown in this particular video. And there have been many trials to get the magnetism in the graphene or the two-dimensional the bulk graphite also. And there have been two driving force behind that. One is from the pure application point of view, where we can have spintronic materials and we can have the memory storage and the spin current observation in such kind of things. And another is from the purely fundamental curiosity for the low dimensional magnetism. So I'll particularly elaborate on the second part, which is purely fundamental curiosity, and we'll see that why this kind of curiosity is actually genuine in 2 dimension. Okay. So before going into that, actually, first I would like to discuss briefly about the 2-dimensional graphene to set up the tone of this presentation. So basically the magnetism of the 2-dimensional graphene that arises from the very unique characteristic of the graphene, which is called the bipoidite lattice. Okay, here I am showing this honeycomb lattice of 2-dimensional graphene with its rhombus unit cell containing A and B to different kind of sublattice points. Okay, and the nature of the bipoidite lattice is that if the A and sublattice point actually prefers to localize the upspins, the B sublattice prefers to localize a downspin. So it is a no-brainer when I do not have any defect or vacancy. I have same number of A and B sublattice points, and I should not have any net magnetization in the particular two-dimensional graphene. And that is what we see actually, the characteristic of bipartite lattice when Na equal to Nb. These are the number of the A and the B sublattice points. When they are equal, I have the zero net magnetization. Okay. Now, to get the magnetism actually, then we need to break this bipartite symmetry in two-dimensional graphene, and there can be three proposals to do so. One is to create imbalance between this Na and Nb, and the resultant magnetic moment will be half into Na minus Nb. Another way to get the magnetism is a finite termination and creating the ribbon kind of structure where you will have the edges, and because of this finiteness in one particular direction, one can have actually magnetism also, because that also breaks the bipartite symmetry. Another thing is that once you have the non-6-membered rings, which is only possible when we have the CPT grown graphene and the grain boundaries are meeting to each other, actually two different grain boundaries. They are meeting without any crystallographic orientation, and there we will have the possibility of non-6-membered ring formation. And we'll see that how the sublattice, lack of the sublattice clarity can give rise to magnetism in such case. Okay. Now, as I told actually, so in case of a graphene system, once we have the the vacancies in the system, we can have the localization of the spins and the resultant magnetism. Or else once we have the edges actually, then also we can have the localization of the spins, as you can see in this schematic diagram. And this has also been experimentally confirmed, where you can see here is a zigzag edge graphene nanoribbon, and the scanning tunneling spectroscopy measurement shows this kind of splitting of the edge states at the Fermi energy. Okay, which can be modeled very nicely within the mean-field Hubbard Hamiltonian. And we can see within the mean-field Hubbard Hamiltonian with a very small on-site Coulomb correlation, we can have the splitting of the density of states at Fermi energy, and that will create one gap just resembling the experimental observation. But when we have this on-site Coulomb correlation, graphene actually, the graphene nanoribbon, zigzag edge, that actually stabilizes in this kind of ground state. Where in the single edge, you have the ferromagnetic alignment of the spins, but since both the edges are from the two different sublattice points A and B, the other edge is actually showing opposite spin orientation. So overall, you get the net zero magnetization. Okay. And the third one is actually, there is a non-6-membered ring formation. As you can see in the first figure, I have these hexagonal rings actually, this honeycomb structure, and nicely I can number this A and A, B alternatively, where each A is surrounded by 3 Bs and each B is surrounded by 3 A type of sublattice, and overall the net magnetism will be 0. Okay, but the moment I have this kind of defects where I do not have the 6-membered ring, and this particular defect is a very well-known defect called the Stone-Wells defect. And now you can see, now if I want to number this A and B alternatively, I cannot do for these two particular atoms. Okay, so if I put here A or B, that is a conflict with these two, and the same case is also here. So now the question is that these two atoms, they belong to whether A or the B sublattice points, and this particular sublattice clarity also can lead to the magnetism. And as you can see here, I am just showing here two different kind of grain boundaries, where the localization of the spins because of the sublattice clarity also give rise to finite net magnetization, as these values are shown here. Okay, so this is a story for the two-dimensional graphene. And another way of inducing the magnetism in graphene is actually the proximity effect, where we can put the graphene on top of this yttrium iron garnet, okay, which is a magnetic one. And because of the presence of this one, it induces magnetism in the graphene, which can be actually confirmed from the very low magnetic field quantum Hall effect and also the spin current in the lateral graphene spin bulb. Okay, now what we have seen so far that such kind of magnetism can be observed in two-dimensional material by defect engineering, doping, or in terms of the add atoms or the magnetic impurities or external perturbations, as we have seen in case of the proximity effect. Okay, the question here actually we want to ask that, can we have a pure 2D material without any this kind of external perturbation or disturbing the system, and the system will show me the inherent magnetic property? But it seems there is a roadblock. Okay, and that roadblock is a Marmin-Wagner theorem. What it shows actually, I am showing here a two-dimensional monolayer Magnon density of states as a function of the energy. And the Magnons are nothing but the quasi-particle for the spin wave excitation. Okay, and as you can see from this figure, we do not have any spin wave excitation gap actually at the zero energy. And because of that, the Bose-Einstein distribution that actually diverges at the zero energy. Okay, And because of the divergence at any non-zero temperature can create a massive Magnon excitation. Okay, and because of that, the long-range spin ordering will be collapsed in the system, and one cannot have any kind of long-range ordering in the 2 dimension. Okay, now it actually tells me that, okay, so there is at finite temperature we cannot have any kind of ferromagnetism in the 2D material. Okay, the question is that, is there any way out? It seems that there is a way out. There is a way out. What is that? We can have the uniaxial magnetic anisotropy in the system. And what do I mean by uniaxial magnetic anisotropy? I'm just showing here the schematic representation of square lattice system, and the spins, as you can see, they are oriented either in the X or Y or in the Z direction. Okay, the moment I incorporate this kind of uniaxial magnetic anisotropy, that means the spins are having a particular directional orientation preference. In that case, I have this kind of monolayer or the multilayer Magnon density of states. Anyway, 3D is not at all any problem, where I can have anyway the non-zero spin-wave excitation gap. But in presence of the uniaxial magnetic anisotropy, now I can have the non-zero spin-wave excitation gap for the monolayer or the multilayer 2D system also. Okay, and because of that, now that non-zero spin-wave excitation gap can resist the thermal agitation, and one can have long-range spin ordering. So in presence of the uniaxial magnetic anisotropy, one can have ferromagnetism in 2D below the Curie temperature. Okay, and very recently this has been actually observed experimentally in quite a few transition metal systems. And today I'll be discussing about 2 different classes of the system. One is the chromium halide system. Okay, so this is the bulk structure, and this is the monolayer top view. Okay, and as you can see, these blue chromium atoms, they form these hexagonal rings, just like the graphene case. Okay, and this particular system shows the Ising type ferromagnetism, where the spins are actually perpendicularly or perpendicular to the plane. The spins are aligned and it's out of the screen actually, so out of the direction of the screen. Okay, so this is Ising type ferromagnet, 2D ferromagnet. Another is this kind of transition metal trichalcogenide, okay, where I have this chromium GeTe3, okay, and the G is the group 4 element. I'll come to this point later. And this is the bulk structure, and this is the monolayer 2-dimensional structure with the same kind of structure. And in both these systems, actually, we have the edge sharing octahedrous. Okay, now the magnetic property of this transition metal trichalcogenide is quite different as compared to this one. What it shows is soft Heisenberg type ferromagnet. That means the spins are actually aligned. There is no alignment of the spins, okay, randomly oriented, but in presence of very small magnetic field, you can actually align the spins in a particular direction, and you can have the 2-dimensional ferromagnetism. Okay, now the question is that how to characterize such kind of things. So here is a magneto-optic Carr effect. So what it does actually, if you shine one polarized light actually on the magnetic material, so because of this electromagnetic radiation interaction with the magnetic material, there is a rotation of this polarization angle. Okay, and that rotation is quantified by this theta k, which is called the Carr rotation. So whenever I have non-zero theta k, that is non-zero Carr rotation, that system must be a magnetic material. If I do not have, that system might not be a magnetic material. Okay, so just to Carr rotation is one measurement to quantify whether the system is magnetic or non-magnetic. Okay, now as I told that CRI3, which is the Ising type ferromagnet with the out of plane spin orientation, and the spin moments per chromium atom is around 3/2. Okay, this particular system, if I see the monolayer, this is experimental result. If I see the monolayer, the Carr rotation shows this kind of hysteresis loop, where H is yellow and the green color H is just the 2 directions of the increasing and the decreasing direction of the applied magnetic field. Okay, now what we can see, the monolayer shows the Curie temperature of 45 K, and if I do the same thing for the bulk, it shows the Curie temperature of 61 K. So one can notice, if I go from monolayer to bilayer to trilayer to bulk, actually there is not much increase in the Curie temperature, and it indeed shows that the interlayer coupling must be very, very small. Okay, now there is something very interesting happens in schema bilayer, which is very relevant in this particular talk. Okay, here I show the Carr rotation for the 1 layer, 2 layer, and the 3 layer system. As you can see, 1 layer and 3 layer, they show this magnetic hysteresis kind of nature. Okay, but the bilayer, it doesn't show this magnetic hysteresis over a large magnetic field. Okay, we know that the monolayer must be a ferromagnetic, right? 2-dimensional ferromagnet. So what happens in this particular region, since I have the bilayer system, both the layers, although intralayer ferromagnetic is actually robust, but interlayer, they have the antiferromagnetic coupling and the net magnetization is 0. So that is what is actually reflected by the 0 Carr rotation. Okay. Now, if I apply the magnetic field around 0.6 Tesla, there is a ferromagnetic saturation happening over a very small, period of this magnetic field of 100 millitesla. It's a very sharp increase. Okay. And if I see the phase diagram of this bilayer system as a function of temperature and the magnetic field, I can see the below the Curie temperature, which is this dotted line actually. I can see with increasing the temperature, this particular critical magnetic field for the antiferromagnetic to ferromagnetic transition, that does not change. Okay, so this is purely by application of the magnetic field, one can achieve this kind of phase transition, which is called the metamagnetic phase transition. Okay, such metamagnetic phase transition not only characteristic of just the magnetic field, one can achieve that one in terms of the electric field also. Suppose in this particular case, I show here, in absence of the perpendicular electric field, you have the anti-parallel alignment of the spins in the two layers. But once I apply the perpendicular magnetic field, both the layers are actually ferromagnetically coupled, and this is the experimental evidence of that. At zero external electric field, perpendicular electric field, you have no magnetization, that means zero car rotation. Okay, but at any finite applied electric field, actually, one can have this hysteresis loop. That means you have the ferromagnetism appearing. Okay, so what is actually happening whenever I apply the electric field or the magnetic field, that basically breaks the inversion symmetry between these two layers. Okay, and because of that, we can see because of this broken inversion symmetry, we can have the metamagnetic phase transition from antiferromagnetic to the ferromagnetic, and that is very nicely explained in this theory paper. Okay, now what very recently has been observed, this particular metamagnetic phase transition is not only the characteristic of the bilayer system. If I have a bulk system also, near the surface layers, actually the layers are antiferromagnetically coupled with each other. Okay, but in the deep in the bulk, they are ferromagnetically coupled. And once you apply the magnetic field, perpendicular magnetic field, at around 2 Tesla, actually one can have full ferromagnetic alignment. Okay, so it seems that the metamagnetic phase transition is actually arising from the surface layers, not exactly from the bilayers also. Okay, this is a very recent result. Now, this is a second type of, so what exactly I want to focus here, there's a metamagnetic phase transition, which has been very well understood and kind of well established fact in this kind of CRI3. Okay, so this is the second type of magnetic material, which is transition metal trichalcogenate. Here I show the monolayer system. And as you can see here, with increasing the magnetic field, here I show the car rotation as a function of the magnetic field. Once I increase the magnetic field, the ferromagnetic saturation is achieved actually around 0.6 Tesla. And one can see the non-vanishing remnants also very near to the zero magnetic field, which actually shows again the very soft Heisenberg type ferromagnet. Once you have to apply very small magnetic field to get the ferromagnetism in this system. Okay. Now, if I show a different layers of this particular transition metal trichalcogenide. Okay, here I show from bilayer, trilayer, tetralayer, and the 5-layer to the bulk. Okay, just to mention that monolayer has not been achieved so far experimentally. Okay, so here in these plots, what you can see actually that the TC that actually changes with increasing the number of layers. And here I show the experimental and theoretical result for the TC as a function of the number of layers. And as you can see, with increasing the number of layers, the TC increases. Okay. Now for the bilayer, the experimental TC is 30K, whereas for the bulk, the experimental TC is 68K, which actually reflects very strong interlayer coupling. There is another evidence of the strong interlayer coupling. That is, if I apply the magnetic field, also I can increase the TC. So this blue and the red ones are for the, so blue one is for the higher magnetic field, red one is for the lower magnetic field, perpendicular magnetic field. And as you can see in all the plots actually, the blue one shows higher TC value. So why it is so, once I apply the magnetic field, I am increasing the uniaxial magnetic anisotropy, and that in turn actually increases the Curie temperature also. Okay, this again shows the strong interlayer coupling in this kind of transition metal trichalcogenide. So what I asked one question here, is there any other possibility, is there any other way actually to tune this TC in this kind of system? So what we had taken, so this is again the same system, this transition metal trichalcogenide, but I have given a CR XT3, X is the group 4 element, and instead of considering only the G, I have changed the group 4 element from the carbon, silicon, germanium, and tin. Okay, and here this is a super exchange path. And as you can see, these are the two chromium atoms. They are connected through this tellurium atom, and the super exchange angle is from the chromium, tellurium, chromium, this one. And these tellurium atoms are also attached to the side groups like these group 4 elements, this X, this blue one. Okay, now what happens actually, if I go down in the periodic table in the group 4, from carbon to silicon to germanium to tin, basically what happens, the atomic radius increases. And when the atomic radius increases, this D also increases. And increase in D actually increases the super exchange angle theta. And here I have shown here there's a quantity, it's how quantitatively that changes. So if I go from carbon to tin, actually the theta changes from 88 to the 94 degree. And what we have observed with increasing the theta, the carbon system, it shows the antiferromagnetic behavior, but the silicon, germanium, and the tin system, they show the ferromagnetic behavior. This EMT stands for the experimental and the theoretical results. Okay. Now, as you can see, with increasing the theta, actually the TC increases in this particular system. Okay, but something very interesting happens in case of the silicon case, which is a boundary case, you can say, where by application of only 0.5% biaxial compressive strain, one can have ferromagnetic to the antiferromagnetic conversion. Okay, where you can have intra-layer actually antiferromagnetism. Okay, so that means if I apply very small compressive strain actually in the silicon layer, it starts behaving like the carbon layer because of the decrease of this angle theta. Okay, now the question is that from the standard Goodenough-Kanamori-Anderson rule, actually we know that if some super exchange angle is near the 90 degree, it shows the ferromagnetic behavior. And if I go towards the 180 degree, slowly the antiferromagnetic ordering that actually grows in the system. Okay, but here something very opposite we are seeing. That is, if I decrease the angle, basically I am getting the antiferromagnetism, whereas increasing the angle getting the ferromagnetic. So the question is that in conflict with the Goodenough-Kanamori rule? Okay, so this is a very nice paper actually, which explains it very, very nicely. Okay, so they have also considered a similar kind of system, which is actually CuGeO system. Okay, the CuGeO3 is to be precise, and here you can see these are the copper atoms, these are the oxygen atoms. Okay, so the super exchange angle is copper, oxygen, copper, and once you do not have this germanium side group attachment to the oxygen, there is a head-on overlap of the orbitals, oxygen p orbitals with the copper d orbitals, which actually sets up the super exchange pathway. Okay, but the moment I have this kind of side groups attached to the oxygen atoms, the super exchange path actually completely changes, and you do not have the head-on overlap of the super exchange pathway. Okay, and that actually modifies this particular system, and that is what is actually giving rise to spin spirals defect also in this kind of CuGeO3. And that is precisely what is happening in this kind of system also, because as you can see, this super exchange path, this chromium, tellurium, chromium, the tellurium atoms are attached to the side group carbon or the silicon, germanium, tin in these X atoms actually. So in this presence of the side group, actually we have to consider the modified Goodenough-Anderson-Kanamori rule. Okay, so there is no conflict here. Now what I did actually, we have considered this bilayer heterostructure of this CrCTe3 and CrSiTe3 with two different stacking geometry, AB and the AA type stacking. I'll tell you what is the motivation behind that. Okay, so the lattice constant for the carbon system is 6.38, whereas the lattice constant for the silicon system is 6.80, and the lattice mismatch is 6.2%. Okay, now if I say the hetero-bilayer actually, the lattice constant is 6.57, which is in between these two lattice constants. Okay, so what one can see, 6.80 to 6.57 angstrom, this is already a 3 to 4% shrinking of the lattice constant for the silicon layer. Okay, but we have observed that only of 0.5% biaxial compressive strain can turn the ferromagnetic order in the silicon to antiferromagnetic one. So what will happen in this kind of case? Also in case of carbon system, okay, monolayer carbon system, it has been observed that antiferromagnetic ordering that is very robust up to the plus minus 16% of the biaxial strain. Plus minus stands for the compressive and the tensile strain. Okay, so this is antiferromagnetism very, very robust in the carbon system. So what will happen if I form this kind of heterobilayers? Okay, so what I did actually, we considered 4 different magnetic orientations in this heterobilayer.
Yeah, so
the first,
yes. So you have all total 5 minutes. Huh?
Okay,
so wrap up in 3 minutes.
Okay, fair.
Yeah, thank you.
So here you can see the intralayer and interlayer antiferromagnetic alignment of the spins in the 2 layers. Here the intralayer carbon intralayer antiferromagnetic, but the silicon is intralayer ferromagnetic. Okay, and in these 2 systems, both the systems are intralayer ferromagnetic. Whereas actually in this case, interlayer antiferromagnetic, interlayer ferromagnetic coupling we can see. Okay, and then we apply the compressive and the tensile strain to change the angle theta to see how the magnetic interactions actually vary. Okay, and here we can see actually at any compressive strain, always this structure 1 is the most stable one, and the stability goes from 1 to 2 to this one, it decreases. But in the tensile strain, initially, although the first structure is the most stable, beyond 1.75% of tensile strain, the second structure actually gets more stable. So this becomes the ground state. And beyond 3.75, these 2 structures become the ground state, but the energy difference between these 2 structures are very, very negligible. This black solid line and the red dotted line, these two. Okay, so what we have observed basically with increase in tensile strain in this particular system, we have seen the magnetic phase transition from this to this to this. And also, since these two structures are very close, energetically very close to each other, one can observe metamagnetic phase transition between these two systems. Okay, now just to remind you, metamagnetic phase transition was a characteristic of the CRI3, not for the transition metal trichalcogenide system. And this is something very new that we are observing in this class of system. Okay, now in this particular, the first structure, when both the system antiferromagnetic, the time reversal symmetry is actually preserved. As you can see, the both up and down spin bands are actually degenerated to each other. So this is MOK inactive. And not only that, as you can see here, the top of the valence band is actually coming from the silicon layer, where the bottom of the conduction band is coming from the carbon layer. Okay, so that means physically one can actually separate the excitons in between these two layers, and we have also observed the gamma 2K strong optical absorption spectra also. So the question is whether we can break the time reversal symmetry in this kind of system, and the answer is indeed yes, and which has been observed in this kind of MNP SE3, another transition metal trichalcogenide, which also shows intra and interlayer antiferromagnetism. Okay, now on application of the external electric field, both the time reversal and the inversion symmetry gets broken, and the system becomes MOK active actually. So that the same thing you can perform here also. Okay. Now, the second structure where I have this antiferromagnetism here and the ferromagnetism here, this also shows MOK, this is MOK active because of the overall ferromagnetism in the system. The time reversal symmetry is broken. Okay, and also this shows a straddling kind of band gap, which is type 1 semiconductor behavior, where both the bottom of the conduction and top of the valence band coming from the silicon layer in between the chromium bands, in between the carbon layer bands. Okay, and this is the last structure actually. As I told, because of the very less energy difference between these two structures, one can have the metamagnetic phase transition between these two. Okay, but instead of the very close proximity of their two energy levels, actually, what we can see, their band structure is completely different, these two systems. Okay, and they are showing completely different kind of electronic properties, although they are having very similar energy. Okay, so one can achieve very different electronic properties just by applying very small magnetic field in this kind of hetero bilayers. Okay, so to summarize what we have actually done, we have considered the hetero bilayers of the two different transition metal trichalcogenides, which actually, because of the lattice mismatch, exerts compressive and the tensile strain on each other, and because of that we see very rich phase diagram of the magnetic phases. And the additional application of the biaxial tensile strain also shows me the magnetic phase transition from here to here, and also there is a possibility of the metamagnetic phase transitions. Okay, and just I want to acknowledge my collaborators Satyananda and Sashmita for this work, and the funding agencies from the DST and the okay, and thank you for your kind attention.
Okay, thank you, Sudipta, for this nice talk. So now it's open for the questions. So I can see one question from Gaurav Jena. So can you ask the question, please, Gaurav?
Hello.
Yeah.
I just want to ask the uniaxial anisotropy term present in the Hamiltonian to get the magnetism in 2D at finite temperature. Is it means there is any justification to get this kind of term in the Hamiltonian, or this is just phenomenological?
Can you just repeat the question? I didn't get the question. So
okay, so you said to get the magnetism in 2D at finite temperature,
right?
So there, you can have some uniaxial magnetic anisotropy in the system,
right?
So is there any justification to get this kind of term in the Hamiltonian? Okay.
Yes. So actually you have another extra term appearing in the Hamiltonian because of this uniaxial magnetic anisotropy. There is a molecular field term, okay, which actually introduces the finite spin wave excitation gap at the zero energy. Okay. Does it answer your question?
Yeah. Yes,
okay.
Thanks.
So, Kalapatru, can I ask a question?
Yeah, sure.
So I have a very basic question. So in this kind of structures, how do I rule out in-plane magnetism?
Rule out in-plane magnetism in the sense, I am not ruling out the in-plane magnetism here.
Yeah, so this is coming out of a DFT calculation I get.
Right.
So there I have to actually fix the spin orientation and then I do a calculation, right?
Right.
So how do I rule? I mean, how do I rule out that it is not 45-degree inclined? Let's say.
Okay.
To the 2D plane, let's say.
Okay. So to be honest, actually in DFT, one can do that one. We have not done that one, but one can do the collinear spin alignment calculation also. But we have not done such calculations. Always we have considered this is actually oriented perpendicular to the plane. Okay, because I will tell you why. Because since this particular system is a soft Heisenberg type ferromagnet, and we have seen that just by application of the perpendicular magnetic field, one can actually align the spins perpendicular to the plane itself. Okay.
Then it is Ising-like, right? Not Heisenberg.
See, but if you turn off the magnetic field, actually immediately you lose the magnetism in this particular system. Ising type is that chromium halide one is the Ising type. But even in the absence of magnetic field, you have the perpendicular alignment.
Sorry. So I was not clear. So what I meant was that one layer, let's say, is pointing down, the other layer is pointing up, right? So, but the pointing up you have fixed in your calculation, right?
You mean this structure, this one?
Yeah.
Okay.
Yeah, just for example, in that one.
No. Actually, for the calculation, we have considered all possible magnetic structures. All possible magnetic spin
but always pointing along the Z direction, right?
Always pointing on the Z direction. That is true. Right. Yeah. So to be precise, it can be done in DFT calculation, the collinear calculation, but we have not done that. We have always considered the Z direction alignment.
Okay, fine.
Kalpataru, can I quickly make a comment regarding to with Amit's question? So as far as I understand, and you can correct me if I'm wrong, so if you take the anisotropy tensor, you can always write it in a diagonal representation where you will always have a x, y, z, only the axx, ayy, azz at non-zero. And in that basis, you can always choose one as the z-axis and do your calculation. I mean,
this right.
So I had a sort of slight curiosity if I can latch on to that. Can I ask that?
Yeah, please.
Okay, so I mean, see, from a general perspective, if I take a Heisenberg-like model, let's say a ferromagnetic Heisenberg model in 2D, and I put a small magnetic field, very small, to break the rotation symmetry.
Okay.
Then I can, as far as I remember, one can stabilize the TC quite quickly, which is controlled by J, but rests on the fact that you have broken the rotation symmetry. So Marmino-Wagner really doesn't apply.
Right.
So the question is, I mean, if you have a given TC in an experiment and you take a genuine 2D, I mean, modulo size effects, boundary effects, etc., is there an understanding of how much anisotropy energy versus how much magnetic energy would be required to obtain the same TC?
You mean the quantification of that?
Yeah, so I mean, my question is, see, if you have a magnet in 2D, you need to break the symmetry in some way.
Right.
Anisotropy is one way of breaking it. Putting a magnetic field is another way of breaking it.
Right.
For the magnetic field, at least I know that once I have a finite magnetic field and you break the symmetry, you can saturate to the TC controlled by the J of the model.
Right.
Fairly quickly in terms of the amount of magnetic field needed.
Right.
The question is the anisotropy, because the anisotropy, if it is in the Z direction, is a up-down, is a Z2 is still preserved,
right,
which is broken in the magnetic field case. So is there a understanding of the amount of or the energy of the anisotropy term needed to get the same TC compared to a magnetic field?
Actually, yes. Actually, there is a quantification. So your question is related to the Hamiltonian parameterization, if I'm not wrong, right?
Yes.
Yeah. So yes. Actually, for this particular system, this CRGT3. Okay. So the first paper, that is CRGT3, where they have reported for the experimental result. So they have actually shown the parameter space in the spin wave theory also in terms of that Hamiltonian that I told. Okay. So how much will be the strength of that one to achieve this, even in absence of the magnetic field? So that has been done for the CRGT3 system.
I see. Okay, thank you. Thanks.
Okay, so we're running out of the time. So let's thank Sudipta again. So thank you, Sudipta. Yeah. So now we have contributed talks from Ganesh Pal. Ganesh, can you share your screen?
Yeah.
So it's 3 o'clock. So we have 12 minutes. So I'll remind you in 9 minutes.
So is it visible? My
No, not yet.
No.
Not yet.
Okay. So I think, can you see my slides?
I can see your screen, but not the slides.
Okay.
You have to save the means that PowerPoint or PDF file only, yeah? Not the screen.
No, that I understand. It's not showing the PDF one.
Yeah, now I can see your
Okay.
screen.
So I can't do the full screen as I
Yeah.
had done earlier. Okay. Should
Okay,
I start?
yeah, start please. So you have 9 minutes plus 3 minutes, 2-3 minutes.
Okay. Thank you. So I start thanking the organizers for giving me this opportunity to talk here about my recent work. So I'll talk about the signatures of interfacial chiral modes by archive interaction in graphene and also in 3D wild semi-metal. So the talk is based on our recent work. I'll talk about these interfacial chiral modes in inversion symmetry broken graphene and also in wild semi-metal. Then I will talk about the stability of these interfacial chiral mode against the deformation of the quantum well. And lastly, I will discuss about the signatures of the interfacial chiral mode in archive-XN interaction. This interfacial chiral mode can be engineered across the interface of two non-equivalent trivial or topological insulators or materials in general. The essential physics is governed by the sign change of the symmetry breaking parameter across the interface, and there is the formation of the quantum well, which acts as domain wall along the interface. If we break time universal symmetry in the system, that gives rise to interfacial chiral modes with same chirality, whereas if we break the inversion symmetry in the system, that gives rise to opposite chirality interfacial chiral modes. So they are well known in the literature. So in our model, we have considered graphene and also wild semi-metal that we have not shown here. So the graphene in top of these HBN, which breaks the inversion symmetry here, and these arrows are indicating the magnetic impurities which we put along the interface. This is the domain wall here, and in figure B, we show the potential structure along the interface. And also there is a formation of quantum well here, which has a form of the Sekar parabolic square. Okay. So interfacial chiral mode in graphene, to start with, so we take this 2D graphene Hamiltonian, and there is an extra term proportional to sigma z, which is due to this broken inversion symmetry. And people have studied in experiments that there can be gap generated by this inversion symmetry, broken inversion symmetry in graphene via HBN. So we model this gamma as gamma tan hyperbolic x by L, where L is the width of our potential. Well, and now decoupling the square of the eigenvalue equation H2D psi equal T psi, then we get these equation, which is like 1D Schrodinger equation with a poststellar potential. So this is like poststellar potential, which has a sec hyperbolic square form. And this poststellar quantum well gives the bound state solutions with n equal to 0 mode and also higher order mode. So this n equal to 0 mode has, you can see the sign of depends on sign of gamma. So if gamma changes sign across the interface, then it gives rise to this interfacial chiral mode with opposite chirality. So a pair of interfacial chiral mode appears at the interface with opposite chirality, and there are obviously these higher order modes. And also these wave functions in both regions can be written in terms of Jacobi polynomials. And here we note that the difference of left and right moving chiral modes is given by the difference of the Chern numbers between the left and the right regions, which are separated by the domain wall So even though there is no topological phase transition by inversion symmetry breaking in graphene, but still the opposite chirality of interfacial chiral modes are topologically protected or preserved. So in case of 3D wild semi-metal, which is basically new and not known in the literature, in this case we write this 3D wild semi-metal Hamiltonian, and there is this beta term which breaks the inversion symmetry. So these beta, again, we have modeled like tan hyperbolic function which changes sign in the two regions, and this does not open any gap in 3D wild, rather it shifts the wild nodes along one of the KZ directions. So we have taken here in inversion symmetry broken case, we have 4 wild nodes, but we have only considered 1 wild node and have calculated things. So there are a lot of mathematics in my slides, kindly bear with that. And then again, the similar way we get, after squaring the eigenvalue equations, we get 1D Schrodinger-like equation, which have these Rosen-Morse potential. So Rosen-Morse potential have both sec hyperbolic square as well as tan hyperbolic term, and these Rosen-Morse potential actually exhibit a minimum for this range of kz, which shows that for some particular value of kz, this potential behaves like a quantum well. And this Schrodinger equation has a solution with n equal to 0 mode as well as higher order mode. So n equals 0 mode, again, you can see there is sign beta, which means if beta changes sign across the interface, so we have opposite chirality interfacial chiral modes, and also higher order modes are there. And the wave functions again can be written in terms of these Jacobi polynomials, but these are complicated functions, so I have not written all the forms here. Okay, and now we have only shown the smooth quantum well, but this is not needed. So even though we deform the quantum well, so you ask the question, what happens to the interfacial chiral mode? So we have taken Q deform hyperbolic function here, and thus the Q deform Rosen-Morse potential takes the form like the following: VQ of x, and then we have calculated as the following the similar way, and we have found that the energy spectrum is actually independent of these Q parameter. So that means that the interfacial chiral modes are robust to any kind of deformation to the quantum well. Indeed, we have checked that if we take a Heaviside theta function, even though we get the chiral modes there, interfacial chiral modes, which have exactly same energy. So so we show that the interfacial chiral modes are insensitive to any deformation to the quantum well. Now, if we put magnetic impurities along the interface, then we've studied what happens to the archiquary exchange interaction, which are conducted by these, the bound states only, not the bulk states. So for that, we have written our Hamiltonian like this, where there is the 2D or 3D wild Hamiltonian, and there is a lambda s dot h, where small s is the spin of the conduction electron of the material, and capital S is the spin of the magnetic impurity, which is put outside from outside. And so then we have written the ground state, the second order contribution to the ground state energy in a perturbative limit of lambda is written like this, equation 2, and where JEX is the archiquary exchange interaction between the impurities which are put in position Ri and Rj. In the first quantized language, this J can be written like this as a multiplication of force size and sum over all the momentums. Okay, so these are found from the seminal papers in the 90s. So we have only taken this J form and have calculated archiquary exchange interaction. So we have shown here JEX as a function of chemical potential for both graphene and wild semi-metal in A and B, where we see that this is of oscillatory nature as a function of mu, which we understand is because of the linearity of the interfacial chiral mode, as I've shown earlier, that En0 is proportional to Ky. Okay, and we also saw that as gamma L is increasing, so the strength of the archiquary interaction is actually increasing, which is due to the increase of the overlap of the wave probability here. And I emphasize here that we have only shown here the results for the interfacial chiral mode, not the higher order energies, because the higher order energy levels contribute very little, and their contribution is about 10⁻³ order or lesser. So this is solely governed by the interfacial chiral mode in graphene as well as wild semi-metal. So in case of wild semi-metal, we see here again similar structure, similar nature of these archicoaxial interaction as a function of mu, where we again see this oscillatory nature, and this increases when this beta L or inversion symmetry breaking parameter increases, which again is due to this probability overlap. Okay, and also we have shown here these archicoaxial interaction as a function of x and y, where x, so this is the width and this is the distance between, y is the distance between the impurities. So we see that as a function of x, it's decaying because of the hyperbolic function, hyperbolic form of the quantum well that we have taken. And also, as we increase the inversion symmetry breaking parameter beta L, we see there's a rise in JEX, which points that this is only coming from the interfacial chiral mode, and the other modes do not contribute in this regime. And we can also understand from the figure A that here gamma L is essentially the gap in the graphene case. So here we have put the chemical potential from -1 to 1, where the gap is 5. So there is only interfacial chiral mode present, and this is similar for while as well. So that's why the other modes do not contribute. As a function of y, the nature is similar to what we have, what we know in case of archicoaxial interaction, which are studied in case of materials, doped materials, where the interaction is carried by the bulk states. But here the difference is that the archicoaxial interaction is carried by the bound states, but the nature is similar. So there is this oscillatory nature coming. And again, here also we see that as we increase this beta L or the inversion symmetry parameter, this increases. And one more important point is that here we see only antiferromagnetic nature of archicoaxial interaction, which is because we have opposite chiral interfacial chiral mode. So scattering from them only can take place with antiferromagnetic nature. So as a summary, we have shown here the emergence of interfacial chiral mode in inversion symmetry broken graphene as well as wild semi-metal. The wild semi-metal case is rather new. The graphene was known long back, and these interfacial chiral modes are independent of the deformation of the quantum well. And there is a clear signature of the interfacial chiral mode of gap graphene or wild semi-metal in archicoaxial interaction due to their dominating contributions compared to the other bound states, E n not equal to 0, the higher order states. And also these, as we can tune this size of the quantum well, so basically we can separate out the bulk and the surface states in wild semi-metal as well as graphene, and which is novel. And as far as the experiments are concerned, so the magnetic catatoms can be implanted on inversion symmetry broken wild semi-metal like TIS or TIP, and archicoaxial interaction can be measured by a spin dependent scanning spectroscopy, as has been done in case of platinum. Cobalt has been deposited on platinum there, and our work is based on this. This talk is based on this work. Okay, so I thank my collaborators, Professor Ajit Shah, my supervisor, Firozda, and Paramitadi. Okay, thank you.
Okay, thank you, Ganesh, for your nice talk. So now we may have 2 or 3 questions. Please, anybody?
Can I ask a question?
Yeah, sure.
Amit
from
please. Kanpur, actually. So Ganesh, can you go to the first slide? I missed the geometry actually.
Yeah.
So X is which direction here?
So X is, so you can see here X, Y, Z are written there. So along Y we have this interfacial chiral mode.
Okay. So then I have some very simple question. So one is, what is the origin of this chiral modes? Meaning, why do I need, let's say, massless Dirac dispersion on both sides?
Right. So essentially, here you can see that from the very first equation, you see that H to D Hamiltonian. So this gamma X is basically the gap that is generated by this inversion symmetry broken parameter. So this can be done by say HBN, so substrate effect. So this breaks the sublattice symmetry and opens up a gap. So if you have gap of a plus gap here in the left side and the minus gap in the other side, then you have a so gap closing near the interface. And that gives rise to these chiral modes there, which has been studied by these 2 papers actually. In graphene, there are studies.
I got mixed up. Then I have even simpler question actually. So in this equation, why do you have this parabolic dispersion dou 2x by dou x2? I would have really thought that for graphene Hamiltonian, I would have a linear term.
Yes, so that's what. So if we decouple the square of the eigenvalue equation, then we get like this. So H2D psi. So this is the equation for the 1D case. So only for the interface. So along the interface,
Interface
there's
is
a
along
one.
y, right? Your equation is along x. So I got mixed up.
Okay.
In your notation, the interface is along y, right?
Interface is along y.
Along x.
And this equation is along x, right?
That's true. Yes.
So are you saying that there are two spinners?
No. So that's correct. So okay.
So if I decouple them, then it becomes a quadratic.
So yeah, essentially square the eigenvalue equation and then have got and no. So you are correct. So this is along the x, and then the solution gives us like these wave functions which have these tan hyperbolic function. I mean these Jacobi polynomials.
Yeah, but why is this not a spinner? I naively would have thought this would be a spinner since you are in graphene.
Okay.
So the normal Hamiltonian in the first line is 2D, right?
Yes.
Sigma polymatrices are there. So the wave function I would have thought was a spinner. Some simple mix-up I am having. I mean.
Okay, maybe Amit, we can
May I
discuss
add
it.
one comment? Sorry.
Sure, sure.
Yeah, myself,
Yeah.
Paromita. So this is a square of the eigenvalue equation, and this is for only one sublattice, as Ganesh is showing. And there will be another similar equation for another sublattice.
So we had coupled linear equations. When we decouple, we get this.
Yes, exactly.
Fine. Thank you.
Okay. So let's. So we may not have more time for questions. So let's thank Ganesh again. Thank you, Ganesh. So now we'll move to Shiv Prasad Sastry. So Shiv Prasad, can you share your screen, please?
Okay, sir. I'm sharing my screen. Okay, sir, is it visible?
Yeah. So next speaker is Shiv Prasad Sastry from IIT Mandi. So we can start, please.
Okay, sir. Good afternoon, everyone. Myself, Shiv Prasad. I would like to present my work on a promising half-user thermoelectric material, FESCB. My study is a first principle study of the electronic structure, phonon properties, and the lattice thermoconductivity of this FESB half-user. Okay. One second, I'm just pasting a. Okay. Outline of my talk is I will give a brief introduction about the thermoelectric materials and methodology, then computational details, and then I will discuss my results and I will give a summary of. Okay. Thermoelectric materials. As we all know that thermoelectric materials are the materials which can convert heat electricity into electrical energy and vice versa. And the efficiency of this thermoelectric material is the maximum efficiency is given by the formula here, eta max equal to Th by Tc divided by Th into root of 1 plus the T bar minus 1 divided by root of 1 plus the T bar plus Tc by Th. And here Z is called the figure of merit, and it's a measure of how good the thermoelectric material for application. And it depends on the material specific quantities, Seebeck coefficient S, sigma, electrical conductivity, and electronic part of thermal conductivity, kappa I, and the lattice part of thermal conductivity. Here we can see that the Seebeck coefficient, electrical conductivity, and electronic part of thermal conductivity are derived from the electronic structure of the material. And this kappa L, the lattice thermal conductivity, is dependent on the phonon dispersion or phonon spectrum of the material. And this, as we know that this thermoelectric materials are useful in applications where waste heat recovery is required in places like automobiles and industry, and they can be used as in radio thermoelectric generators in space missions, and they're as a portable power and as Peltier coolers. So advantage is that they are scalable, noise and vibration free, less harmful to environment. And at the basic physics level, as we have said that this understanding of studying the thermoelectric properties gives an understanding of the electronic structure and phonons in the material. Okay, then why half-user thermoelectric materials? So as we can see from this figure, here we can see that the half-insular materials based on this MnISN, MCOSB, and this FeRASB, where R is vanadium and niobium, and here M is titanium, zirconium, and hafnium. They are drawing attraction of the thermoelectric community. As we can see that at the higher temperature region, 900 to 1200 Kelvin, there we can see higher ZT values for the N-type and P-type materials. And another advantage is that compared to other materials like lead telluride or silicon germanium, bismuth telluride, they have higher melting point, and these materials are have good mechanical strength. So this has the advantage of using it in the high temperature applications. So keeping this in mind, we are studying exploring the half-insular materials as thermoelectric materials. And here we studied one more promising thermoelectric material, FeVSB. And FeVSB also has the space group number 216 and with the C1b structure. Here the iron atom sits at the 4C wiper position, and vanadium is at the 4A 000, and SB atom at the half. Okay, then to study the thermoelectric materials, foreign materials, there are two ways we can study. One is experimental method, and another is the computational method. So, so here we are doing the computational study method. In the computational approach, generally it involves the first principles electronic structure calculation. So mostly density functional theory is used, one of the popular method, and or GW or DFT plus dynamical mean field theory can be used. And later to study the phonon spectrum, density functional perturbation theory and or supercell finite displacement method can be used. And if you want to further study the electron and phonon transport calculations, Boltzmann transport theory is employed, and carrier lifetime calculations. Okay, so in our work we use the density functional theory calculations to get the electronic structure of the material and forces on the atoms. So in density functional theory, the system is described by a Condensed Hamiltonian, and in this by solving the Condensed Hamiltonian, we get the Condensed eigenvalues, and once which is displayed here is Hamiltonian, and once we get the eigenvalues, using the eigenvalues, we can get the total energy of the system, and also once we get a band structure E and K, we can get the group velocity and effective mass, which are essential to understand the transport in a material. And we can also calculate the forces on atom as a derivative of the energy energy with respect to position. Okay, then next we want to study the transport in a material. So the method is the Boltzmann transport theory is employed. So when a measurement is done on a sample like electrical conductivity or electronic thermal conductivity or Seebeck coefficient, a sample is subjected to electric field gradient, magnetic field gradient, temperature gradient. So when a material is subjected to these external influences, the sample is the system is driven out of the equilibrium. So in such case, the state of the system is described by the non-equilibrium distribution function. So this non-equilibrium distribution function gives the probability of occupation of a state of a system when external influences are applied. Okay, so once so knowing the non-equilibrium distribution function under different conditions, for example, in case of electrical connectivity measurement, there is delta E. We are applying a electrical field gradient, but keeping the temperature gradient 0. So applying this condition into the what is called the non-equilibrium distribution function, one can get the transport distribution function, which is given by this expression sigma of E of t equal to integral of these terms, which are here, which contains the group velocity and here we can see tau. This is a lifetime, relaxation time, which is dependent on the band index and position, wave vector and position as under the relaxation time approximation. And once using this, here we can see that a general transport coefficients are defined using this L of alpha mu of t, where mu is the chemical potential, and here Q is the charge, and sigma is this general transport distribution function. Sorry, this transport distribution function. And here F naught is the Fermi-Dirac distribution function. So once we know this, then in terms of then the current density, electrical current density, and charge current density, JE and JQ, they can be obtained in terms of the generalized transport coefficients. So as these two expressions. So from the generalized transport coefficients, we can get the sigma as L of 0, and the Seebeck coefficient as 1 by Qt into L of 1 divided by L of 0, and electronic thermal conductivity as 1 by Q square T into L of 1 whole square divided by L of 0 minus L of 2. So in our study, we have used the program which based on the constant relaxation time approximation. That means here in this expression of the sigma, tau is considered as a constant, so it comes out of the integration, and electrical conductivity is calculated as sigma by tau. Similarly, electronic thermal conductivity is calculated as kappa e divided by tau, and in this case, the Seebeck coefficient becomes independent of the relaxation time. So we can directly get the Seebeck coefficient.
So,
okay.
So we have 3 minutes all total.
Okay. I will be moving faster. So this is the calculation of the lattice thermal conductivity. So in the lattice thermal conductivity, mainly lifetime is calculated, and it is obtained from this expression kappa pH. And C lambda is the mode heat capacity, E lambda is the group velocity, and tau lambda is the lifetime of the phonons, obtained as the inverse of the imaginary part of the self energy. So for the calculations of forces and this electronic structure, we use the VN2 program, and the Phono 3Pi and Phono Pi are used for the phonon calculations, along with the Abinit. Okay, and here I will discuss my results. So here I'm showing the electronic structure of the FEVS decomposed. Here we have calculated with including spin-orbit coupling and without including spin-orbit coupling. So band gap is 0.33 eV using the scan meta GGA, and here also we can see the partial DOS, and in the valence band region, mainly iron 3D iron in the valence and conduction band orbit, we can see the iron 3D and vanadium 3D orbitals, and the band gap is due to hybridization between vanadium and iron 3D orbitals. And for this compound, actually band gap is not reported experimentally till now from any optical measurements. So we try to explain the experimental Seebeck coefficient of the two et al. So we calculated the Seebeck coefficient under Boltzmann transport theory. Red one is the calculated one, and black one is the experimental one. Here we can see the good matching with the experimental calculated one. And this was done by varying the band gap between 0.2 to 0.7 eV, and good matching was obtained for the at a band gap of 0.7 eV. And the band gap calculated from the MBJ, which is known to give a good gap for semiconductors, is also 0.7 EV here. And next, I'm showing the phonon dispersion. For this compound, we have reported the phonon dispersion, which is not yet studied. And here, first one figure shows the dispersion without including the effect of the long-range Coulomb interactions. And after including a long-range Coulomb interaction, here we can see the lift in the degeneracy of the longitudinal optical modes. Optical modes in the near the gamma point. And we also calculated under the harmonic theory the specific heat and Helmholtz free energy. This is we can see specific heat we compare with the CP, and it's in good agreement at the lower temperatures. And further, for a thermoelectric material, to design a thermal generator, thermal expansion plays an important role. At the junction of two materials, how much distance we can have to keep, and how much stress it can produce. So for that purpose, we calculate thermal expansion.
Sipasad, how many slides you have? So your time is almost over.
Last two slides.
So please talk in 30 seconds, please.
Okay. And this is the lattice thermal conductivity. And here we can see that at higher temperature, there is a good matching between experimental and calculated one using phonon-phonon interactions. And the cumulative lattice thermal conductivity analysis shows that maximum contribution comes from the acoustic phonons. And we also predicted the figure of merit and efficiency, and maximum ZT figure of merit for the p-type is 0.66 and the n-type is 0.44. Okay, thank you.
Okay, thank you, Shiv Prasad. So maybe we have one question if somebody has a urgent questions. Any raising hand? No. Okay, if not, let's thank Shiv Prasad again. Thank you, Shiv Prasad. So this session is over. Over to you, Anamitra. Anamitra,
okay,
are
sir.
you there?
Thank you.
Yeah.
Hi, so thank you, Kalpataru. So we are running a bit late. So the next session, is it okay if we start in 5 minutes? I mean, or if, I think that's a fair amount of this thing. So Sumilan, I have made you the session chair. We'll go by whatever you say. So should we start in 5 minutes? It gives me a little time to get the other speakers in.
Sure. Yeah. Okay.
Okay,
I'm
so
here.
we
Yeah.
start at
Yeah.
3:35.
Yeah.
Okay.
That's fine.
Sure. Okay. Brown. Okay. Am I not? Oh, okay, sorry. So any of the speakers of the present session wants to check their this thing, screen sharing, or if people are confident, then we can skip that.
Hello.
Hello.
Am I audible?
Yes. Who is this?
Okay. Oh, Prabhakar. Just I want.
Okay. You can try and share your screen with me. Try sharing your screen.
Okay. You haven't made me co-host, I think.
Yes. Okay. Sorry about it. Okay. Now try. You should be able to do it now.
Is it visible?
Yes, it is visible. We can see yours. Just go to full screen.
Yes, you can see the cursor.
Yes, that is fine. Yeah.
Okay. Thank you.
Good. Okay, so you can unshare your screen.
Okay.
Okay. Anamitra, this is Shubhra. If there are no other people who wants to try, shall I try?
Yeah, please go ahead.
Can I try once?
Sure. Just go ahead. Yeah.
Okay. So
yeah, I can see your screen.
You can see, right?
Yes. Yes.
And you can see cursor, everything now?
Yes, it's full screen. I can see your cursor moving.
Okay, okay. Yeah.
Okay, thanks. So Shubhro, you can try.
Okay, let me just do that. Okay, good. Can you see my screen?
Yes, it's on full screen. If you want to move your cursor,
Yeah.
you can.
Yeah. Can you
Okay.
see my cursor?
Yeah, it's a pointer. Yeah, sure.
Okay, good.
Okay.
Yeah. Okay, shall I leave this here or?
Anybody else? So there is another speaker. So Mona Lisa, did you want to try? You.
Yes, sir. I tried yesterday.
Okay. Okay, fine.
Should
Then
I
we
check
can.
again?
No, no. If you are confident, it's fine. I think it will work. There's no issue. There should not be an issue.
Okay, sir. Thank you.
Okay. Okay. So I think you can leave it on Shubhro, and we'll start in a minute.
Yeah. Okay. Sure.
So Sumilan, just to let you know, so there was another speaker, Ranjan Modak. Some of you might know him. So
Yes.
he unfortunately he has a COVID case in his family.
Oh, I
So he
see.
had to drop out at the last moment.
Mhm.
So we hope things are okay with him.
Yeah.
Aside, I'll inform you guys.
Okay. Yeah. Thanks. Yeah. Yeah. So we have basically one list of. Okay. Fine. Yeah.
Yes. Okay, Shubhra, Sumilan, I'm muting myself. I'm turning it over to you.
Okay. Yeah. Good. Thanks. Okay, so I'll start this session. So welcome you back to this last session of today. And I'm Shumilan from IISc, Bangalore. And I'll be chairing this session. And so we have 4 talks, 1 invited talk and 3 contributory talks. And the first talk will be given by Professor Shubhro Bhattacharya from Bhattacharya from International Center for Theoretical Sciences. And he'll be talking about many body chaos in classical spin systems with and without quasi-particles. So Shubhro, I'll let you know at 19 minutes. Okay.
Okay. Yeah, thanks, Shumilan. And let me start by thanking the organizers for inviting me. And I was, these meetings used to be a good annual catch-up meeting with friends and the physics that is happening at different parts of the country in their groups. But I guess because of this abnormal times, this has to be online this year, and I hope that all of you are safe wherever you are. So I would be talking about some of the recent things that we have been doing, and I'll be talking about classical spin systems in a quantum condensed matter meeting, but soon we would realize that the context in which I would be talking about is very familiar, and it's essentially the transport and dynamics of unconventional phases and conventional phases, a bit classical. Okay, so so these are the people with whom I have been collaborating from various with various expertise and backgrounds. The ICTS gang with the students and my colleagues Abhishek, Shamriti, and Anupam, the students Abhijit and Sugan, and their people who were from ICTS and have since moved on, and collaborators from outside. And these are some of the things that we have put out, and there are several things in the process. And in particular, I'll talk about, I'll introduce this first part, and then I'll mostly talk about these second and fourth. And there are various things I can go on talking about, but I'll try to summarize then. Okay, good. So, so what I want to talk about are classical spins, particularly spin rotation invariant systems with Hamiltonians given by the Heisenberg type of Hamiltonians by and by classical spins. We basically are thinking about unit vectors at every site of the lattice. And what we want to do is to take such systems and think about cooling them at high temperatures. We have thermal paramagnets, and when we want to when we cool them or decrease the temperature, we get depending upon the kind of interactions, we get unfrustrated magnets where we have compatible interactions. At some point, the symmetry breaks. We have spontaneous symmetry breaking, and we go into an ordered phase like the ferromagnet and antiferromagnet, etc. And a typical signature of these kind of things happen in the magnetic susceptibility, where when I reach a temperature of around the interaction scale, the dominant interaction scale, I switch over from the Curie-Weiss type of behavior of 1/T type of behavior to something else dominated, and this signifies the phase transition. Okay, so this is what sort of well-behaved magnets do, but there are other things like these frustrated magnets with lots of incompatible interactions, which cannot be simultaneously satisfied, and one has to reach some kind of compromise. And in this kind of systems, what happens is that unlike in the unfrustrated case, once you start cooling down the system, even on reaching a temperature scale which is compatible with the dominant interaction scale, the system does not order, but goes into what is called a correlated paramagnet, which is really a crossover from the thermal paramagnet, but it has interactions built into it. Okay, and until at further lower temperature, it reaches it orders due to secondary exchanges or thermal order by disorder in classical systems. Okay, so that's what the thermodynamics is, and what one can do is that by fine-tuning your interactions, getting rid of the secondary energy scales, you can keep the you can prevent the correlated paramagnet from ordering down to zero temperature, and that's sort of model system where you have macroscopically degenerate ground state manifold and finite entropy density in the thermodynamic limit. But because of the energy constraints at low temperature, you have non-trivial spin correlations, and that leads to non-trivial dynamics, which has to take in care of the energy constraints. Okay, so what we want to do is to try and understand the dynamics of these kind of systems, both these kind of systems, and the low temperature dynamics of these unfrustrated systems, once the system orders, is controlled by the ballistic collective modes, which are these quasi-particles or spin waves. And at low temperature, we can roughly think about the system as a gas of weakly interacting spin waves. Okay, so the spin waves are long-lived and they are weakly interacting. On the other hand, what happens with these frustrated magnets is that there are no ordering, so there is no quasi-particle description. What instead happens is that there is an extended ground state manifold, and the system sort of keeps on fluctuating within this ground state manifold with a width of proportional to the width is roughly proportional to the temperature. So the system has lost its microscopic energy scales, but and temperatures serves as the only energy scale. Okay, so the particular questions that we want to ask is that what are these many body signatures of chaos, and particularly in presence and absence of symmetry breaking, or in particular, what kind of what does presence or absence of symmetry breaking does to the many body chaos, the presence or absence of quasi-particles. And one of the many reasons to ask this question is that these time scales and length scales of chaos and the dependence on correlations on thermodynamic variables needs to be understood, and their connection with transport time scales and length scales also needs to be understood. Okay, and then the question is that how do we measure chaos? And this is something that we sort of addressed in this paper. Is that you take two copies of the spin systems, one slightly disturbed from the other locally, say at one site, and try to evolve these two copies separately. and at every point of time, take the 2 copies and compare the spin configurations through calculating the difference of the spins at the same time, at the same position, but for the 2 copies. Okay, so that's what is called the cross correlator or the decorrelator, and one can study that. And what we find is that even in absence of ballistic modes that set infinite temperature, one gets a light cone where inside this red region the decorrelator is exponentially active, whereas in this blue region the decorrelator is exponentially suppressed. And what one gets is that at sitting at a same position, the decorrelator grows exponentially in time, which is characterized by this Lyapunov exponent, and the front spreads ballistically in space, which is specified by this butterfly velocity. And these butterfly velocity and Lyapunov times basically characterize the chaos length scales and time scales. And what we would like to then ask is that and probe are these 2 particular things. What happens when we suppress ordering, and what is the signatures of chaos in this correlated paramagnet, and which is what was done here, and more recently, what happens when the system starts ordering. Okay, so this is the main result. What happens if I try to draw the light cones, and I'll show actual data. This is just a schematic, is that at short time scale, once the system orders inside the ordered phase, we have a short time integrable behavior, which is this blue region, and then which is followed by sort of a scarred regime, which is dominated by rare events of scattering of spin waves, followed by a fully developed chaos at long times, which is this red region. But this chaotic region sort of disappears as temperature goes to 0. And this, I'll claim, is this kind of picture is the basis for kinetic theory type of description of transport in these kind of systems in terms of the low energy quasi-particles. On the other hand, the chaotic dynamics in this correlated paramagnets survives all the way, all through, and there is no emergent short-time integrable behavior, but the chaos disappears much slowly at 0 temperature, and we don't have a simple kinetic theory description. Even then, the diffusion of conserved charges is determined by the chaos timescales and length scales, even though there is no single particle scattering picture. Okay, so so let's start with the correlated paramagnet, and I have about 10 minutes. So let's start with about with the correlated paramagnet, where there is a lot of entropy, and the question along with the energetic constraints, and we want to ask is that due to this entropy, the system can arrange itself in various ways, loosely speaking, and then how does this disorder? What are the chaos signatures of this disordered system? Okay, and these similar kind of questions, you can pick your choice about the context of asking these questions. You can pick the frustrated magnet as in the present talk, but there are other contexts in which you can essentially ask the same questions, both quantum and classical. Okay, so so the particular microscopic model is a model on a Kagome lattice, which has the next nearest neighbor, and third nearest neighbor, all tuned to the same value. This is the fine tuning that I was talking about, and this is something that Arnold Shen and his collaborators looked at also for the statics, and this has a macroscopically degenerate ground state manifold and realizes what is called a classical Z2 spin liquid, where you have finite correlation length but no ordering. And these are the equal time structure factors, and you can see that there are no magnetic Bragg peaks, and that's the signature that there is no ordering present in the system. And if you look at the dynamic correlators, for example, the autocorrelation function at the same site, you would see that the autocorrelation function is exponentially decaying, but the exponent is completely completely determined by the temperature which you can also get from the large N analysis. But the idea is that once you have this ground state manifold, there is no other temperature scale, and the system sort of goes around and decorrelates in this manifold whose width is given by the temperature, and that is the reason why the autocorrelation decays with temperature. Similarly, for the diffusion, you get diffusion in long, you can calculate the dynamic correlators and get the diffusion at long wavelengths, and the diffusion constant essentially becomes temperature independent at low temperature. At low temperatures, that's essentially because to go through the ground state manifold, the system does not essentially require any energy. Okay. Okay. So what you see for the chaos is that once you start calculating the decorrelator, the decorrelator again spreads ballistically, and this is a movie showing the same thing, the spread of the decorrelator, and you can see that the decorrelator spreads ballistically even though there is spin diffusion, and the spread is isotropic even though the underlying microscopic symmetries is only C6. So this solitonic like spread, by that I mean the sharp front in the decorrelator is characteristic to it, and again there is exponential growth and ballistic spread, and the exponential growth is characterized by a Lyapunov exponent which goes as temperature to the power half, and a butterfly speed which goes as temperature to the power 1/4. Okay, so what we see is that this remarkable fact that this temperature dependence basically dimensionally v square over mu accounts for the diffusion constant, and then the question is that how general are these results? In the sense that the diffusion constant of the spin diffusion is captured by the chaos time scales and length scales. And one way to understand this is that in both the copies, both the difference of the spin densities and the mean spin density both are trivially conserved because these are spin rotation invariant system. And so, so in a system with short range interactions, one expects that these diffusion constants to be diffusion constants. Sorry, these densities to diffuse with different diffusion constants. So so basically let the mean magnetization diffuse with diffusion constant D plus, and the difference that we have actually calculated in this decorrelator to diffuse with D minus, and then essentially ask how should I think about these two densities? And apart from the short range fast oscillations, these are how they should evolve. There is a 1 over square root t factor that I'm missing, and but these fast oscillations for the mean magnetization is always of the order 1. But for the difference fields, it grows exponentially, starting with a very small value, and that kind of idea fixes the fact that the difference.
Hello.
Hi, is this Shumilan?
Yeah, I can't hear anything. Yeah, is that?
Yeah, I think Shubhro's end there is some connection. Maybe we can just
Okay.
drop him.
Yeah, just wait a little bit. Yeah, I will mark the time. So what should we do, Anamitra?
I have just written a chat to
Hmm.
Shubhru that is not audible.
Okay.
Let's see what is. Shumilan, you have Shubhru's phone number?
Yeah, I can call him.
Probably it will be better to call him. Maybe he's not aware of the issue.
Yeah. His number is showing switched off. I'll try to call him by WhatsApp.
Okay, I think here Ashish has his number. He's also trying.
Oh, okay.
Maybe it's another number. Maybe let's wait a little bit. I mean, this is the last session. Maybe we can continue a bit more.
Yeah, right.
Oh, Shubhro left and joined. So let me make him this thing, co-host again. Yeah.
Sorry, I had an internet glitch.
Hi, Shubhro. I've made you a session chair, co-host. You can try share.
Yes, I'll share my screen again. Sorry about this.
That's it.
So Shumilan, can you tell me where did where was I lost?
Yeah, so if you bring your slide.
Yes,
Yeah.
I'll
tell you. So it is after you showed that D equal to this.
Hello?
D equal to this. Yeah, here. So no. So go slightly. No. So go slightly farther.
Hello?
Yeah, go ahead.
I should go back.
No, go ahead. Yeah, I'm actually hearing some echo.
Yeah, how about this?
Here. So this fixes that point.
Okay. Yeah. Sorry about this. I'll start again.
Yeah. So I think you lost 3-4 minutes.
Yeah.
So we'll
I'll try to make up. Yeah, I'll try to make up. Okay. So essentially, what happens is that because because of the absence of microscopic timescales, these two diffusion coefficients, the physical spin diffusion coefficient and this difference of this fictitious difference field that I have cooked up, they become proportional, and one can show this with various approximations. But as I pointed, and this is where we started missing, I went offline. So the derivation of this the physical diffusion constant and the difference field for a correlated paramagnet in closed form is not there. There are various hand waving approximations that one can make to motivate this, but not derive it. And the general problem seems to be trying to derive an equation motion for the decorrelator, which involves solving a nonlinear mode coupling problem, both for quantum mechanics and the classical systems, and which is generally difficult. And the usual truncation schemes for the mean magnetization does not work. for the decorrelator, and this makes the problem even more harder. And what we have been able to do so far is to try and answer this question, that to obtain a controlled limit of this mode coupling theory for the decorrelator in the low temperature ordered phase. And in this process, we now understand this interplay of chaos and spontaneous symmetry breaking, which is what I'll try to cover in the next 3 or 4 minutes. Okay, good. So so essentially what we find is that at short times, we and this is the actual numerical data of the decorrelation function, is that at short times you get this nice non-exponential behavior, which is characteristic of integrable systems. And essentially this is coming from non-interacting spin waves, or spread of non-interacting spin waves, which then give away to an interaction. Still rare interaction is rare, so it gives rise to a scarred regime where you have few interactions. This is, by the way, a single realization. And finally, this scarred regime gives away to the fully developed chaos, where you see exponential behavior at longer times. So this is what you can capture using a mode coupling description, where in presence at low temperatures, you can expand the spin fluctuations as the ordering field and then perpendicular fluctuations or the spin waves, and derive the mode coupling equations for the difference field from the equation of motion from the spins. And it has a free linear part and a mode coupling part arising from arising due to spin scattering.
Shubhro, 19 minutes. Shubhro, 19 minutes.
Yeah, okay. I'll wrap up in a couple of minutes. Okay, so then this mode coupling theory is controlled really in the spin wave amplitude, and one can go ahead and calculate the decorrelator using these expansion schemes, and it has a free linear part, and then there is an exponential part. So this free linear part dominates the short times, gradually this nonlinear part takes over, and this is the mode coupling route to chaos that this system gets. And this is a short time behavior, and you can in fact you can exactly calculate the integrals at short times, and you get Bessel's function for a ferromagnet. And you can see that the free theory you can plot, and this is the actual numerical calculations, and they are in nice agreement. You can make more quantitative estimates. This is for the antiferromagnet. Again, you can see the difference between the anisotropy of the wavefront comes from the nature of the ground state. So at intermediate times, you can see that as you heat up the system, and at short times, this is and at low temperature, this is governed quite nicely by the linear spin wave theory. But then it starts to deviate, and this occurs because of the spin wave fluctuations, and this rare scattering events in this intermediate times gives rise to this scarred behavior, and finally giving over to chaos, where these mode coupling terms really dominate. And what we could prove is that this Lyapunov exponent in this regime is bounded by the maximum of the inverse spin wave lifetime, and that's the connection at low temperatures that we know from other places too. So regarding the temperature dependence of Lyapunov, there is a temperature dependence for the Lyapunov. It goes as temperature T to the power alpha, where alpha is greater than 5, so it becomes it is less chaotic than the correlated paramagnet. Whereas for the butterfly speed, unlike the correlated paramagnet where the butterfly speed goes to 0, it becomes finite, and it has a characteristic dependence for the ferromagnet, and particularly for the antiferromagnet, where it is related to the spin wave velocity and suffers from the same kind of renormalization as the spin wave velocity in an antiferromagnet. Okay, sorry for this trouble. I think I badly run out of time, so I'll just leave the summary and thank you for your attention. And if there are questions, I'll try to answer.
Okay, thank you, Shubhro. So we have we have couple of minutes for questions. So go ahead.
Shumilan, I have one.
Yeah, please go ahead. Yeah, please go ahead. Anamitra.
Hi, Shubhro.
Yes.
There is some sort of an echo, but anyway. Suppose.
Yes, Anamitra.
Yeah. So that you said is SI dot SJ model, illustrated system leading to a finite parameter.
Shubhro, sorry, there is an echo. Maybe when Anamitra asking question, can you mute your?
I'll try to do that. Let me try to do that. Okay.
So I think now Shubhro is muted.
Yeah, please go ahead, Anamitra.
So I was asking if I had a frequency dependent J, so J of omega SI dot Sj. The reason I'm asking that question is, if you take a generic Hubbard model kind of system, and in a Hubbard stratum which sense integrate out the fermions, in the auxiliary field coupling, you can get a spin model, but of course the J's of this model will be frequency dependent. So I understand this problem is hard to do. I mean, I'm just wondering if there is some intuition that one can gain there. When I say, we're just talking not the superconducting pseudogap, but the pseudogap that arises on heating the half-filled Hubbard model. Shubhro has to be unmuted.
Sorry, you're thinking about the fluctuations in these coupling constants, the temporal fluctuations in these coupling constants?
Yes. So if you write an effective, the kind of thing one does in determinantal quantum Monte Carlo, where you have some effective classical model, but a frequency dependent J.
Mm-hmm.
So even if one linearizes it in frequency, how much of this intuition can be borrowed there?
So I think that the general point is that if you make the coupling constant dependent, then there is no energy conservation. So lots of these properties go away in the form that I presented. So this is in the sense of what I said is in the sense of Hamiltonian chaos. But then there is this whole idea of chaos in dissipative systems, which is where I think your question would fit. And there you can see analogous behaviors of these light cone spread, etc. And some of these things have been very recently looked at by one of my colleagues. I think he is around, Manas Kulkarni and Anupam Kundu and their collaborators. And so some of the broad features like light cone, etc., go through in the chaotic regime. These are the regimes analogous to the chaotic regimes of Lorentz map, etc. And but there are regimes where the dissipation dominates, and there you don't see any chaos, but you see decays of correlators. So I think that your question fits in that scheme of things.
Okay, thank you, Shubhro.
Okay, Robbie, one quick question. So Robbie, go ahead.
Yeah, so am I audible?
Yeah.
So Shubhro, when you were making the comparison between these decorrelators for the ordered state and the Kagome model that we were looking at, so in the ordered state, there is a natural starting point about which you will perturb and look at two nearby states. Which part of the degenerate manifold in the frustrated case are you looking at to evaluate the decorrelator?
So for the frustrated magnet, sorry, there is a lot of echo. Yeah. So in the frustrated magnet case, I did not do mode coupling expansion, and sorry, I went over this fast. So that's the problem, that I do not have any thing to expand about. And in fact, I can tell you what the problem becomes. You have this manifold, which is a hyper plane in the phase space, and you want to try and understand the change of configuration in this hyperplane, and that seems to be a problem in a high dimensional classical gravity, which is what you need to solve. So I can tell you discrete results about this, and various people from chaos community knows about this, and the Lyapunov exponent and these butterfly velocities can be understood from trying to understand the geodesic problem, geodesic separation problem in high dimensional gravity. That's what it becomes, but that's a problem that we have not been able to solve.
Okay, so very quick question if you have, since it's the last session, I'll just, very quick question, Shumila.
Hi, Shubhro. So, firstly, I presume the fine-tuning of the Hamiltonian is you can unfine-tune and the scenario that you laid out goes through, right?
Yeah.
Yeah. But my question is, all this dynamical information that you presented, would that translate to some dynamical measurements on magnets? Like, how would that show up?
Oh, so what the claim is that the chaos timescales and length scales determine things like diffusion constants. Okay, so diffusion constants are things that you can measure in 2-point correlators, right?
I see.
The dynamic 2-point correlators.
So some spin transport or something.
Yeah, not spin transport, just dynamic correlation functions.
I see. So just regular dynamical structures.
Yeah. So the point is that the decorrelator is not really you can try to think about protocols to measure the decorrelator itself, but I think that the point that I'm trying to make is that even though that is a different line of questioning, the point is that the timescales and length scales that come out of the decorrelator go on to fix the timescales and length scales of transport that you can measure by linear response calculation of the usual 2-point correlators.
I see. Okay, thank you.
Okay, I think, thanks, Shumiran. So I think, okay, thank you, Shubhro. I think we'll stop here for your, because, running out of time. So we'll so let's thank Shubhro again for this wonderful talk. And let us go to the next speaker, Prabhakar. So Prabhakar, could you please share your screen?
Yes.
Okay, we can't. So now
hello.
I see your.
Hello.
Hello. Yeah,
can you see my screen?
Yeah, I can see your screen. So so you can start now. So I'll let you know at 9 minutes.
Okay.
Okay, you have 10+2. Go ahead.
Okay, thank you. So first of all, I would like to thank the organizers to giving me this opportunity to present my work in this conference. I have done this work with my supervisor, Dr. Anamitra Mukherjee. Topic of my talk is the recursive approach for the bound complexes in many-body systems. So this is the outline of my talk. So first, I would talk about the novel approach for the many-particle Green function. Then I will discuss its advantage over ED. And of course, from our method, one can extract 1 and 2 particle excitation spectrum. Finally, we will apply our method to study the bound complexes, especially the few-hole bound complexes in a many-body ground state, which can be relevant to the few-body spectroscopy, like OJ scattering. In OJ scattering, an X-ray creates a core hole, which decay in a pair of valence hole, and an electron goes out. So finally, we have a 2-hole in a same atom. So our theoretical goal is to study the 2-hole local spectra in many-body ground state. So now I'll briefly talk about the quantities of our interest. So we considered the expectation of the resolvent in a many-particle basis, and we are denoting it by G. P is the number of particle, and A1 to AP are the site labels. Here I have shown a real space basis element. It is calculated over all the basis element. From this G, one can extract the information about the exact spectrum and also the P particle density of states. We also derived the relation between the expectation of the resolvent and usual single and two particle green function. From there, one can extract the single and two particle spectral function. This kind of studies, this kind of ideas are used in a recent study by D. Logan group. So now I will talk about our method. So in our method, we reorganize the Fock space such that the standard recursive green function can be used. So I will explain our method by using example of 8-site lattice with a 4 spinless particle. So here I have shown a basis with the restriction that 2 particle is on the left side and 2 particle is on the right side. This basis can be represented by this column vector 0 to 0 2 and labeled by A. With the restriction of 2 particle on the left and 2 on the right, there will be such more column vector labeled by B to I. And these column vector are connected to each other via nearest neighbor hopping. And we call this whole thing 2, 2 particle sector. Similar to this particle sector, there will be some other particle sector like 3, 1, 4, 0, and 0, 4. We arrange these particle sectors such that they connect to each other via nearest neighbor hopping. So finally, our Fock space mapped into a matrix, matrix valued 1D lattice connected by nearest neighbor hopping matrices tau. Of course, we considered the hard-walled boundary conditions. Basically, to calculate the expectation of the resolvent, one need to invert this G minus H matrix. So here I have shown this matrix, and these blocks are the blocks I showed in the previous slide. So basically, a recursive green function contains the forward recursion and backward recursion. During forward recursion, the block 1 enters as a self energy in a block 2, giving rise to the left connected green function of block 2. And forward recursion, we use this formula. So in this way, when we reach to the block 5, it turns out that the left connected green function of block 5 or the fully connected green function. Then we use the backward recursion formula, and we start from the block 5. One can calculate the all diagonal blocks, and once you have the diagonal blocks, all the off diagonal blocks can be calculated. A couple of things you can note here. There is a inversion involves only the forward recursion. Backward recursion is the just multiplication of the matrix, and instead of inverting this whole matrix, I need to invert these smaller blocks. So instead of inverting this NCP dimension of matrix for P particle and N sides, we need to invert this N by 2 C P by 2 square dimension of matrices. Our method has some advantage over the full exact diagonalization for Hopf filling. So here I have shown the dimension of matrices versus the system size. You can see that for n equal to t, there is a drastic reduction in the dimension of matrices. So instead of inverting 2 lakh dimension of matrices, here we need to invert the 18,000 dimension of matrix. So which reflect in a reduction in RAM. Instead, so here we get reduction in RAM about 250 GB. And also our method allow for the parallelization. One can also use many approximation schemes. We used our method to study the impurity model and a periodic model. So this is our Hamiltonian. I will explain it with the help of this picture. So here these yellow sites represented by I1 and I2 are the impurity site. We call them the TM sites. U and delta is the nearest neighbor interaction and on-site energy respectively. We call all the other site by bath sites, and the corresponding Hamiltonian is represented by HB and STM, and the hybridization between these two are represented by H hybridization. So here we assume that all the hopping strengths are same, and we will vary U and delta to see the interesting physics. Of course, our system, we consider the hard-walled boundary conditions. In a repeated system, these impurity sites are repeated periodically. So our goal is to study two-hole bound state on a TM sites in a completely filled system and in a partially filled system. So here, let's discuss our results. So here I have shown a two-hole TM spectrum calculated on this site by this formula. Actually, we derived this formula. Let's understand these features. So when two holes will be on the impurity sides, there will be reduction in energy by -2 delta minus U. And for our parameter, you will get a peak around -12. When one hole sit on the impurity sides and one on the bath, there will be reduction in energy by -delta minus U. And you will get a band-like feature around -8. When the both holes will be on the bath, you will get the continuum-like structure shown in this inset around 0. We also calculated this two-hole TM spectra in a fully filled background in a repeated in a periodic system. So you can see that the local TM site spectra remains the same. That's why the impurity model works. But the features around -delta minus U and around 0 instead of band-like feature, we are getting these peaks which correspond to the eigenvalues of the unit cell. So to check that, we increase the size of the our unit cell. I have shown here. So we found that feature around -delta minus U and around 0, we get more peaks corresponds to the eigenvalues of the unit cell. So we also calculated the TM spectra in partially filled band.
9 minutes.
Okay. So we also calculated the two-hole TM spectra in a partially filled background. So here, this figure shows the two-hole TM spectra calculated on these impurity sites. In both periodic and impurity cases, we get a band-like feature around -delta. This can be understood by these cartoon pictures. In ground state, actually, we have configuration like these are the TM sites and these are the bath sites. So ground state is like 1 0 1 0 1 0. So, and there will be such many states. So, there will be such many states, and we are looking at the two-hole spectra on these sides. So in case of impurity, we found that the ground states are like that, where two holes sits on the TM spectra, TM sites, and there are many such states which due to mixing of these things, we get a broad band around -delta 5. In case of periodic system, two holes sits on the transition metal sites, but there are many such states due to which we get a broad band around omega equal to -delta. Yeah. So I will conclude my talk. So we propose a novel ways to study the many particle systems. It is numerically exact, and there is a large suppression in the RAM requirement. Also, we checked the ground. We did the ground state comparison with the ED at half filling for 18 sites. So we found that within numerical precision, ground states are exact. Within numerical precision, ground states are the same. We apply our method to study the application of the few holes in the bound states. In the field background, we found that there's a clear signature of two-hole bound state spectra, and the impurity approximation holds good. But in case of partially filled band, there's a considerable broadening due to mixing with the many low energy states, and the impurity approximation is poor. So, yeah.
Okay, thank you, Prabhakar. So we'll have time for questions. Anybody has some question, please come forward. Okay, so Prabhakar, so I have some questions. So this method you can also use. So actually, two questions. So this two-hole bound state that you get. So do you think, I mean, it will survive? I mean, even at higher system sizes, I mean.
Actually, we did it on 32 on the 32 system size. So a lattice of 32 sides.
Okay.
So I think
so these are seen experimentally. I mean, like there
are analytic study on these kind of things. Actually,
okay.
I don't know about experiment, but there are analytic studies on this kind of.
Yeah, another question is, since there is no other question, so from other people, so yeah, so transport, so you can also calculate transport with this, right? I mean, have you calculated, or like some transport quantities?
We haven't calculated, but yeah, one can calculate by using our method.
Okay, good. Yeah, thanks. So I think, yeah, so let's thank Prabhakar for a nice talk and interesting work. And let us go to the next talk. So next speaker, Mona Lisa Singh. And so Mona Lisa, if you have your, can you share your slides?
Yes, sir.
Yeah. Okay.
So can you see my slides?
Yeah, I can see it. Please make it full screen.
Yes.
Okay, so our next speaker is Mona Lisa Singh from SN Bose Center. So Mona Lisa, sorry, I can't see your slide now.
You can't see my slides?
No, it was visible without the full screen mode, but now it's gone.
Okay. Let me reshare this. Is it visible now?
Yeah, it is visible. Yeah, but if you make full screen, can you make full screen? Yeah, and then it's not. Now it's visible. Okay, great. Okay, so so Mona Lisa will be talking about FFLO phase in interacting one-dimensional Fermi gas. Mona Lisa, go ahead. So I'll give you I'll tell you at 9 minutes.
Okay, thank you, sir. So let me begin by thanking the organizers for giving me the chance to present our recent work here. So let me start right away. Whenever we are thinking about quantum gas, what we have in mind is a non-interacting ensemble of quantum particles, which can be easily solved using tight binding like model, nothing interesting. But during interactions, and we get a very rich variety of phases, metals, insulators, superconductors with different kind of pairings, and the rest of it. So now, over the last decades, physicists have a very new tool in their hands, which is ultra cold atoms in optical lattices, which has now allowed us to see quantum many-body physics in action using Hubble-like models. So before I go to the work, let me recount some of the milestones in our journey to this point. So in 1911, more than 100 years ago, superconductivity was discovered. Bose-Einstein condensation was predicted theoretically in 1925, and the phenomena of superfluidity was demonstrated in liquid helium in 1938. It seems fairly recently that in 1995, Bose-Einstein condensation was achieved in atomic gases, and in 2005, superfluidity was definitely demonstrated in cold atomic gases. Now, this is important because this is the platform we would be basing our models on. So it was shown that in atomic gases confined in optical lattices, towards this attractive interaction regime, at very highly attractive interaction, we have this Bose-Einstein condensation. Whereas for dilute attractive limit, we have this BCS-like phases. It was shown by Liao et al. That introduction of magnetic field in this system, for very small values of magnetic field, we have this BCS phase intact. But for very strong magnetic field, we have a fully polarized system. But in the intermediate regime, there could be this partially polarized phase, which they call as the FFLO phase. So let us see what they mean by it. So just offhand, superconductivity brings to mind the images of pairing of fermions with opposite spins, no net momentum. But can superconductivity coexist in presence of magnetism? Because magnetism is a destroyer of superconductivity. So if they could coexist, we would be saving tons of money in order to not maintain that pristine condition. So is it possible? It was answered in 1964 by Fulde-Ferrell and Larkin of Shenikov. They showed that at low temperatures and in very high magnetic field introduces imbalanced spin population. It flips one spin to the other side. So now they are not equal in population. But there can exist a special condition where superconductivity is still present in the system, notwithstanding this imbalanced spin population. And they showed that in this phase, there can exist bound pairs with non-zero total momentum. And this would lead to spatially modulated order parameters. And so far, it has been observed in organic superconductors, layered superconductors. But all these are very difficult to realize because of the stringent conditions associated with maintenance of the material. So they observed this FFLO phase in this organic salt, and this is again at low temperature and high magnetic field as expected. But because these conditions are not very easy to maintain, is there an alternative platform? Turns out there is. So optical lattice is an artificial crystal created by superimposing orthogonal laser fields, creating this standing wave pattern of light maxima, and atoms can be trapped in these lattices. So various phenomena as superfluidity, Mott insulator phases have already been seen in here. So we would take advantage of this picture, and we shall go back to the recipe where we already know that in a Hubbard-like model, introduction of magnetic field simply splits the up and down spins bands, whereas introduction of only SOC field will just tear up this momentum. But when both of them are present, then there can exist this very special condition by tuning this effective Fermi energy between these two. This can, in principle, give rise to this edge conductances and a topological phases. So our goal is to first see whether we can find FFLO phase in such a setting. Then whether in the FFLO phase we can discern any signature of such topological phases. So for that, our model is a Hubbard model with attractive interactions. We have a Zeeman field and perpendicular to it, SOC field in the X direction. We have solved this model using exact diagonalization for smaller system and DMRG calculations for larger systems. So first off, let us have a look at the charge density and spin density. So at very low magnetic field, we see that there are only these, NIs are the charge oscillation, there are only these, no magnetic oscillations in the system, whereas increasing the magnetic field for some intermediate values give us commensurate charge and spin densities. Whereas very high magnetic field gives us this fully polarized phase. It's completely polarized, but just before this fully polarized phase, we again have this phase where it is still partially polarized, but we have this maxima in between and oscillations towards the end. So an alternate picture of the same thing would be to think in terms of up and down spins. What we have here is in the BCS overlapping up and down spin expectation values. In the fully polarized phase, only one species exists here, the up one. Intermediate values, we have oscillations, commensurate oscillation in both the up and down species. So here we find that FFLO phase can exist with intertwined spin density and charge density order for moderate values of magnetic field. So next, because we know that this FFLO phase is characterized with non-zero momentum, what we do, we find the singlet pair density correlation and take its Fourier transform. So what it gives us is at the BCS phase, there is a single peak structure as is to be expected. But in the FFLO phase, this partially polarized phase, actually, we have this exotic two-peak structure. At this is at finite k, not k is equal to 0, symmetric, and at very high field in the fully polarized phase, we don't expect it. So let us now look at the effect of on-site interactions. So because our U here is negative, we expect that you would be promoting BCS-like order. It would like to keep the pairs forming. So that's what we see here. at this orange one, very dilute U, we see that we have already reached this FFLO kind of order. But very strongly attractive U minus 4, we have a single peaks BCS structure. Let us have a look at what electronic density does. So these two were calculations at quarter filling. So we find that at quarter filling and these electronic densities, we are in the FFLO phase, but for the same parameters at 0.1 density, which corresponds to 2 electrons per 10 orbitals, we are in the fully polarized phase. So that is because for lower electronic population, we need less magnetic field to go to the FFLO phase. So FFLO phase is there also in the dilute limit, but at lower magnetic field strength. So let us see if we can just explain that in one picture. So what we have done here is at quarter filling, we present the phase diagram of this model in the phase space of magnetic field and on-site interactions. So as expected, this U promotes our BCS order. So for larger U, we need higher magnetic field to break the pairs and go to the FFLO phase. Whereas just before this fully polarized phase, we have this thin strip of we are calling it trivial partially polarized phase. Here it is just staggered odd even kind of oscillations. So up to here, it was what happens in absence of SOC field. So let us see what happens in presence of SOC field. So this is at finite SOC.
So Mona Lisa, 9 minutes.
Okay. So here again, we find that the U as before promotes the BCS kind of order. But this alpha, this finite value of SOC field is also promoting superconducting order, because as we are increasing this SOC field, now we need larger magnetic field to go to the FFLO phase. And also in between the FFLO and BCS phases, we have this exotic three-peak structure, which is a mixture of BCS and FFLO. As before, when we look at the effect of electronic densities, we see that at lower densities, it is easier to go to the FFLO and fully polarized phase, whereas at larger electronic densities, we are still at the BCS phase. But it can be realized just using larger magnetic field. Now, another important thing, because this platform has been proposed to host a topological phase, we check what happens to the energy gaps. So what we find is that this alpha 0.05 corresponds to the FFLO phase. We see that it goes linearly with system size, whereas larger alpha, where it corresponds to the BCS phase, we have this gap which is expected of the BCS phase. So no exponential decay of energy gaps. So I will just directly come to this phase diagram. So the addition of this SOC field gives us this another thin strip, which is a mixture of BCS and FFLO, where this system gradually goes from the BCS to the FFLO phase, single peak to two peak structure, and the rest of the physics is the same. So let me recount some highlights of this work. So here we show that this FFLO phase spans a large area of the phase diagram for different magnetic, different U, different electronic densities, and different SOC field. And we show that just before the fully polarized phase, we have a phase which shows just staggered order, but it is still partially polarized. Another thing we note is that introduction of SOC field gives us this thin strip of mixture of BCS FFLO phase, which is characterized by three-peak structure in the Fourier transform of the pair density correlations. And we find no exponentially decaying gaps in the system, which was expected in case there was some topological phase in the system. So in a separate work, we have shown that this exponential energy gap can exist, but in presence of a harmonic potential. So these are some of the references. Summing up, we showed that there can exist 4 different phases in a spin orbit coupled 1D interacting Fermi gas, BCS phase at low magnetic fields, and the moderate magnetic fields giving us a partially polarized phase. There can exist this FFLO phase. And just before this fully polarized phase boundary, we have this trivial partially polarized phase, just staggered order, just before it enters the fully polarized phase. And this FFLO phase gives its signature in twin peaks in the momentum resolved spectra at finite K. And it also has commensurate spin, charge, and pair density orders. And this phase spans a large area of the parameter regime, and we do not find any exponential gaps. So some things we are working on right now is dynamical signatures of this FFLO phase. We also want to check how robust this phase is in response to impurities, because experimentally it has been said that this is supposed to be a bit fragile. So we have to check that how it responds to impurities. Next, we are trying to extend these studies to 2 dimensions and present a phase diagram there. And finally, we would like to present a phase diagram of this system for finite T. So I thank my supervisor, my group members, and thank you for listening.
Okay, thank you, Mona Lisa. So we can have one question maybe.
Yes.
Hi, Shumilot. Can I ask a question?
Yes, please go ahead, Shubhu.
Sorry, I missed the first part of your talk. This U that you put in is an on-site Hubbard?
This is on-site Hubbard, yes.
Yeah. Is that the reason why you, cannot open up any of these P plus IP type of superconductors?
Actually, yes. So what we are trying to do is, we were trying to do that with SOC field instead.
Yeah, but maybe another way to do that is density-density interactions with the right sign and decouple it in the nearest neighbor BCS channel. I don't know. I mean, so is that so that might be the way to stabilize the P plus IP. Do you have a comment on that?
Not
In
right
presence
now,
of a
but
magnetic field?
may I talk to you after regarding this?
Sure.
I would like to know more about.
Yeah, sure.
Okay, any other questions? Okay, if not, let's thank Mona Lisa for a very nice talk. And let us go to the last talk of this session by Shivaram Ruidas. So Shivaram, if you can, thanks Mona Lisa. So Shivaram, can you please share your...
Yeah, I'll do it.
Okay, so next talk will be given by Shivaram Ruidas from Indian Institute of Science, Bangalore, and he'll be talking about many-body chaos and transport in 2 dimensions. So Shivaram, your time starts now, and I'll give you, I'll tell you at 9 minutes from now.
Okay.
Go ahead.
Yeah, so I'll talk about this many-body chaos and anomalous diffusion across thermal phase transition in 2 dimensions. So you see there are a lot of terms are there. I'll try to explain this one by one, but if you want to find it in detail, you can go to this preprint archive. Okay, so many-body you all know that is interacting. So I'll start with chaos. So what is chaos? So to start with, I'll show you one quote by Edward Lorenz, who was a pioneer in this field, which says that when a present determines the future, but approximate present does not approximately determine the future. So the essential idea of chaos is that it is very sensitive to the initial conditions. I mean, if you change it very slightly, and it can have a very large effect at some later time. Okay, so that is why this kind of metaphor became very popular at the time, which says that if a butterfly flaps its wing at some point, then can it create tornado at some other place? So which is not true basically, but anyway. So what is the essential idea? The essential idea is this: so you have a dynamical system. You start with some initial condition, and you have this Newtonian trajectory, and then you change the initial condition very slightly. Then you see that the trajectory is very different from the earlier one, and this difference diverges exponentially like this. And so by now you might have seen this plot from Subhra's talk. So basically, if you create this perturbation here, you will see that this chaos front actually propagates ballistically in linear in space with time with a velocity vb. So among various parameters, there are 2 important parameters of our interest. One is the Lyapunov exponent, another one is butterfly velocity. What is the motivation behind our project? So there are very recent studies in condensed matter system on this chaos and all. So there was this by Mandelsson and Shankar, which says that this Lyapunov exponent cannot be greater than this value. There is an upper bound for this Lyapunov exponent for quantum systems. Okay, so obviously it becomes very interesting to ask how this lambda tunes with H bar. So another one is this phenomenological connection that Subhra was talking about between chaos and transport. So whether we can relate this diffusion constant with this v square by lambda kind of expression or not. And so we all know that condensed matter is always gifted with some very exotic phases and phase transitions. So can we have any effect of chaos on these phase transitions? Can we basically identify different phases via chaos or not? Okay. So for a dynamical system, we have this early time, and there is this long time sets in. So can we connect these two regimes with this chaos or not? So these are some of the questions I will try to explain in this talk. So let's start with the model. So our model is very simply this is simply classical anisotropic Heisenberg Hamiltonian defined on a 2D square lattice. So you see that these x and y components are isotropic; their couplings are same, but we have an anisotropy in the Z coupling. So due to that anisotropy, we get these two different class of phase transition. One is Kostelis-Thouless, another one is this Ising case for these two different values of anisotropy. One is greater than one, less than one, and greater than one. Then as the spins are classical here, we can easily define a dynamics over it and using this Poisson bracket. So that is basically physical dynamics around its local magnetic field defined by this nearest neighbors. So there is this construct of motions. One is total energy, and another one is this total component of total spin component of Z component of the spins, which will be interesting as I go along. So now to get this effect of chaos and catch up all this effect, we need to define some function. So this was done by this Abhijit Das and Subhrata, their paper. So they defined this function called decorrelation, which is basically defined like this: 1 minus this thing. So this is defined on each spatial point and time, and there is this A and B are the two copies. So basically we have these two copies of the same system, which are defined very infinitesimally at initial time by an amount this, which is a local perturbation we are giving, okay, which is the initial constant difference that we are putting. And this is a thermal average, which is basically drawn from this initial condition by Monte Carlo. So this decorrelation function can give us two parameters, this Lyapunov exponent and butterfly velocity, how I will explain later. And there is this spin-spin correlation function, which is defined like this, okay, which can give us these dynamics of excitations. So from this correlation function, by summing over these spatial sites, we can get this spin-spin autocorrelation function, which will have these two different time regimes. On its intermediate time, we will have this exponential dependence over some time scale tau, and at large time, we will get this 1 over t to the power law dependence. Now, this depending on the value of alpha, we can have this diffusive or non-diffusive behaviors. And by Fourier transform this quantity, we can get the structure factor, which will also be useful later. So I have defined all these parameters, and on this, depending on all these parameters, I have tried to summarize our result in this schematic phase diagram. So where you see in this x direction, we have these coupling parameters, and in the y direction, we have this temperature. So so in this all these four regimes, you see that we have shown that this chaos always spreads ballistically. Always chaos, the spatial is dependence always linear with time. And this Lyapunov exponent is has this square root of t dependence at high temperature for all these anisotropies, and low temperature we get this kind of power law dependence. And there is a crossover from diffusive to subdiffusive from transport perspective for this KT case, and in this case we get this diffusive to subdiffusive, and also from subdiffusive to superdiffusive kind of crossover. So this thing you will understand as we go along. Yeah, so basically we have these initial conditions which are equilibrated from Monte Carlo, and we evolve this system using some numerical technique, and then we calculate this decorrelation function. We have taken these two anisotropies. One is this easy plane case we're naming, which is 0.3, and another one is the easy axis case, which is 1.2. So this is the color plot shown for this decorrelation function, okay, for these two different temperature along with this 1D cut along for this easy plane case. So we remember we defined this decorrelation as 1 minus this dot product. So if it is, so this color represents decorrelation. So when it is 1, that means that these two copies are uncorrelated. That means the chaos frontier is already propagated. So initially you see there is that happens nothing. So we are creating this initial condition difference here, and there happens nothing for this time, and then this chaos sets in, and then we see that this front propagates throughout the system. And same thing happens at low temperature. We get this similar behavior, but it gets delayed at low temperature. So motivated by this, we write this decorrelation function using this kind of exponential form, as it should be exponential, using this kind of generalized Lyapunov exponent. And the main idea is to extract the Lyapunov exponent, which is the maximum Lyapunov exponent here, and which is defined at side 0, which we can get from here. So that is a log normal plot for this decorrelation function for these different sides. So you concentrate on this 0 side, you see that there is a clear exponential regime which you can fit and get this Lyapunov exponent. So that we have done for different temperatures across the transition for these two different anisotropies. We see that this is for easy plane case and this is for easy axis case. We said there is a clear crossover across the transitions. We get this high temperature square root of T dependence here, also here, and we get this low temperature phases in power dependence here. So there is no such financial effect, but there is, we can definitely identify two different phases from this dependence. Okay, now how does chaos spreads? Okay, so now from our definition of decorrelation function, we can write this generalized Lyapunov exponent as this. Okay, in terms of we just in this ln form, we see that when this dxt is around epsilon square, we get this lambda xt to be 0, right? Okay, now so if we try to trace out this lambda xt 0 contour, we see that there is this kind of light cone behavior across all the temperature from high to low. Okay, so from this we can say that this chaos actually spreads ballistically. So to further probing, we have tried to scale this Lyapunov exponent, generalized Lyapunov exponent to this kind of linear scaling, and this scaling actually works very well. You see that near the this light cone edge, we get this clear collapse. And so to find the velocity at which the chaos front propagates, we just need to scale this, feed this line with this linear scaling, so that we can get this butterfly velocity. So this is what it shows. So we get this dependence of butterfly velocity for these two different anisotropy. We see that there's a clear minima at the transition, and this is the only sharp transition that we get in terms of chaos. Okay, this is the only effect, sharp effect. So far so good. So now let's connect with the long time dynamics. So to get it, we will calculate this autocorrelation.
So Shivram, 9 minutes.
Yeah. So we will calculate this autocorrelation function, and depending on the conserved mode of the system that we have, like for the Z component, we will see that these Z components will have a diffusive mode. I mean, when this is around 1, and that's what this plot shown here. We have plotted this alpha T with temperature for the different anisotropies. We see that for KT case, it is always at high temperature, you find it to be diffusive, but across the transition, we get the subdiffusive behavior. Now for the easy axis case, we find that this is like from the high temperature diffusive to get this subdiffusive behavior, and across the transition, we get the super diffusive behavior. So these are the two different anomalous diffusion that we found out here. Now also from this XY component of this correlation, we can find out this time scale tau, which is plotted in green here. We see that across the transition, there is a clear divergence, that there is a critical slowing down. So, but the chaos is always remain unaffected. Now to connect with the diffusion constant, we have connected we calculated the structure factor, and then from it we have calculated this d from the exponential dependence, and we have compared it with this VB square by for lambda. And you see that we have shown it for this easy plane case. We see that this is not very good agreement with each other. There is a qualitative and quantitative difference, but at high temperature, these two matches, but it doesn't match for the easy axis case. So it raises the question about the physical origin of this d tilde. What is the actual behavior of this tilde for this model? So to summarize my talk, so there is definitely, it could be additional tool to characterize the different phases. So we can get these different crossovers from this using the chaos. And while this chaos always spread ballistically, we always find that this dynamical correlation is very different for this low temperature, for this KT ionizing cases. And from this heuristic background, this decorrelation function we can write it using separable answers, like we can separate out this exponential growth and we can put in this diffusive form. Then we can write this Lyapunov exponent as this, which will equal these two parameters. But what we found out this d tilde is different than d, and this is because we are getting this kind of anomalous diffusion at low temperature. So this is similar to the quasi and without quasi particle that Subhrata was talking about for these different symmetry and symmetry unbroken phases. And so in absence of any theoretical understanding, obviously this kind of results motivates us to work with these new theoretical frameworks. So this ends my talk. Thank you for your attention.
Okay, thank you, Shivram. So if there are any questions,
Shmulat, can I ask? Sorry.
Yeah, please go ahead.
I think Ravi has his hand up, so maybe Ravi can ask.
Okay, Ravi, maybe go ahead then.
Yeah, I have a trivial question.
Yeah.
What was the picture that you started out the talk with in the title slide?
Oh, that picture was something like this. So it was meant to put it like if you start these different conditions, these are like trajectories. So you will get this kind of very different trajectories if you start with some different initial conditions. Just an abstract idea of chaos.
Sorry, Sumilan, can I now ask my question? Sumilan?
Yeah, please go ahead. Yeah.
So this bound on the Lyapunov exponent that you mentioned, I know this is not your work, but in the quantum case, in one of the earlier references. Yeah, so this doesn't have any dependence on the specific system you're looking at, what the Hamiltonian is or anything, and what is the basis of this result?
So you are asking about what is the basis for this bound?
Yeah.
Okay, so that bound, they have calculations very difficult. Actually, I couldn't follow what is the, but essential idea you can see that for this quantum system, we get this, we have this, what is it say, uncertainty principle, like we cannot make this, there is always bound. So the measurements are always bound by uncertainties, right? So that's what the main essential idea, but I don't know, I'm not very, I don't know what is the essential idea.
Yeah. Okay, no, I don't know either. I just wanted to, okay, fine.
Okay, yeah.
Okay, Shubhro, if you have, if you want to ask.
Yeah. Okay. So the Shubhram, can you just go to this slide where you were pointing out the 4 regimes of your calculation? Yeah, so it's slide 6. Yeah, okay. So in this green part, I have 2 questions. One is that with what certainty can you say that this Lyapunov exponent is power law in temperature and not exponentially small? And B, when you say super diffusive, so there is this long range Ising order. So are you talking about the diffusion of the transverse fluctuation and saying that they are super diffusive?
Yeah, basically we have already only calculated the Z component, so maybe that is the transverse component. That is fine.
No. So do you calculate the longitudinal component or the transverse component?
No, only transverse component.
So the XY components?
No, the ZZ component in the
Yeah, ZZ is not transverse.
Oh, sorry, yeah, that is longitudinal. Yeah. Sorry, yeah.
So you calculate, so do you know what happens to the transverse components, the XY components?
No.
The ones that doesn't order?
Actually, we have calculated that correlation. It actually shows this kind of exponential dependence with time at above the transitions.
Yeah, because that's higher up in energy. I see. So, and what about the Lyapunov? Do you, on what certainty do you have that it is power law and not an exponentially suppressed? Because of the same kind of ideas that the system is gapped.
Actually, you see this, we haven't gone very much less temperature here, and it is around this. So I for this larger system size, we see that we can get this kind of
I see.
fitting for this exponential.
Yeah, I think temperature is too high for that.
Yeah, temperature is very high.
But I mean, if I just try to fit it with an exponential, how bad it would look? I guess that's another way of asking the question.
Okay. So I think it will be not, it will not match very good because I have tried it, but I cannot.
Okay. Thanks.
Yeah.
Okay. So I think thanks, Shibram. So any other question? Okay. Anyway, I think we should end.
Can I ask a quick question? No.
Okay. Very quick question.
Yeah. So actually, all Shivaram. So whatever you presented is for the classical XSZ, right?
Yeah.
So do you know how much of it survives if you think of the quantum model, corresponding quantum model?
There are studies on XSZ quantum model where, but I mean the calculation that I have presented here, it's one can, but quantum calculation for these decoherence functions is like you can do it in a different perspective, not like that, not like the way I did from this trajectory, because quantum there is no trajectory. But yeah, one can do in quantum case also and see how things change.
Yeah, I mean, as far as the different phases are concerned and different parameter regimes, is there any study or do you have any intuition? Like,
Sorry, what?
I'm saying you were showing these 4 different phases
Yeah,
and the
yeah.
of anisotropy and temperature. So, do you have any intuition or if there is any work from other group for the corresponding quantum system and how this schematic diagram is?
Kind of no, we haven't find any quantum correspondence for this thing. We have done this simple classical. We are not.
Okay, Shivram, can I make a comment? So,
Yeah,
Arti, so I think the thing is, in 2D, there is no quantum way to solve, access this problem. I mean, you can do some truncated Wigner or something, maybe. In 1D, I mean, this kind of model typically, I mean, first of all, I think any quantum model people have studied like spin-ups and all, they are not chaotic. Okay, meaning that you don't get e to the power lambda LT. So it seems it only happens in the semi-classical limit when you take S tending to infinity, which is the model he's studying.
Okay.
So it's not clear how to connect these two ends, basically. Yeah.
Okay, thanks.
Yeah. Okay, I think we'll end here. So thank you, Shivram, and let's thank all the speakers of this session. And yeah, so I'll if Anamitra has any announcement, so let's close this session and go to Anamitra.
Let me thank all the speakers and all the chairpersons for carrying the day smoothly. So we'll start at 9 a.m. tomorrow. I think the first session Aarti is chairing and the first talk is, I think, Rajdeep's. So I'll see you guys at, we'll see you at 9 tomorrow. Okay, so then I'll